Welcome to Software Engineering. Are you interested in learning about software engineering? Does finding out more about the software building process appeal to you? Would you like to get more information about software development? Does learning about the basics of programming interest you? Would you like to know more about software architecture and design? Or have you ever wondered what the job prospects are like for a software engineer? If so, this course is for you. According to the most recent U.S. Bureau of Labor Statistics report, about 1,850,000 software engineer-type jobs are posted annually in the U.S. alone, and job growth in the industry is projected to increase 22% through 2030. At the time of this course publication, the median U.S. software developer specialist salary is $110,140 annually, and per hour pay is almost $53. Software engineering jobs are also a great way to start on your path to a high-paying career in information technology. This course has 3 instructors, Rav Ahuja, Bethany Hudnut, and Lynn Joyner. Rav is a global program director at IBM and the architect for several IBM professional certificates. Bethany is an instructional designer at SkillUp Technologies, and Lynn is also an instructional designer at SkillUp Technologies. So, what's in this course? It's divided into 5 modules: the Software Development Lifecycle, Introduction to Software Development, Basics of Programming, Software Architecture, Design, and Patterns, and Job Opportunities and Skill Sets in Software Engineering. When you complete this course, you'll be able to describe software engineering and approaches to software development, identify software development tools and technologies, compare different types of programming languages and recognize basic programming constructs, outline approaches to application and deployment architectures, and review the skills required in software engineering and describe the career options it provides. During this course, you will learn through guided instructional videos that walk you through key concepts with essential need-to-know facts, interactive exercises to reinforce what you've learned in videos, insider viewpoints that enrich your understanding of IT support work, practice assessments to help you gauge your knowledge, and finally, graded assessments to prove what you've learned. Upon successful completion of this course, you'll earn a shareable badge and certificate that you can show to prospective employers. We're here to support your success. If you have any questions for the course staff, or if you want to connect with your peers in this course, please feel free to post on the course discussion forums. We're excited you're here, so let's get started. Welcome to Meet the Experts. In this course, you will learn from several experts in various roles who will provide their insights and perspectives about software engineering. Let's meet these experts and learn about where they work and what they do.
Hi, my name is Kadesha, and I currently work as a developer advocate at GitHub.
Hey, well, my name is Liseli Bueno. I'm a software engineer, and I work at Blend, also known as Blend Labs.
My name is Tommy Young. I'm a software engineer at Google. My role is Uber technical lead, overseeing publisher video ads.
My name is Diane Panagiotopoulos. I am a research and development engineer at Bandwidth, and I work directly through Bandwidth. I am not self-employed as like a contractor with them.
Hi, my name is Zubin Pratap. I'm a software engineer and currently I'm a developer advocate at a Web3 startup.
My name is Daniel Rudnitsky, and I'm a full-stack software engineer at IBM.
My name is James Reeve, and I'm a full-stack software engineer at IBM.
Hi, my name is Rupinder, and I work as a Chief Solutions Architect at SkillUp Technologies.
Hello everyone, my name is Upkar Litter, and I'm a developer advocate with IBM.
Hi, I am Jan Stoneman. I'm a solution architect at Smartronix.
Now, let's listen to some of these experts describe a little more in detail about what they do.
Yes, so a developer advocate is a software engineer who enables developer to be successful with a product. That was a mouthful, so essentially what that means is, for example, at GitHub, I create a lot of content. So I will do blog posts, workshops, go to conferences to speak about GitHub, the product. I'll also showcase developers in the open source community and to like give publicity to the projects that they're working on. And being an advocate means that I'm able to communicate deeply about technical concepts in a way that's digestible for engineers across experience level to understand. Before I was an advocate, I worked as a software engineer in the finance sector for 2 years. I spent a majority of my time coding. I primarily worked on the front end of the application using tools such as Git, Docker, GraphQL, React, JavaScript, and the very few times I would go into the backend, we use Node.js on our backend to make changes and updates. My experience as a software engineer and also as a technical content creator paved the way for me to become a developer advocate at GitHub today.
I'm a software engineer right now. I'm still pretty junior, so most of my tasks involve creating new features, fixing bugs, and addressing any customer concerns that we have that they have with the current software.
Yeah, so I work on a suite of products that are they're targeted to large content creators, video publishers, customers such as ESPN, Disney, etc. And we basically have suites of tools to help them monetize their video content, help them distribute it, help them target it appropriately, report on it, troubleshoot it for across all devices, all surfaces. So it's kind of a full suite of products. It starts with the user interfaces that their sales teams and trafficking teams use to sell the ad space, upload the creatives, the advertisements, and target them to their audiences and contextually to the content that that they create. We offer reporting on that, so a lot of it's performance and various other analytics, reach analytics, and so forth.
Previously, before this, I was a software engineer at Google, and before that, I was a software engineer at a small startup. But before that, for about over 15 years, I was a corporate lawyer and then a business executive for a while, and I even had my own startup in the middle. So yeah, very diverse background. And I taught myself to code in my very late 30s when my startup started to fail, and I really needed to keep it going, and my tech co-founder quit. So that's what I do, that's who I am. Today, as a developer advocate, I not only write code, I also produce a lot of educational content and material that is useful for people to onboard onto Web3 and other technologies. And my role is really to help connect the product team with the actual developer ecosystem, bring the two together through code, content, education, and community.
Welcome to What is Software Engineering? After watching this video, you will be able to define software engineering, list the responsibilities of a software engineer, and compare and contrast software developers and software engineers. Software engineering is the application of scientific principles to the design and creation of software. The field uses a systematic approach to collect and analyze business requirements in order to design, build, and test software applications to satisfy those business requirements. When computing began in the late 1950s, software engineering was a relatively undefined discipline, but over time it transformed into a modernized engineering field. The software engineering field became a discipline in the 1960s and evolved as new technologies were developed and the approach to software development became more scientific. Trends in software engineering transformed from ad hoc programming towards more formal and standardized methods. Initially, the creation of software lacked a formal development process. As the world widely adopted computers, software became increasingly integral to more aspects of life. The inefficiencies in the software development process made it difficult to meet the rapidly increasing demand for computing resources and complex software. This led to what is known as the software crisis, which began in the mid-1960s and lasted until the mid-1980s. During this period, software development often ran over budget, behind schedule, and consisted of unmanageable, buggy code. By the time older software solutions came to fruition, newer, better, and faster technologies had already been developed, causing software engineers to have to refactor their code or completely redesign their system. Often software development solutions that worked for small software systems did not scale to large complex projects. Now, some of these issues still exist today, although to a much lesser extent, due to the consistent application of engineering principles to the software development process. Computing resources have become more widely available, and standardized methodologies for software development allow for large complex solutions that scale. The solution to the software crisis involved transforming unorganized coding efforts into an established engineering discipline. The mid-1980s also saw a rise in the growth of computer-aided software engineering, or CASE, which also helped to relieve the software crisis. CASE tools can be divided into 6 categories: business analysis and modeling, development tools such as debugging environments, verification and validation tools, configuration management, metrics and measurement, and project management. Now, the term software engineer is often used interchangeably with software developer, but there are subtle differences. Software engineers are also developers, but the term software developer is usually deemed narrower in scope than that of a software engineer. A software engineer's knowledge is usually broader. Software engineers take a systematic big-picture approach in their thinking to software development, whereas developers may have more creative approaches. And both software engineers and software developers have specialized knowledge, but software engineers use that knowledge to build entire systems, whereas software developers use their knowledge to write code to implement specific functionality within a system. Software engineers are often employed on larger scale projects, and they are focused on the broad structure rather than solving an immediate problem. Software engineers are tasked with designing, building, and maintaining software systems. Their responsibilities include writing and testing code and consulting with stakeholders such as clients, third-party software vendors, security specialists, and other team members. The adoption of a measured scientific approach to software development has influenced the way software is created and designed. Today, the development process is typically guided by the Software Development Lifecycle, or SDLC. The SDLC identifies the steps needed to develop high-quality software. Later in this module, we will discuss the SDLC, the traits of high-quality software, and roles common in the field of software engineering. In this video, you learned that software engineering is the systematic approach to design and development of software. Responsibilities of a software engineer include designing, building, and maintaining software systems, writing and testing code, and consulting with stakeholders, third-party vendors, security specialists, and other team members. And finally, software engineers build systems while software developers implement specific functionalities. Welcome to Insider's Viewpoints. What is software engineering? In this video, we will hear from experts discussing software engineering.
I think software engineering is the process of using programming languages and engineering principles to build products. These products could look like web apps, mobile apps, desktop apps, operating systems, or even networking systems. It is a skill that's integral to the success of our modern society because without technology, we couldn't get a lot of things done today. Within software engineering, it's a very broad term. And so within software engineering, you have roles such as front-end, back-end, security, mobile, test, full stack, DevOps, cloud, data, and machine learning. And these are all different types of engineers within software engineering.
I would define software engineering as building and improving software from anywhere from design and architecture to the user interface to fixing small bugs. So anything that falls in that range, that's what software engineers do.
So software engineering to me, I think really has to do with, I consider it a creative process, and it fundamentally is the practice of designing, envisioning, implementing, and then supporting and maintaining software through the full life cycle of it. So not just writing code, but in thinking about the software you're building before you've even written a line of code, the journey from idea inception to actual implementation and launching of said software, and then maintaining it, improving it, supporting it, and potentially evolving it to something else. So it's very much a sort of creative and full life cycle end-to-end engineering process.
I know in the United States, at least, software engineering, software development, programming, they all have, depending on who you ask, they mean very specific things or very hazy things or very contradictory things, or it's like, why do we even have 3 different titles for the same thing? I think of those titles as kind of all meaning the same thing.
What's the difference between a software engineer and a developer?
I think the difference for me, I consider engineering to be a little bit sort of broader, software engineering to be broader than development. I think development to me means is sort of one part of the process. So I think one fundamental difference for me is I think software engineering is beyond just writing code, which I think a developer often is handed a task to write a piece of code, or create a module, piece of software, whatever term you want to use. And I think engineering involves sort of starting a very long time before you even get to the development process, and continues on beyond the time you would actually take your code, deploy it. So this kind of goes into the full life cycle.
In my opinion, there isn't a difference really. So for example, I was trained as a full stack engineer or a full stack developer, but I was hired as a software engineer to work on the front end of the company's application. So I think it's a matter of semantics, and a lot of it I think is a lot of gatekeeping to keep people who don't know anything about the industry out. Somebody who has studied CS may argue differently from I do, but as a person with a non-traditional path into the world of software engineering, I only see it as like title changes and title differences, and I think it depends on what company you work in and what company you work for, because at the end of the day, we're all using the same tools and technology to get the product shipped to production.
I think that they are pretty similar roles. They are used interchangeably a lot, I think. But I think the main difference is that software engineers are also responsible for the system design and architecture, as well as data, how it's received, used, and how it's disseminated, whereas software developers, I think, focus more on the building of apps and features.
So in Canada, being a computer programmer or a software developer is incredibly different than being a computer engineer or a software engineer, where to be an engineer, it means you've taken specific classes in like codes of ethics, and you're held to the same ethical standards as a civil engineer or a mechanical engineer. And so depending on where you are, the titles can mean very different things. And I know for like purposes of immigration, the titles also can mean very specific things, and you have to be careful about like what it is that you put down. But in job descriptions, I kind of see them all used interchangeably, and I tend to just kind of think of them all as the same thing.
It's much of more of a longer time horizon, I think, in terms of engineering versus development. And I think there's a lot more considerations and hats you need to put on throughout the software engineering life cycle versus the kind of more narrowly scoped development cycle.
Welcome to the introduction to the software development lifecycle. After watching this video, you will be able to describe what the software development lifecycle is, explain its history, and discuss some key advantages of using it. The software development lifecycle, known as the SDLC, is a systematic process to develop high-quality software in a predictable timeframe and budget. The goal of the SDLC is to produce software that meets a client's business requirements. The SDLC defines phases of the software development process that encompass their own process and deliverables. It's a cycle of planning, design, and development that can be implemented as an iterative approach to software development. Adherence to the SDLC minimizes risks and costs to the development of high-quality, deployable software. The software development lifecycle began to take shape in the mid-1960s as software development began to necessitate a more detailed approach because of its growing complexity. The SDLC led to a more deliberate approach as large corporations needed to manage complex business systems requiring heavy computational resources. In its initial conception, it used what is called the waterfall method to manage projects where the development of software follows a linear pattern through discrete stages. The SDLC has since been adapted, however, to more iterative methods in response to addressing customer needs and shifting requirements. Waterfall and other approaches to software development will be discussed in another lesson. There are some key advantages for businesses in following the SDLC. The first advantage is that it gives development teams a process to follow rather than using an ad hoc approach to improve efficiency and reduce risks. Secondly, there are discrete phases to the SDLC. Each phase is well defined so that team members know what they should be working on and when. The phases of the SDLC will be discussed in another video. Because of the well-defined phases, it facilitates communication between the customer, other stakeholders, and the development team. The SDLC offers an overview of the process so stakeholders know where they fit into that process. Also, since each phase is discrete, cross-domain teams know when they have completed their tasks and when development can move to the next phase. The SDLC provides room for iteration, where, at the end of a cycle, the process can circle back to incorporate additional requirements as needed. Problem solving is incorporated early in the cycle, so problems are addressed in a timely fashion and can be addressed in the design phase rather than during coding. Finally, each team member has a well-defined role which reduces conflict and overlapping responsibilities. In this video, you learned that the SDLC provides a systematic process for software development. Its initial development in the 60s and 70s was driven by the need for a systematic approach because of the growing complexity of software. And key advantages of the SDLC include a roadmap to the software development process helping to reduce risk and improve efficiency, increased communication between the team and stakeholders, clearly defined and understood responsibilities for each team member, and the ability to be used iteratively, allowing for changing requirements. Welcome to the phases of the software development lifecycle. After watching this video, you will be able to name the phases involved in the SDLC, describe each phase, and identify several tasks associated with each phase. There are generally 6 phases in the SDLC process: planning, design, development, testing, deployment, and maintenance. Each phase is discrete, meaning that tasks from a previous phase do not overlap with tasks in the next phase. The original SDLC was conceived as a traditional waterfall method, where the phases are linear, but have since been adapted to introduce iteration so that shifting requirements can be accommodated. Waterfall and other approaches to software development will be discussed in another video. Note that some organizations may have different names for each stage. For example, planning may be called requirements or strategy or analysis. Also, some organizations may have additional or fewer stages. In the first stage of the SDLC, the planning phase, requirements are gathered, analyzed, documented, and prioritized. When planning a software solution, the following factors must be considered: users of the solution, the overall purpose of the solution, data inputs and outputs, legal and regulatory compliance, risk identification, quality assurance requirements, allocation of human and financial resources, and project scheduling. As part of the planning process, labor and material costs are estimated and weighed against time constraints. Also, project teams are identified and roles of each team member are proposed. If stakeholders are struggling to define requirements, often the development team may produce prototypes during the planning stage to tease out those requirements. A prototype is a small-scale replica of the end product used to get stakeholder feedback and establish requirements. A prototype is used to test basic design ideas. Though prototyping usually occurs during the planning stage, prototyping can occur at various phases of the SDLC whenever requirements need to be reconsidered or clarified as the project develops. After requirements have been gathered, they are combined into a document called a Software Requirements Specification, or SRS document. The SRS needs to be clearly understood and approved by all stakeholders. The developers are also involved at this stage so they can gain a clear understanding of these requirements. Requirements and the SRS will be discussed in more detail in a later video. In the design phase, the requirements gathered from the SRS are used to develop the software architecture. Several team members work together at this stage to design the architecture. The architecture is reviewed by the stakeholders and team, and during this phase, prototypes can be designed. A prototype is a preliminary mock-up of the system or parts of the system used for demonstration purposes. The document created in this phase is called a design document and is used by developers during the next phase, which is the development phase. The development phase, sometimes called the building phase or the implementation phase, is when the developers start the coding process once the design document is completed. The project planners use the design document to determine and assign coding tasks. This phase often requires the use of programming tools, different programming languages, and software stacks. Organizations may also have standards or guidelines that need to be followed. The testing phase is next in the process once the coding is complete, and some large projects have dedicated testing teams. Code needs to be thoroughly tested to ensure it is stable, secure, and meets the requirements outlined in the SRS. Testing can be manual, automated, or a hybrid of both. Product bugs are reported, tracked, and fixed, and the code is retested until the software is stable. Some common levels of testing include unit testing, integration testing, system testing, and acceptance testing. Each of these testing levels will be described in further detail in another video. Next, the deployment phase is where the application is released into the production environment and made available to users. This can also happen in stages. First, it is released onto a user acceptance testing, also called UAT, platform, and once the customer signs off on the functionality, it is released to production. This approach can be used for making software available on a website, mobile device app store, or a software distribution server on a corporate network. Finally, the maintenance phase happens once the code has been deployed into a production environment. This phase helps to find any other bugs, identify user interface issues, or UI for short, and identify other requirements that may not have been listed in the SRS. Code enhancements can also be identified at this stage. If bugs are discovered in this phase that were missed during testing, these errors may need to be fixed for high-priority issues or incorporated into the requirements as part of a future software release, and the process can start over again. In this video, you learned that the SDLC can be divided into 6 phases. Planning involves requirement gathering and development of the SRS. The architecture is developed during the design phase, and the design document is created. The development phase is when coding takes place, and then during the testing phase, issues with the code are found and fixed if possible. Deployment is when the code is released to the production environment, and finally, in the maintenance stage, feedback is collected from stakeholders, other UI issues may be identified, and code enhancements suggested. And this information can be fed into another software development cycle if necessary. Welcome to Building Quality Software. After watching this video, you will be able to list common software engineering processes and describe the common software engineering processes required for building high-quality software. There are numerous processes that are common to software engineering projects. In this video, we will discuss 6 of them: requirements gathering, design, coding for quality, testing, releases, and documenting. The Software Requirements Specification, or SRS, encompasses the process of collecting and documenting the set of requirements that the software needs to adhere to. It may include a set of use cases that describe the business needs and user flows that the software must implement. Software requirements can be classified into 4 broad categories: functional, external and user interface, or UI, system features, and non-functional. These categories are discussed in more detail in another video. Software design is the process of transforming the requirements into a structure that is implementable using code. The software design process translates the requirements into a language the developers can use to write the code. It transforms the requirements into a software solution. The technical lead breaks down requirements into sets of related components with clearly defined behaviors, boundaries, and interactions. These components define the system architecture. The system design incorporates guidance on system functions, performance, security, and platform characteristics. The design communicates business rules and application logic. Application programming interface design, which is how apps talk to each other or communicate with the database, user interfaces, and database design. Code quality refers to the characteristics of the code, including attributes such as maintainability, readability, testability, and security. Quality code must fulfill the intended requirements of the software without defects. Additionally, it should be clean and consistent, easy to read and maintain, well documented, and efficient. Coding for quality entails following a set of coding practices during development. These include following common coding standards, conventions, patterns, and styles, using automated tools known as linters to detect pragmatic and stylistic errors, and commenting in the code itself to make it easy for others to understand and modify. Software testing is the process of verifying that the software matches established requirements and is free of bugs. Its purpose is to identify errors, gaps, or missing requirements when compared with stated requirements. Properly tested software ensures reliability, security, performance, and efficiency. Software testing can often be automated or done manually. Levels of testing include unit, integration, system, and user acceptance. Unit testing is often done by the developer and tests the smallest component of code that can be isolated from the rest of the system. Once components are integrated into the larger product, integration testing occurs. Then, after the larger product is deemed completed, system testing can take place. User acceptance testing, or UAT for short, and sometimes called beta testing, is when the software is tested by the intended end user. Types of testing can broadly be divided into 3 categories: functional, non-functional, and regression. Testing levels and types will be further explained in an upcoming video. When the newest version of the software is distributed, it is referred to as a release. Different types of releases are intended for different audiences. There is generally an alpha, a beta, and a GA release. GA stands for General Availability. The alpha release is the first functioning version of the system released to a select group of stakeholders. The alpha release likely contains errors and may not contain the full feature set, but does contain most of the desired functionality. Design changes may still occur during this release stage. The beta release, also called a limited release, is given to the stakeholders outside of the developing organization. One of the intents of the beta release is to try out the software under real conditions, test the functionality, and identify any outstanding bugs or errors. The beta release should meet all the functional requirements. Then, after beta release, changes are agreed upon, made, and tested, and a stable version is released. The audience for the GA release is all users. Software documentation should be provided to both non-technical end users and technical users. System documentation is geared toward the technical user. Technical users may be other engineers, developers, or architects. System documentation explains how the software operates or how to use it. It consists of README files, inline comments, architecture and design documents, verification information, and maintenance guides. User documentation is provided to the non-technical end users to assist them in the use of the product. Generally, user documentation is provided in the form of user guides, instructional videos and manuals, online help, and inline help. More details about documentation will be discussed in another video. In this video, you learned that requirement gathering is collecting and documenting the set of requirements that the software needs to adhere to. Designing transforms requirements into a structure that developers can use. Coding for quality entails following a set of coding practices during development. Testing is the process of verifying that the software matches established requirements and is free of bugs. There are 3 types of releases, including alpha, beta, and general availability. And finally, documenting requires text or video that explains the software to technical and non-technical users. Welcome to Requirements. After watching this video, you will be able to describe the steps of the requirement gathering process, explain the purpose of a user requirement specification or URS document, explain the purpose of a software requirement specification or SRS document, and explain the purpose of a system requirement specification or SysRS document. Requirement gathering is a 6-step process of defining a problem to be solved and documenting how to go about solving that problem. These steps include identifying stakeholders, establishing goals and objectives, eliciting requirements from the stakeholders, documenting the requirements, analyzing and confirming the requirements, and prioritizing. Generally, the stakeholders work for the organization that requests the development of the software product. Key personnel from the organization may include decision makers, end users, system administrators, engineering, marketing, sales, and customer support personnel. It is good to have a representative from every group that the product affects. The goals of the product should be clearly defined. Goals are broad, long-term achievable outcomes. Goals can include customer outcomes and business goals. Next, objectives should be identified. Objectives are more specific than goals, and they are actionable and measurable actions that achieve the stated goals. The next 3 steps, eliciting, documenting, and requirement confirmation, are usually completed iteratively. Elicitation can be accomplished through surveys, questionnaires, and interviews. As the requirements emerge, they should be documented and checked to ensure they align with the goals and objectives. Documented requirements should be easily understood by stakeholders and the project team. In order to confirm the requirements, they should be analyzed to ensure consistency, clarity, and completeness. And after analysis, the requirements should be shared with and approved by the stakeholders. After confirmation, requirements should be prioritized. Labels such as must-have, highly desired, and nice-to-have are helpful. If possible, order the requirements within those categories. Typically, there may be 3 documents that result from the requirements gathering process: Software Requirement Specification or SRS, User Requirement Specification or URS, and System Requirement Specification or SysRS. The most common of these is the Software Requirement Specification. The Software Requirement Specification, or SRS, is a document that captures the functionalities that the software should perform and also establishes benchmarks or service levels for its performance. Parts of an SRS include a purpose statement that contains the intended use of the SRS, its audience and scope, constraints, assumptions, and dependencies, and requirements which can be sorted into 4 categories: functional requirements, external interface requirements, system features, and non-functional requirements. The product's purpose describes who will have access to the SRS and how they should use it. The scope describes the benefits of the software, its goals, and objectives. And the second part of the SRS should detail constraints, assumptions, and dependencies. Constraints describe how the product must operate under given conditions that may limit options in the design phase, such as conformation to standards or hardware limitations. Assumptions may include things like a required operating system or hardware that is needed by the software to function. Dependencies on other software products should also be noted. Requirements can be classified into 4 categories. Functional requirements are those that cover the functionalities of the software. External requirements are the requirements that address the behavior of the software in relation to external entities, such as users and interactions with other hardware or software. System features are a subset of functional requirements. These are required features for the system to function. There are also non-functional requirements, such as specifying performance, safety, security, and quality standards. User requirements describe the business need and expectations of the end users from the software system. The user requirements are written as user stories or use cases that answer 3 questions. Who is the user? What is the function that needs to be performed? And why does the user want this functionality? User acceptance testing determines if these requirements have been met. Often, though, the user requirements and software requirements are combined into a single SRS document. The SRS details the expectations of the software system. The System Requirement Specification Document, or SysRS, to differentiate it from the SRS, clearly outlines the requirements of an entire system. The System Requirement Specification is often used interchangeably with Software Requirement Specification, but the SysRS is actually broader in scope than the SRS. Many software projects develop an SRS rather than a SysRS. The SysRS contains system capabilities, interfaces, and user characteristics. It also may include policy requirements, regulation requirements, personnel requirements, performance requirements, security requirements, and system acceptance criteria. It also outlines expectations of the hardware needed for the system in addition to software requirements. In this video, you learned that the requirement gathering process entails identifying stakeholders, establishing goals and objectives, and eliciting, documenting, confirming, and then prioritizing requirements. The SRS documents functional, external, system, and non-functional requirements. The URS documents user stories. And finally, the SysRS documents system capabilities and acceptance criteria, and policy, regulation, personnel, performance, security, and hardware requirements. Welcome to Software Development Methodologies. After watching this video, you will be able to list several commonly used approaches to the software development lifecycle, explain waterfall, V-shape model, and agile methods, and compare the pros and cons of each of these 3 methods. There are many ways to approach software development. A specific methodology for developing software is commonly used in order to assist the development team to clarify communication among team members and determine how and when the information is shared. In this video, we will discuss 3 of these approaches: waterfall, V-shape model, and agile. In the beginning, when the SDLC was conceived, it implemented what is known as the waterfall method. Waterfall is a sequential method of software development where the output of one phase is the input for the next phase of the cycle. Development and work on the next phase start only after the completion of the previous phase. All planning, such as defining requirements and architectural design, is done up front. The customer usually does not see the product until it is in the testing phase. For a major version release of the product, the same process is repeated, resulting in long intervals, such as years, between releases. The V-shape model is named as such because the phases form the shape of a V. The phases going down the left side of the V are called verification. Then, going up the right side of the V, those phases are called validation. The V-shape model is like waterfall in that it is also sequential. Each phase in verification corresponds with a validation phase. There are 4 stages that occur on each side of the V. Going down the V are planning, system design, architecture design, and then module design. The bottom of the V is the coding phase. And going back up the V are the 4 phases that correspond to the phases going down the V: unit testing, integration testing, system testing, and acceptance testing. The tests are written during the verification phases on the left and executed during the validation stages on the right. Now, the Agile model is different. It focuses on a collaborative software development process over multiple short cycles rather than a strictly top-down linear process. Agile is what is called an iterative approach to development. It still aligns with the SDLC, but each phase is short. Teams work in cycles, or sprints, which are usually 1 to 4 weeks long. Unit testing happens in each sprint to minimize the risk of failure. Rather than the maintenance stage of the SDLC, the final stage of the sprint is a feedback stage. At the end of each sprint, a chunk of working code is released at a meeting called the Sprint Demo, where stakeholders can see the new functionality and provide feedback. After the sprint demo, the entire process is repeated for every sprint cycle. After several sprint cycles, a minimum viable product, or MVP, is developed so stakeholders can provide feedback on the basic feature set. The MVP contains a feature set to validate assumptions about the software. The 4 core values of Agile development outlined in what is known as the Agile Manifesto are individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. The main difference between traditional SDLC methods, such as waterfall and the V-shape model, compared to the Agile method of software development, is the former are sequential, whereas Agile is cyclical. Traditional SDLC methods, such as waterfall and V-shape, center around the whole product being developed before soliciting customer feedback, whereas Agile focuses on quick, short bursts of development. There are pros and cons to each method, though Agile is probably the most popular method used in modern software development. Regarding the pros of the waterfall method, it is easy to understand and follow. Each stage is discrete and well-defined, making it easy for all team members to understand their roles. Also, since planning is done up front, it is easier than iterative methods to estimate a budget and allocate resources. That said, waterfall lacks flexibility. Since all planning is done up front, if a requirement is changed or overlooked, that change can be hard to incorporate at a later date. Inevitably, unforeseen complications happen or agreed-upon functionality shifts from what was initially envisioned. Like waterfall, the V-shape model is simple and easy to use. It is even more rigid than waterfall, but designing test plans during the verification phase saves considerable time during coding and validation phases. Drawbacks are also similar to waterfall because it does not readily accommodate changing requirements. Once an application is in the testing phase, it is extremely difficult to go back and change functionality. Agile development is different, relying on ongoing research, planning, and testing during product development. When adding new features to a product, development still goes through the same phases as in traditional SDLC. But with Agile, new and changing requirements are handled quickly and easily because planning is initiated at the beginning of each sprint cycle. Most resources are spent on the building phase. At the end of each cycle, the QA team, stakeholders, and the customer have some piece of working code to test against requirements and are encouraged to provide feedback. As coding languages and technologies have developed in recent years, they now allow for modular design where developers can focus on smaller chunks of code that are readily integrated into the larger product. These small chunks can be released to provide the MVP. Cons of Agile are that upfront planning, such as budgeting and scheduling, can be challenging because the overall scope of the product is not clearly defined. In this video, you learned that 3 of the common approaches to software development include waterfall, V-shape model, and Agile. Waterfall and V-shape are sequential, whereas Agile is iterative. Both waterfall and V-shape models are easy to implement, but neither accommodates changing requirements well. And Agile allows for changing requirements, but resource allocation can be challenging. Welcome to Software Versions. After watching this video, you will be able to discuss software versions on computing platforms and identify software versions and numbering. Software versions tell us a lot about programs and applications. Users can determine what software version they are using, and developers can provide useful information with version numbers. Software version numbers vary in length and meaning. However, most version numbers follow a similar format and represent similar information. Version numbers indicate when the software was released, when it was updated, and if any minor changes or patches were made to the software. Software versioning is how software developers keep track of new software, updates, and patches for programs and applications. Version numbers can be displayed in several ways. Version numbers can be short or long depending on the software and the preference of the developer with 2, 3, or 4 number sets. Each number set is divided by a period. The first release of an application or program might have a 1.0 as the version number to indicate no updates, patches, or fixes to the software. Note, a version still in beta or testing could have a version number lower than 1, such as 0.9. A program or application with many releases and updates will have a longer number, sometimes 4 different number sets within the version number. Some software developers may use dates for their versioning. For example, Ubuntu Linux version 18.04.2 was released in 2018 April. The third number set, .2, designates an additional change or update. What do these numbers mean? Some version numbers follow the semantic numbering system and have 4 parts separated by a period, but not all numbering systems follow this 4-part example. In semantic numbering, the first number indicates major changes to the software, such as a new release. The second number indicates that minor changes were made to the software. The third number in the version number indicates patches or minor bug fixes. And finally, the fourth number indicates a build number or build date, and it can indicate less significant changes made. Software version numbers are identified in the About or Help section of software. You can practice identifying your version number in a web browser. This example illustrates how to view the version number in the Google Chrome desktop web browser. However, if you are using a different web browser, you should be able to follow the same or similar steps. To view the web browser version, first select the 3 dots or 3 lines in the top right corner of your browser. Next, select the menu item, Help, then select About to view the version information. The version of your web browser will display. Are newer versions of software compatible with older versions? Lack of compatibility between old and new versions of software is a common problem. You can troubleshoot compatibility issues by viewing the software version to determine if you are using an outdated version of the software. Sometimes updating software to a newer version will resolve compatibility issues. Some software is backwards compatible. If a program or application is backwards compatible, then the older versions of files, programs, and systems will work properly with newer versions. In this video, you learned that version numbers indicate the history of changes, updates, and patches to software. Some version numbers follow the semantic numbering system and have 4 parts separated by a period. Compatibility with old and new versions of software is a common problem. And you should view the version of the software you are using to determine software compatibility. Welcome to software testing. After watching this video, you will be able to define the terms functional testing, non-functional testing, and regression testing, and compare and contrast typical testing levels. Software testing is the practice of integrating quality checks throughout the software development cycle. The purpose of testing is to check whether the software matches expected requirements and ensure error-free software. In order to test software, the team writes test cases. These test cases are written to verify the functionality of a software application and ensure requirements have been satisfied. Test cases can be written in different stages of the SDLC and may vary depending on the type of test or the method used to develop the software, such as Agile or Waterfall. A test case contains steps, inputs, data, and the expected corresponding outputs. Regardless of the test type or development method, test cases should always be written after requirements are finalized. Software testing helps evaluate the software to identify whether or not the software product meets requirements and is error-free. Types of testing can be broadly classified into 3 categories: functional testing, non-functional testing, and regression testing. Functional testing usually involves black box testing, which is a method of testing without looking at source code or internal structure. Functional testing is only concerned with inputs and corresponding outputs of the system under test, also called the SUT. It is entirely based on testing functional requirements, and functional testing can be carried out manually or using automated tools. The goal is to test the functionality of the application, making sure the application is usable and accessible. Functional testing tests the SUT to make sure it meets functional requirements. Functional testing makes sure that when user errors or input edge cases do occur, the software handles those exceptions seamlessly by displaying appropriate error messages. Non-functional testing includes testing the application for attributes like performance, security, scalability, and availability. Non-functional testing checks to see if the SUT's non-functional behavior is performing properly. Non-functional testing should answer questions like the following: how does the application behave under stress? What happens when many users log in at the same time? Are the instructions in documents and user manuals consistent with the application's behavior? Does the application behave similarly under different operating systems? How does the application handle disaster recovery? And how secure is the application? Regression testing, also called maintenance testing, confirms that a recent change to the application, such as a bug fix, does not adversely affect already existing functionality. Regression testing should occur when there has been a change in requirements or when defects have been fixed. In order to conduct regression testing, all or some of the test cases should be selected to test against the application. Regression test case selection and prioritization can be challenging and can depend on several factors. Common reasons for regression test case selection include cases that have frequent defects, contain frequently used functionality, contain features with recent changes, or are complex test cases, edge cases, and randomly successful or failed test cases. Now that we have discussed different types of testing, let's discuss testing levels. There are 4 testing levels: unit, integration, system, and acceptance. Each level occurs at a different time in the SDLC. There are 4 different levels in order to reduce the amount of time spent on testing by preventing overlap. We will discuss each of these testing levels next. Unit testing refers to the tests that verify the functionality of a specific section of code, usually at the function level. It is performed by the software developer or engineer during the development phase of the software development lifecycle. Unit testing aims to eliminate construction errors before code is integrated with other modules. Unit testing is intended to increase the quality of the resulting software, as well as the efficiency of the overall development process. Integration testing seeks to identify errors when two or more smaller independent code modules are combined. Integration testing is another type of black box testing. Prior to integration testing, smaller independent code modules that passed unit testing are incorporated into the larger software application. After modules are integrated together, then integration testing can occur. Integration testing exposes bugs that occur when those smaller units of code interact with each other. Integration testing uncovers deficiencies in communication with a new module in conjunction with other existing modules, databases, or external hardware. Integration testing uncovers situations where bugs develop due to differing programming logic between modules, for instance. Also, sometimes during module development, requirements change, and the module isn't fully unit tested. Poor exception handling can cause problems when modules are integrated together. System testing occurs after integration testing and is conducted on a complete integrated system to evaluate the system's compliance with its specified requirements. It validates the system as a fully completed software product. System testing is both functional and non-functional. And system testing is done in a staging environment, which should be similar to the production environment. And finally, acceptance testing is formal testing with respect to user needs, requirements, and business processes. It determines whether a system satisfies the needs of the users, customers, and other stakeholders. Acceptance testing is usually done by the customer or the stakeholders during the maintenance stage of the SDLC. In this video, you learned that there are 3 categories of testing: functional, non-functional, and regression. Unit testing verifies small independent chunks of code. Integration testing looks for errors when 2 or more small chunks of code are combined. System testing validates the system as a fully completed software product. And acceptance testing verifies correct implementation of user requirements and business processes. Hello and welcome to Software Documentation. After watching this video, you will be able to list documentation formats, compare and contrast product documentation to process documentation, describe the categories and types of documentation, and explain the purpose of standard operating procedures. Software documentation is information about the software that describes what the product is and how to use it. These can be written, video, or graphical assets associated with a software product's development and use. Documentation can be in any of these 3 formats. Documentation is an essential aspect of software engineering applicable across all the phases of SDLC. Software documentation can be written for different types of audiences, such as end users, software developers, QA engineers, system administrators, and other stakeholders. Documentation can be divided into 2 categories: product and process. Product documentation relates to the product's functionality, whereas process documentation describes how to complete a task. Process documentation should provide the requirements for the quality implementation of a business process. Okay, now let's discuss some specific types of product documentation. There are many types of documentation, and we will discuss 5 categories, including requirements, design, technical, quality assurance, and user documentation. Requirements documentation is written during the planning phase of the SDLC and is intended for the development team, including the developers, architects, and QA personnel. Requirements documentation describes the expected features and functionality of the software system. It includes the software requirements specifications, system requirement specifications, and user acceptance specifications. Design documentation is written by the software architects and the development team to explain how the software will be built to meet the requirements. It consists of both conceptual and technical design documents. Technical documentation includes comments written in the code to help other developers read the code to understand its behavior. It also may include working papers that explain how the code works, and documents that record engineers' ideas and thoughts during project implementation. Quality assurance documentation includes all documents that pertain to a testing team's strategy, progress, and metrics. Types of test documentation include test plans, test data, test scenarios, test cases, test strategies, and traceability matrices. Traceability matrices map test cases to their requirements. User documentation is intended for end users and explains how to operate the software or help them to install or troubleshoot the system. End-user documentation includes frequently asked questions, installation and help guides, tutorials, and user manuals. Standard operating procedures, called SOPs, often accompany process documentation. Process documentation provides an overview of a process, but SOPs go through much greater detail. The SOP is written documentation that explains step-by-step how to accomplish a common yet complex task that is organization-specific. For example, checking in code using a code repository is common knowledge for a software engineer. However, an organization might have specific steps to follow for that organization in order to get code merged into the main branch. The SOP documentation explains those steps in detail. SOPs can be in the form of a flowchart, a hierarchical outline, or step-by-step instructions. Documentation in any form must be kept up to date. Take, for instance, online user manuals. If a cloud-based application user interface changes, then the accompanying online documentation must be updated accordingly. Businesses need to ensure they allot resources for this step. With regards to the software development in the SDLC, updating documentation happens during the maintenance phase. Ideally, documentation should also be reviewed periodically to ensure its accuracy. In this video, you learned that documentation comes in 3 formats: written, video, or graphical. Process documentation describes how to complete a task. Product documentation relates to how a product functions. The types of product documentation include requirements, design, technical, QA, and user. And SOPs are written instructions detailing an organization-specific procedure. Welcome to Roles in Software Engineering Projects. After watching this video, you will be able to list the common roles on a software engineering project, describe each role, and explain the responsibilities of each role. There are several common roles on a software development project, and these roles can have different names depending on the approach being used, such as Agile or Waterfall. Sometimes different companies have different names for similar jobs, but not all projects will have all these roles. The roles we will discuss in this video are Project Manager or Scrum Master, Stakeholder, System or Software Architect, UX Designer, Software Developer, Tester or QA Engineer, Site Reliability or Ops Engineer, Product Manager or Owner, and Technical Writer or Information Developer. Now let's describe each role and some of the responsibilities for each job. Traditional SDLC methods have project managers, but in Agile, the equivalent role is called a Scrum Master. A project manager makes sure the project runs smoothly and facilitates communication about the project. The project manager often deals with bigger picture issues such as planning, scheduling, and budgeting, allocating personnel and resources, executing the software plan, and team communication. In Agile, there is a Scrum Master. Rather than focusing on planning, the Scrum Master is focused on ensuring team and individual success. Remember that the 4 core Agile values prioritize people and communication over processes, and the Scrum Master is responsible for facilitating that communication. The stakeholders are the people for whom the product is being designed. They include individuals such as the customer, end users, decision makers, system administrators, and other key personnel. The stakeholder is mainly responsible for defining project requirements and providing feedback if the team members need clarification on requirements or if a proposed solution cannot be solved as planned. The stakeholders may also sometimes participate in beta testing and acceptance testing before the software is released. The system architect designs and describes the architecture of a project as well as communicates that architecture to team members. They are sometimes also called a software architect or a solution architect. They are responsible for designing the essential characteristics of the inner structure and technical aspects of the software. The architect provides technical support across the different stages of the SDLC. Note, software architecture will be discussed in further detail in another module. UX means user experience. The goal of a UX designer is to balance making the software intuitive, but also as robust as it needs to be to address requirements. They define how the software behaves from the user's perspective. The UX designer determines how the software communicates its functionality to the end user and how the end user interacts with it. Next, the developers write the code that powers the software. Responsibilities include implementing the architecture laid out in the design document, incorporating the requirements laid out in the software requirements specification, and employing the UX requirements determined by the UX designers. Testers, or QA engineers, are in charge of ensuring the quality of the product and that the software solution meets customer requirements. They are responsible for writing and executing test cases to identify bugs or deficiencies and provide this feedback to the development teams. A site reliability engineer, sometimes called an SRE or ops engineer, bridges development and operations by combining software engineering expertise with IT systems management. They track incidents and facilitate meetings to discuss them. They also automate systems, procedures, and processes, assist with troubleshooting, and ensure reliability for the customer. The product manager or product owner has the vision of what the product should look like. They have an intimate understanding of the client's requirements and the end user's needs. They are responsible for leading development efforts to create the software and for ensuring the product provides the value stakeholders are looking for. Finally, the technical writer or information developer writes documentation for the end user. They write documentation on technical material geared towards a non-technical audience. Not only does this documentation help the end user to use the software, but it also helps the customer so they can provide timely feedback to the development teams. Technical writers may be asked to write user manuals, reports, white papers, and press releases. In this video, you learned that there are a variety of job roles on a software development project, and each occupation has responsibilities unique to each role. Welcome to Insider's Viewpoints, job roles in software engineering teams. In this video, we will hear from experts discussing the various job roles you can expect to work with on your software engineering team.
Yeah, so on the engineering team I worked with, we had a product manager, we had a tech lead, we had a few QA analysts or test engineers, and we also had access to UX designers. And so the product manager ensured that we were on task and on track to deliver the features that we said we were going to build according to the business needs. That way we're not left behind.
Yeah, I think in my experience, the roles that software engineers would interact with the most, I think would, in no particular order, product managers. So the folks who are actually sort of working with the sales teams, the marketing teams, figuring out what actually needs to be built, what are customer needs, what are innovations and ideas that, looking forward that you might want to invest in and build out.
We asked our experts to describe these job roles in software engineering teams in further detail.
I think software engineering these days, as it becomes more and more, it's more and more large scale, more complex, more systems at play, more considerations. There's just a lot of things to consider in today's world as a software engineer. So you often work with a project or program manager who helps you set up your timelines, helps you ensure you're meeting your goals, helps you unblock yourself, helps you keep your stakeholders up to date with what is happening with your project. So there's just a lot of pieces involved, and I think project and program managers really are there to help tie it all together.
So the product manager would always act somewhat like a scrum master. So like we would have stand-ups and we would talk about the tickets that we had in Jira, and it was like, okay, so what are you working on? What do you need help with? And are there any issues? And during that process, the product manager does ensure that we were on task and on track, and if we had any issues, he would help us to resolve it.
You'll have a software engineer who's more focused on the architecture, and they can keep the big picture in their brain more easily. And then some software engineers who are more the nitty gritty, I'm sitting down and I am writing code, and my job is to like turn business logic into computer logic. And some companies have those all split out as different roles.
I think software engineers and these roles, the more they're embedded and work closely together and actually collaborate as part of a single team, versus handing off things in a more waterfall approach. I think that's generally the best way, or one of the most effective ways, is to actually work together as much as possible. Regular check-ins, actually having brainstorming sessions, group chats that involve all the various folks from all the roles. I think close collaboration there is super key.
And at some companies, all the different hats have their own titles. So you might be talking to a software engineer who's actually doing more kind of DevOps, infrastructure building, monitoring and alerting kinds of work. And then there's a software engineer who's also doing QA work, and they're the ones who are focusing on pipelines and continuous development, continuous integration type projects, working on getting test suites and automation all set up.
In terms of working with the UX designer or the UX engineer, they would give me like specific specs from Figma in order to meet the certain specifications of the business. And let's say we're building a checkout page, so the UX designer would design the spec out page in Figma and then deliver that spec to me, and then I would code it according to the design.
UX designers who actually come up with if you are working on and engineering a user interface, you'll work with UX designers to essentially from the moment of sketching out sort of a draft on paper or a whiteboard of an idea, all the way down to working with them on mocks and implementing the mocks and iterating on those. UX researchers often are worked with when you actually need to go out and do research in market and interview your partners or customers to get sort of as real time as possible and just real feedback from real users of your software.
So once I code something, I get it reviewed by my tech lead or my senior engineer. It would go to QA for them to test the application to ensure that whatever I did or implemented didn't break anything. If something is broken that I didn't catch, the QA tester would write up like a test plan or would do like a detailed testing document. That way I understood exactly what needed to be resolved, and I would resolve it and then go back to the QA person and say, hey, this is fixed, can you take a look at it again? And they would tell me whether or not it's fixed and whether or not something else was broken, which often happens with code.
So you generally work a lot with product managers because you need to know what to build. They generally give you a lot of guidance on on what they want to build, and you collaborate with them in terms of how to build it and discuss trade-offs and timelines and expectations. So it's a very much a collaborative process.
Typically, I have found that I interact most with product owners. So either at some places it's been a customer who works inside the company, and so I go to them quite frequently for questions on clarifying refinements, for getting test schedules up and running, for figuring out pain points and trying to optimize their workflows using technology to support them.
Software engineers work often with site reliability engineers, or sysadmins is maybe the role could be called, to actually maintain and help run the software and deploy it and actually get it running somewhere that's not on your desktop. You often work with more dedicated test engineers who are responsible for end-to-end testing, automated testing, integration testing at all points of the life cycle.
So as an engineer, you're never alone, you're never working alone. It's just a matter of knowing how to communicate directly with the people on your team.
Hello, welcome to Overview of Web and Cloud Development. When you're starting out as a web developer, it can be difficult to determine what you need to learn and what order you should learn it in. Understanding how familiar websites are constructed and delivered to you is a good starting point. Let's review the basics of how you interact with a website. You launch an internet browser. There are lots available. Google Chrome, Microsoft Edge, Mozilla Firefox, and Apple Safari are some of the most popular. The browser has an address bar into which you enter a URL, like www.ibm.com. The browser then contacts the server with the name and requests the information that makes up the website. The server then sends a response, which contains the data that the client requires to display the website. For most websites, the server will return HTML, which defines the structure of the page but doesn't look very attractive, CSS, which adds style and flair to the page, and JavaScript, which adds interactivity and dynamic content. Content displayed by websites can contain elements that are either previously stored on the server, called static, or generated each time they are requested by the client, called dynamic. Dynamic elements can involve information coming from other systems and applications, such as databases. Most websites contain static and dynamic elements to provide the best user experience. Cloud applications are similar to websites in that they request content that a server returns. Cloud apps are built to work seamlessly with a cloud-based back-end infrastructure, cloud-based data storage and data processing, and other cloud services, making them very scalable and very resilient. The environment for building websites and cloud applications is divided into two primary areas, front-end and back-end. The front end deals with everything that happens at the client side, everything the user can see and interact with. You can choose to specialize in front-end coding using HTML, CSS, JavaScript, and related frameworks, libraries, and tools. The back end deals with everything that happens on the server before the code and data are sent to the client. The back-end coding usually handles the logic and functionality that make the website or app work, and the authentication processes that keep data secure. Back-end developers may also work with relational or no SQL databases, even collaborating with database administrators in bigger projects. Full-stack developers have skills, knowledge, and experience in both front-end and back-end environments. Whichever way you choose to specialize, you will need the appropriate tools to help you work. The first tool most developers add to their resources is a code editor. Developers also need tools to integrate, build, compile, and debug code. Integrated Development Environments, or IDEs, incorporate some of these additional capabilities beyond just code editing and make it easier to build and manage your code. Good IDEs support multiple languages and integrate with management and storage tools like Git and GitHub. Other useful features are custom extensions and themes for supporting your working style and environment. Examples for code editors and IDEs include Sublime Text, Atom, Vim, VS Code, Visual Studio, Eclipse, and NetBeans. In this brief overview, you learned about the basic communication between client and servers, how websites are built and displayed. Front-end development is about what happens on the client side. Back-end development is about what happens on the server. Full-stack development includes both front-end and back-end development. IDEs will help you create and manage your code. Internet websites offer lots of different services, one of the most popular being online shopping. When you explore an online shopping website, navigating through pages, choosing different product categories, or comparing products, you are interacting with the front end of a website. Let us see how the front end of a website is developed by front-end developers. For this, we need to understand how a website is made. To create a website, web developers usually use hypertext markup language, HTML, cascading style sheets, CSS, and JavaScript. These languages are designed to work in conjunction with each other. HTML is used to create the physical structure of a website. The physical structure contains elements such as text, links, images and videos, page dividers, and buttons. The HTML code ensures a proper formatting of all text and image elements so that browsers display the page consistently. The back-end developer codes the structure of the website. A website is like a house which has only been constructed. Just like we need interior designers to add style to a space, we need front-end developers to add the necessary glamour and appeal to a website. When you order products from any website, you realize that the pages have a pleasing font, attractive colors, and are easy to navigate. Developers use CSS to create stylish websites. CSS provides front-end developers with a standard method to define, apply, and manage different sets of style characteristics for a website and each of its components. CSS ensures uniformity in look and feel, style, colors, fonts, designs, and layouts. So, HTML is used to create the structure, and CSS is used to design it and make it appealing. CSS is also used to create websites that have cross-browser compatibility, which means that they are compatible with multiple browsers and multiple devices, such as PC, mobile devices, iPads, etc. Online shopping websites are intuitive, interactive, and quick to load. This is where JavaScript comes into the picture. JavaScript is an object-oriented programming language that is used in conjunction with HTML and CSS to add interactivity to a website. For example, you use HTML to add a login button to a page and CSS to style that button. Then you use JavaScript to add login functionality to that button. A new front-end development language is Syntactically Awesome Style Sheets, SASS, called Sass. It is an extension of CSS that is compatible with all versions of CSS. Sass enables you to use things like variables, nested rules, and inline imports to keep things organized. Sass allows you to create style sheets faster and more easily. Another language that is being used now is Learner Style Sheets, LESS, or LESS. LESS enhances CSS, adding more styles and functions. It is backwards compatible with CSS. Less.js is a JavaScript tool that converts the LESS styles to CSS styles. Using all these languages, websites are designed as reactive and responsive. Reactive, Or adaptive websites display the version of the website designed for a specific screen size. For example, a website can provide more information if opened on a PC than when opened on a mobile device. Responsive design of a website means that it will automatically resize to the device it is being accessed from. For example, if you open up a product's website on your mobile device, it will adapt itself to the small size of the screen and still show you all the features. A JavaScript framework is an application framework that is written in JavaScript. Programmers can manipulate the different functions, use them wherever required, and can create device-responsive applications. A few examples of several frameworks being used are Angular Framework, an open-source framework being maintained by Google. Angular frameworks allow websites to render the HTML pages quickly and efficiently. It has built-in tools for routing and form validation. React.js has been developed and maintained by Facebook. It is a JavaScript library that builds and renders components for a web page. It is not a complete suite of tools. For example, routing is not a part of this framework and will need to be added using a third-party tool. React.js only helps build and drop components into a page. Vue.js is maintained by the community, and its main focus is the view layer, which includes user interface, buttons, and visual components. It is flexible, scalable, and integrates well with other frameworks. It is very adaptable. It can be a library or it can be the framework. The task of a front-end developer evolves continuously. The technologies are upgraded constantly, and so front-end developers need to keep upgrading the websites that they create. The websites that they create should work in multiple browsers, multiple operating systems, and multiple devices. Welcome to the importance of back-end development. A front-end developer creates websites and cloud applications using HTML, CSS, and JavaScript to create what the user sees and interacts with in the client software. A back-end developer creates and manages all the resources that are needed to respond to the requests that the user makes through the client. The back-end developer's tasks focus on enabling the server infrastructure, or back-end, to process requests, supply data, and provide other services securely. Front-end and back-end developers must work together very closely. Each needs to understand the requirements of the solution and how their respective parts will interact before the development process can begin. Throughout the lifecycle of the website or cloud app, front-end and back-end developers collaborate to resolve issues and add functionality. How does the work of a back-end developer affect you as you are browsing the internet or using a cloud app? Think about it like this. When you're shopping online, what happens to the data you enter? Your login information, your product searches, your payment info. The back-end processes all of these things, and the back-end developers write and maintain the parts of the application that process the inputs. Let's think about your experience as you explore an online shopping site and make a purchase. As you search for products, your search request is submitted to a web application, which then retrieves the data from a separate database and serves it back to the client for display. To facilitate this, a back-end developer must understand the language that the web application uses, how to query the database for the correct data, and how to bring the two together. Even a simple task like navigating around the site can require the skills of a back-end developer. Many sites have restricted areas that are only available to users who have an account and have logged in. User account management, authentication, and authorization can be the responsibility of the back-end developer too. Once you've decided what you want to purchase, you must add it to your cart and make a payment. The purchase process requires you to submit sensitive information, such as your address and credit card number, and the back-end developer must ensure that this data is securely handled and stored. Front-end client interactions, whether a request for data like an image, accepting input from a user filling out a form, or securing sensitive information like a credit card number, all require different services from the back-end server. Each request needs to interact with the back-end in a different way. Back-end developers use APIs, routes, and endpoints to process incoming requests. An API is code that works with data, usually using JSON or XML. APIs have set rules and structure. A route is a path to a website or page that the user interacts with. Routes generally take user input and show results based on the input. An endpoint may be an API or may simply be a path. When a request from the front end arrives at the back end, it is routed to the correct service. If the back end has an endpoint defined for the request by using routing, the request will be addressed and replied to. If the endpoint is missing, the server returns a 404 error. Back-end developers must create and maintain this server-side routing. Along with back-end APIs, routes effectively allow the front-end client to plug into the correct socket at the back end. APIs provide a mechanism for cloud apps, mobile apps, and other types of software to access resources from the back end. To perform all this back-end development, you will need to be familiar with at least one back-end language and its associated frameworks. Among the most popular languages today is JavaScript, which was originally designed to run in web browsers, adding extra interactivity and dynamic content to web pages. JavaScript is also being used on the back end, with new releases adding server-side functionality. JavaScript has many frameworks, but two of the most well-known are Node.js and Express. Python is another popular language. It's very flexible and easy to learn. Python has wide functionality. It can be used for everything from creating web pages to connecting to a database to performing data analysis. Two well-known Python frameworks are Django and Flask. Back-end developers often work with data and databases, so you will also benefit from learning some SQL. To help handle requests from databases, back-end developers can use Object Relational Mapping Tools, or ORM, to connect to the databases and retrieve the correct data. Although an ORM can hide some of the complexity of querying databases, it's useful to understand the fundamentals of databases so that you can troubleshoot any issues that arise. The day-to-day tasks of a back-end developer focus on the behind-the-scenes functionality that keeps websites, cloud apps, and mobile apps up and running. Back-end development covers a wide range of technologies, from managing user accounts, authentication, and authorization, to ensuring that sensitive data is stored and transferred securely. Back-end developers also work with databases, retrieving, processing, and storing data as required. Life for a back-end developer is varied, challenging, and ever-changing. Welcome to Teamwork and Squads. After watching this video, you will be able to define teamwork and describe the advantages of collaboration in software engineering, and describe squads. By definition, a team is a group of people working together towards a common aim. Within a team, you'll find a range of different people with different skills, experience, and talents. Each person can give their attention and effort to the things that they are good at, and by working alongside others on tasks outside their current repertoire, they can expand their skill set. Working in a team promotes creativity. Collaborating with others gives you the opportunity to discuss ideas and challenge one another's thinking about a subject. Good teamwork is empowering. Positive attitudes and behaviors can impact the rest of the team and create positive results. Working well as a team doesn't always come naturally, But there are some things you can consider to help your team succeed. Each member needs to trust and respect the other members of the team. This generally comes with time, but depends on all of the members contributing equitably. Defining and agreeing on goals for a project is essential so that the whole team knows what they are working towards. And you also need to define and agree on roles to avoid any duplication of effort or missed tasks. Working with each member's strengths is important to make the most of the talent within your team, as is celebrating success and analyzing problems. Communication is vital in a team environment. Ensure that you choose a method that works for everyone so you know that the whole team is seeing and responding to information. So, what does teamwork look like in software engineering? Teams often start projects with a kickoff meeting where they plan how they will complete the project, assign tasks, and agree on goals. Throughout the lifetime of a project, you're likely to have a whole team and/or sub-team meetings to review progress and plans. Design and code reviews can be requested at the team level and undertaken by whoever has availability at that point in time. Also, team members might present walkthroughs of their sections of responsibility to the rest of the team so that the whole team has oversight of all parts of the project. And key team members will likely present walkthroughs to stakeholders at various times during the project. When a project is complete, retrospective meetings may be held to review what went well and what could be improved in future projects. You may have a mentor who may or may not be in your current project team. You might also be asked to be a mentor. Sometimes team mentoring is used so everyone can learn from each other. And some groups also have teams working on internal projects, such as defining code standards, maintaining or updating legacy cross-project code, or reviewing potential new software for usefulness to the team. Good teamwork can bring many benefits to a project. Working alongside others can encourage creativity and enable you to take advantage of each person's strengths while also allowing them to gain knowledge and skills from other members of the team. When working as part of a team, software engineers are more likely to adhere to corporate coding standards and regularly document their code. The additional accountability that teamwork creates results in better quality code, fewer bugs, and more maintainable code. From a software engineer's point of view, working as a team can reduce stress because there's always someone to turn to and get help from. And having someone to discuss problems with can help you to increase your understanding and resolve more issues by yourself. By working in a team, each member has a greater idea of the bigger picture, resulting in a more coherent overall solution. Some organizations that follow agile development methodologies may call a team a squad. Typically, a squad is a small team of up to 10 developers. It is likely to consist of a squad leader, who acts as the anchor developer and coach for the squad, and a few software engineers who develop and implement the product features and test cases. It may also include 1 or 2 user experience developers or designers. In some squads, the developers may work together in pairs to practice pair programming. You'll learn more about pair programming in another video. In this video, you learned that software engineering teams meet regularly throughout the duration of a project. Good teamwork encourages creativity, shares knowledge, and results in better quality code. And squads are small teams used in agile development. Welcome to Insider's Viewpoints, Teamwork in Software Engineering. In this video, we will hear from experts discussing how teamwork is important in software development and how teams work together.
Yeah, so teamwork is very, very important in the world of software development. As a software engineer, you're not just going to be sitting at your desk coding all day. One of the most important aspects of working on a team or on an engineering team is communication and knowing how to collaborate and speak with your team members about the code you've written, especially if you're going to a UX designer and say, hey, here's what I can do, and your spec is a bit off. Can we massage your specs a bit just so we can meet the coding requirements?
Incredibly important. While I think it's possible for a single person to engineer and deploy and run software, I think doing it as a team is both more impactful and gives you more potential to do bigger and greater things. I think it's also just a more fulfilling process when you're building something with a group of individuals. I think without the support structure, it's hard to build something and support it and maintain it just by yourself.
So teamwork to me is essential because we're talking to each other all day, and we're not only talking to our tech leads or senior engineer, we're talking to product managers, we're talking to UX designers, we're talking to business analysts, we're talking to data analysts, and so on and so forth.
You have the support system, you have diversity of opinions and perspectives in terms of how you go about building it. It's more satisfying. You kind of can take larger risks because you're in it together and you're there to support each other. I think the celebration of a job well done is a lot more, it's a lot more fulfilling when you're doing that with someone else. But I think it just gives you both kind of a larger range of scope and a larger sort of risk portfolio, if you will, and you're able to, I think, just get a lot more done, have a lot more checks and balances, and really gives you, there's a less likely chance that you're going to miss something or you're going to make a mistake. There's a lot of support there.
And so every project I've worked on has had at least 3 other people that I have needed to communicate with, and to support, to be a reliable resource for them, to go to them for questions. Like I always have to be talking to somebody about something. So teamwork is crucial. Like you can't work in an isolated silo forever. At some point, you have to talk to someone else.
Building a product takes a lot of people. A lot of us come together to make a whole and to get the product shipped to production so our users can use it. And so teamwork is imperative.
Welcome to Pair Programming. After watching this video, you will be able to describe pair programming and compare different styles, and list the benefits and challenges of pair programming. Pair programming is an extension of teamwork where 2 developers work side by side at one computer. They can either be physically at the same computer or work virtually via video link or shared screens. The former is the preferred option, but virtual pair programming can also be productive. Pair programming is a type of agile development where 2 developers can plan and discuss their ideas continually as they create a solution, generally resulting in a better end product. And there are various styles of pair programming. Driver-navigator style is the most common style, where one developer is the driver typing in the code, and the other is the navigator reviewing the code as it's written and giving directions where to go next. The navigator also keeps an eye on the bigger picture of the overall solution. When working in this way, it's important to regularly swap roles to keep both of the pair engaged across the whole task. Ping-pong style incorporates test-driven development. For each task, one developer writes a failing test, and then the second developer writes code to pass that test. For each new task, they swap roles, so regularly changing who writes the test and who writes the implementation. The 2 developers work together at the end of each task, refactoring the successful code to refine and improve it. Strong style pair programming is a good way for junior software engineers to learn from more experienced ones. The defining rule for this is that for an idea to go from your head to the computer, it must go through someone else's hands. So the more experienced of the pair is the navigator, and the driver learns from witnessing their implementation and thought processes. For this to work well, the driver shouldn't challenge any ideas until the full implementation is complete, so as not to interrupt the flow of ideas from the navigator. Now, pair programming has many benefits. It's a good way to share knowledge and skills from one developer to another, or between the two, and a great way for a new team member to get up to speed on a project. As well as enhancing the technical skill of the pair, it's also a good way of building soft skills, such as communication and problem solving. Having two sets of eyes on the code often results in fewer typos, logic errors, and bugs. And it enables code reviews to be done on the fly. While this doesn't replace formal code reviews, it does enable another layer of review. Now, having two people thinking about a problem can result in multiple initial ideas, but is likely to result in the optimal approach being chosen earlier in the process. And although pair programming can take longer than individuals writing the same solutions, it's likely to result in better code with less time spent reviewing, testing, and bug fixing. There are also a few challenges to overcome. Working in a pair requires long periods of focus, which can be exhausting for the two programmers, and personal or other work commitments can impact the pair schedule. Sometimes one of the pair can end up controlling the entire process, resulting in a more typist programmer pairing, which doesn't benefit from any of the positives of pair programming. At other times, individual personalities may not work well together. When multiple sets of pair programmers are present, their discussions can result in a noisy environment for the other workers in the room. In this video, you learned that pair programming is an agile development technique where two developers work alongside each other. There are multiple styles of pair programming. And pair programming builds technical and soft skills, results in better quality code and solutions, and increases overall efficiency. Welcome to Insider's Viewpoints, Pair Programming. In this video, software engineers will discuss their experiences with pair programming and share their thoughts about the benefits and potential challenges associated with this way of working. First, we will begin by asking about their experiences with pair programming and about the benefits they associate with it.
At every job I've ever had, there have come times where you pair up with someone else. You get someone else sitting next to you at a computer, you're sitting next to them at their computer, you're looking at a problem together, you're thinking about it.
Yes, I have actually. Some of the benefits are definitely working with an engineer who might be more of a senior engineer because they have a lot of insight and they obviously have a lot of experience doing what you're probably trying to figure out how to do. And it's really great when it's someone who can both guide you, but also kind of take a step back and not take over at the same time.
I think pair programming can be very beneficial. I think when you're working with someone together, it's an opportunity to learn. I think pair programming can be very great in circumstances where someone is new to a team, new to a programming language, new to a set of tools, or a development environment that is new to them. Sitting next to someone who's an expert, I think, can both help you ramp up more quickly. It can help the team itself sort of understand where you are in terms of your own knowledge and journey, and help put you in a place to both succeed and utilize you and your skills as best as possible. It does help you get real-time feedback. You don't necessarily have to wait for code to be sent out to be reviewed, and you can kind of brainstorm together in real time on the actual implementation of it.
Ultimately, I try to keep in mind that the goal of pair programming is that everyone has inherent blind spots in the way that they think and the way that they approach a problem. And if you are talking to somebody else, they can point out what your blind spots are. And they're going to have different blind spots than you as well. So you can point out their blind spots.
What do you think are the drawbacks and challenges of pair programming?
I think that can be a con sometimes when you're working with another engineer and you're trying to pair program, is someone who kind of like takes over and then doesn't allow you to do your part or to learn, especially if they kind of like already know how to do something. So it's kind of like a double-edged sword. On the one hand, you want to get that practical experience of pair programming, and you want to get that experience from someone else. But at the same time, you want to make sure that you're learning.
I personally find pair programming to be a little frustrating because the ways I go about solving problems can be very different than the ways other people go about solving problems. And it's not that I have some special, unique, wonderful technique. It's just that everyone's brain works differently. And watching someone else go through their workflow of how to solve a problem, they're not clicking the exact same buttons that you are. And that can get very frustrating to me. And it's like, why are you using your mouse to click all of those things? There's keystrokes for it. Like, you could be doing this so much faster. And so I find it a challenge to do pair programming sometimes.
You actually need calendar time, so you need to be able to dedicate time to sit together and work together and have an aligned schedule. You could either be physical, you could do it virtually, but you need to make the time to do it. Pair programming can come with some overhead in terms of getting off the ground. So if you have a tight time crunch, competing priorities, maybe just not enough, there might be not enough time in the schedule to allow for it. That can be one of the cons. That it can, while you can get long-term, I think, efficiency benefits from writing the code together, because then support in the future will be easier because you have more people who know how the code was written and what the intent was. So there are definitely long-term benefits, but there could be some short-term costs to it. So there are trade-offs in that sense.
Welcome to Introducing Application Development Tools. Getting your cloud app from the ideas stage to fully formed, written, and deployed is a long process, but there are many tools which will help you along the way. A cloud application developer's workbench includes version control, libraries, and frameworks. When many developers are working on the same project, knowing what order changes were made, thereby creating a new version of the source code, becomes overridingly important. Version control systems keep track of what changes were made when and by whom, and resolve any conflicts between changes. For developing your code, version control can be useful even when you are the sole contributor on a project. Properly used, it can give you a way to revert to an older version of your code if something goes wrong, and gives you some basic information about how the code developed over time. Version control functionality is generally tied to the storage system you are using, which is why a code repository is recommended, even for beginners. Git and GitHub are extremely popular for source code storage and management. Git stores files in repositories where you can track changes, split code into different branches for more focused development, and then merge them back into the main body of code. Libraries are collections of code, like standard programs and subroutines that you can use within your code. For example, you might want to include a navigational feature, like a carousel. A code library can supply you with the code for that so that you don't have to spend the time and energy creating one from scratch. Being able to reuse code in this way makes developing your app much quicker and easier. Multiple code libraries can be integrated into your existing project. As you discover a need for a specific function or feature, you can research an appropriate library. You determine when to call the required method as needed. The control returns to the program flow once the subroutine is finished. When you use a code library, you are in control. Code libraries are generally used to solve a specific problem or add a specific feature set. Either way, there are lots for you to choose from, so do your research. Here are some examples of code libraries. jQuery is a JavaScript library that simplifies DOM manipulation. Email Validator is a small library that checks an email address is correctly constructed and valid. Apache Commons Proper is a repository of reusable Java components. Frameworks provide a standard way to build and deploy applications. You can think of a framework as being a skeleton that you can extend by adding your own code, providing a scaffold on which to build your apps. The framework you intend to use must be determined early in your development planning and used right from the beginning. New frameworks can't be incorporated into an existing project. Your chosen framework dictates the architecture of your program and controls the program flow. The framework determines which subroutines and methods will be called when. When working with a framework, there is a specific structure that you must follow. The framework calls on your code rather than you calling on the framework. Frameworks are less flexible than libraries, allowing you less control, but they do provide good standardization and can help you create efficient code. To use an analogy, if you are a carpenter building a house, the framework is the frame that you add to, bricks on the outside, plasterboard on the inside, and so on. The frame acts as a guide for how the house is constructed. Here are some examples of frameworks. AngularJS is a JavaScript-based framework for dynamic web applications. Vue.js is a JavaScript framework focused on the user interface. Django is a framework that uses Python for web development. Frameworks define the workflow that you must follow, unlike libraries, which allow you to call functions as and when required. When using a framework, it can sometimes feel like you, as a developer, are not in full control of the development process. This sense of the framework and its predefined workflow controlling the development process is referred to as inversion of control. Frameworks that have a lot of control are known as opinionated. They have opinions on how their workflow should be used and remove a lot of the decisions you would otherwise have to make about how code is written, the location of files, and even file names. Frameworks often include their own libraries, which they can call when needed. Inversion of control allows you to create standardized apps and takes away a lot of the tedious configuration work, so you can focus on the code for your app. In this video, you've learned about some of the tools that you will utilize in your career as a developer, including version control, libraries, and frameworks. Welcome to more application development tools. Let's look at some tools which can help you get your app built and deployed. CI/CD, build tools, packages, and package managers. CI/CD refers to the practices of continuous integration and either continuous delivery or continuous deployment. CI/CD is a best practice for DevOps teams, enabling developers to deliver frequent changes reliably. Implemented through a build automation server, continuous integration, or CI, ensures that all the code components work together smoothly. A CI build environment enables you to integrate newly developed code frequently, at least every day, if not every hour, depending on how quickly the project changes. Continuous delivery, or CD, begins where CI ends. The CI process automatically builds and tests your code, then CD deploys all code changes in a build to a testing or staging environment. A build tool transforms your source code into the binaries needed for installation. Build tools organize your source code, set compile flags, and manage dependencies. They are most important in environments where there are many interconnected projects with multiple developers contributing to each project. In these environments, it can be very difficult to keep track of what changes were made, in what order, what dependencies exist, and what needs to be incorporated in the next build. So automation is key to keeping everything running smoothly. Build automation can automate a wide variety of tasks that developers do in their day-to-day activities, like downloading dependencies, compiling source code into binary code, packaging that binary code, running tests, and deployment to production systems. You can initiate a build from the command line or from an IDE. There are two categories of build tools widely in use. Build automation utilities, which generate build artifacts like executables by compiling and linking source code. Build automation servers, which execute build automation utilities on a scheduled or triggered basis. Some examples of build tools are Webpack, a module bundler for JavaScript, Babel, a JavaScript compiler, and WebAssembly, a binary instruction format that runs in your browser. Now that you have your app developed and tested, you're ready to deploy. But how does that happen? The app needs to be simple and trouble-free for the user to install. So a commonly used technique is to collect all the necessary files and bundle them together into a package. Packages are archive files that contain the app files, instructions for installation, and any metadata that you choose. They have their own metadata too, including the package description, package version, and any dependencies, like other packages that need to be installed beforehand. Once you have bundled your app into a package, you can use a package manager to distribute it. Package managers take care of the tasks of finding, installing, maintaining, or uninstalling software packages at the user's request. Package management systems coordinate with file archivers to extract package archives, verify checksums and digital certificates to ensure the integrity and authenticity of the package, locate, download, install, or update existing software from a software repository, and manage dependencies to ensure a package is installed with all packages it requires. Some commonly used package managers for each of the major platforms are listed here. On Linux, Debian Package Management System, or DPKG, Red Hat Package Manager, or RPM. On Windows, Chocolatey. On Android, Package Manager. On Mac OS, Homebrew and MacPorts. Any libraries or utility code that is developed as part of the application is managed with the Cloud Application Package Managers. Here are some examples of package managers for popular languages. For Node.js or JavaScript, NPM. For Java, Gradle and Maven. For Ruby, RubyGems. For Python, pip and conda. In this video, you've learned about some of the tools that you will utilize in your career as a developer, including CI/CD, build tools, packages, and package managers. Welcome to Introduction to Software Stacks. After watching this video, you will be able to describe software stack terminology, identify some commonly used software stacks, and list the benefits and challenges of different software stacks. A software stack is a combination of technologies that include software and programming languages. Developers use a software stack to create applications and solutions such as web and mobile apps. The set of individual technologies is stacked in a hierarchy and work together to support the execution of an application. The higher levels in the stack provide tasks or services for the user, and the lower levels interact with the computer hardware. Software stacks typically include front-end technologies such as programming languages, frameworks, and user interface tools, and back-end technologies such as programming languages, frameworks, web servers, app servers, operating systems, messaging applications, and databases. You might hear the term technology stack used in place of software stack. However, a technology stack is a broader term that includes hardware and infrastructure, like virtual machines, containers, storage, and load balancers, as well as the software stack. The simplest implementation of a software stack consists of a presentation layer, a business logic layer, and a data layer. However, more complex applications use more complex stacks, which could include software for virtualization, scheduling and orchestration, runtime environments, database connectivity, networking, and security. The software and services that make up a stack can be from a variety of sources, from internal resources to third-party providers to cloud providers. There is no formal definition of the structure of a stack, the only rule being that the software and the services included must support an application's development, functionality, or deployment. When you're using a software stack, you don't have to use all of the available layers, you only need to use those which are relevant to your solution. There are many different examples of software stacks. The Python Django stack uses the popular Python programming language alongside the Django web framework. This combination is all open source and commonly used for large-scale, fast-changing web applications. The Ruby on Rails stack uses the Ruby programming language with a server-side web application framework. Ruby on Rails is great with JSON or XML for data transfer, and HTML, CSS, and JavaScript for front-end development. And the ASP.NET stack includes Microsoft technologies such as the ASP.NET MVC framework, the IIS web server, SQL Server, and Azure. You'll learn more about the LAMP, mean, MEVN, and MERN stacks next. The LAMP stack runs on the Linux operating system. It uses the Apache HTTP or web server, MySQL databases, and the PHP programming language. LAMP is an example of an early incarnation of a software stack designed for building websites and cloud applications. All its constituent parts are open source and loosely coupled, so it's easy to swap different options into the stack. For example, you could choose to use PostgreSQL instead of MySQL for your database server, changing the LAMP stack to be the LAPP stack. Similarly, you could use the Python programming language instead of PHP. The mean stack uses a MongoDB database with an Express.js web application server framework, the AngularJS framework for front-end JavaScript development, and the Node.js platform for server-side scripting. The mean software and services are platform agnostic, free, and open source. And there are other stacks related to the mean stack, including the MERN stack, which replaces AngularJS with React and is a flexible and high-performing framework for developing front ends, and the MEVN stack, which replaces AngularJS with Vue.js. Vue is a lighter-weight JavaScript framework with less capabilities, but it can provide better performance than AngularJS. Let's consider some advantages and disadvantages of three different software stacks: Mean, MEVN, and LAMP. Mean is a free and open-source JavaScript software stack used for building web applications. The biggest advantage of the mean stack is that all of the parts use JavaScript, so developers only need to know a single language. The stack is also open source, which means the cost is lucrative to businesses, and there is a lot of documentation and reusable code for developers to use. Development can happen quickly because Node.js has a huge collection of free, reusable module libraries. However, the mean stack may not be well suited for large-scale applications. When using Express.js, the business logic often resides on the server, preventing the reuse of some services, like batching operations. And MongoDB is great for unstructured data, but it doesn't provide the same level of functionality as a relational database. The MEVN stack is a web stack, like Mean, but it uses Vue.js instead of AngularJS for user interfaces. MEVN and Mean stacks have similar advantages, but Vue.js is a much newer technology and doesn't have as many reusable libraries as AngularJS. Like Mean and MEVN, the software and services in the LAMP stack are open source, meaning that there are lots of reusable chunks of code available to the developers. And because LAMP is one of the oldest software stacks, it's easy to find support and reusable solutions. However, because the Linux operating system is an integral part of the stack, it isn't as flexible as Mean and MEVN, which are platform agnostic. MySQL is a relational database, so the stack cannot take advantage of unstructured data. The other disadvantage of the LAMP stack is that the back end runs on PHP, Perl, or Python, whereas the front end uses JavaScript and HTML, making it harder for developers to switch back and forth between the Mean and MEVN stacks, which use JavaScript throughout. In this video, you learned that software stacks are a combination of technologies for creating applications and solutions. Software stacks can range from simple 3-layered systems to many layers. There are numerous types of software stacks for different developers and environments. The biggest advantage of the Mean stack is that all of the parts use JavaScript, so developers only need to know a single language. And the LAMP stack on Linux works well for relational data. Welcome to Insider's Viewpoints, Tools and Technologies. In this video, we will hear from experts discussing their favorite tools and technologies for software engineering projects.
Our team uses Git and GitHub every single day for all of our projects. We use it for tracking code, we use it for collaboration, and we use it for tracking bugs, features, and tasks for all of our projects.
I believe most open source projects are now using Git. Every project I've contributed to, whether open source or closed, has used it. Git's true value is most apparent when you're working on a team with multiple people, at which point you'll be glad to have things like feature branches and pull requests. But even if you're working on a project where you're the sole committer, I recommend using Git, and in particular GitHub, for the community aspect.
So if you are a front-end developer, if you understand JavaScript, then picking up backend using a framework like Node.js is not that much of a stretch. I actually started building static websites, and then slowly learned how to put in dynamic content using JavaScript, and then I had to use Java or PHP to build my backend systems on the server.
For front-end development, you're primarily using HTML, CSS, and JavaScript. If you're very front-end focused, you might want to try out an IDE built for that specific purpose, such as brackets. If you want to keep things more general, I recommend VS Code. In either case, I recommend installing IDE extensions for automatic formatting and linting of your code using Prettier and ESLint. These will help you catch issues as early as possible. For backend development, the tools are quite a bit more varied, so it's hard to give specific recommendations, but if you choose Node.js, you'll be able to use some of the same tools that I mentioned for front-end development. Otherwise, I recommend just looking into what IDE extensions are available and what linters and auto-formatters are available.
JavaScript is a very powerful language. It lets you do pretty much anything you can imagine, including shooting yourself in the foot if you're not careful. The practices I typically follow with JavaScript include proper scoping of variables and functions, and writing unit and integration tests for my features.
React.js was developed at Facebook, very popular. Angular is a framework operated by Google that allows for development of single-page applications, SPAs. jQuery is possibly the most popular and oldest library out there, created by John Resig in 2006. And jQuery is frequently used with both Angular and React. Backbone is a lightweight JavaScript library that is very popular. In terms of backend languages and frameworks, Node.js is an open source server-side platform built on the Google Chrome JavaScript engine. It uses an asynchronous single-threaded architecture that allows it to serve a very large number of concurrent connections. Flask is a framework used on Python that is popular with Pythonistas. And the Spring framework based on Java has been around for years and remains popular.
We use React JavaScript framework. It is better than Angular in terms of speed and efficiency. React is easier to learn than other JavaScript frameworks, which makes its adoption in the team easy. It also resolves the problems related to cross-browser issues. Another great feature of React is the use of JSX. JSX is helpful when working with UI inside the JavaScript code. It helps React to show more useful error and warning messages.
My favorite front-end JavaScript framework would be React.js. I love the whole component-driven design and architecture that you have to follow when you create a React.js based application. I also like the idea of props and states to hold the state of your application.
By using Express.js for backend development, we are able to scale applications quickly. We can code both frontend and backend with the help of JavaScript easily by using Express.js. Express.js is supported with the Google V8 engine, with the help of which you would be able to get higher performance without any lag or error in processing. It also supports the caching features, so you would not have to re-execute the codes again and again. Moreover, it will help web pages to load faster than ever.
When working with Node.js, I'll give you two of my favorite packages that I use on a daily basis. So first is making requests to web services. I use a library like Axios that helps me create these requests with the right headers and also provide me with callback functions or promises to be able to handle the responses that come back. My second package would be when I'm working with databases. I'll use NPM packages more likely than not to talk to an external database, regardless of if it's a relational database or a NoSQL database.
So when writing JavaScript, I really like to take advantage of the features in ES6 because it can make my code look cleaner, easier to read, and just more beautiful, such as the arrow functions or the ... operator. And so I encourage you to, after learning JavaScript, dive into ES6 a bit and have fun with it.
Welcome to Interpreted and Compiled Programming Languages. After watching this video, you will be able to identify interpreted programming languages and identify compiled programming languages. What are programming languages? Programming languages help us tell computers what to do. Computers don't use human language, they use their own language called machine code. Machines understand binary code, that is, ones and zeros, so to make communicating with computers easier, we have human-readable programming languages. Two common categories for programming languages are interpreted and compiled. These are broad categories, and there are many programming languages that are classified under compiled languages and interpreted languages. The purpose of the project helps a developer determine which programming language is best. Interpreted language is also commonly referred to as scripted or scripting language. Programs written in interpreted or scripted language, like Python and HTML, run through the programming interpreter on your computer's operating system or in your web browser. Remember that programming languages are in human-readable code, so the interpreter takes the human-readable scripted code and then translates it into machine code, enabling the computer to complete the requested task. As computers and web pages have changed and advanced, some interpreted programming languages are outdated, and they are not as useful or relevant. Some other languages are more versatile and easier to learn, which means they are preferred over other scripting languages and are used more often. All interpreted programming languages need an interpreter to translate the source code. Translators are built into your web browser, or they require a program on your computer to translate the code. Several different interpreted programming languages exist. Some examples of common interpreted programming language types are JavaScript, a simpler scripting language that runs through the web browser interpreter; Python, a language that is popular because it is easy to learn and use for developers; Lua, a general-purpose, lightweight game scripting language that is easy to learn and use; and HTML, a markup language used for formatting web pages. Another category of programming languages is the compiled programming languages. Compiled programs are applications and programs, like your music app or your operating system, that you run on your computer or device. The programs are packaged or compiled into one executable file. They are usually larger programs. Compiled programs are used to help solve more challenging problems like interpreting source code. Compiled programming languages are often referred to more simply as programming languages. A compiler program creates a program file, which runs the software. Simply put, it piles the code into one file that runs when you double-click on the app on your device. The program runs faster, and it can be done repeatedly. The source code is converted from the programming language to machine code. Then it is compiled into one executable file. Finally, the program runs when you select the icon or file on your device. Some examples of compiled programming languages are C and its variations, C++, and C#, which are used in many operating systems like Microsoft Windows, Apple's Mac OS, and the open source operating system, Linux. Java is another compiled programming language. It shouldn't be confused with the interpreted language JavaScript. The Android OS is written in Java because it works well across computing platforms. Let's look at this process. When you update to a new version of your operating system, like Microsoft Windows, your device might download an installation program. That program is made up of many files. The files are written in a compiled programming language. These files give instructions to your device in machine code. The compiled program is running on your device. A compiled program that you commonly use is your device's operating system, such as Linux, Microsoft Windows, Apple's Mac OS, or Android. Your operating system is written in a compiled programming language, like C, C++, C#, or Java. In this video, you learned that interpreted programming languages run scripts that are repetitive and need to be run often. Interpreted programming languages are more versatile and can be used across platforms as long as there is the correct interpreter. Some examples of interpreted programming languages are JavaScript, Python, and HTML. Compiled programming languages are for more complex programs that complete larger tasks. Compiled programming languages are used for creating executable files that can run directly from your device. And some examples of compiled programming languages are C and Java. Welcome to Comparing Compiled and Interpreted Programming Languages. After watching this video, you will be able to compare interpreted and compiled programming languages and discuss interpreted and compiled programming languages. How do developers choose a programming language? Developers choose which programming language is best to use depending on what they have the most experience with and what they trust, what is best for their users, and what is the most efficient to use. What are interpreted and compiled programming languages? Interpreted programming languages are used to create a scripted source code for smaller tasks. The source code goes through an interpreter. The interpreter is built into the operating system on a computer or on a web browser. Compiled programming languages are used to create files. The files are executable files. They are then grouped in programs that you can run on a computer or device. Interpreted programming languages are also called script code or scripting because they are used to automate tasks. Interpreter programs read and execute the source code line by line like someone would read a script. Each time the program runs, the source code needs to be executed to receive the desired output. And source code written in one of the interpreted programming languages runs on almost any operating system with the right interpreter. For example, imagine you have a client requesting information about web page views for last month. Which type of programming language would be the most appropriate and efficient to create a program for this task? You would use one of the interpreted programming languages to write code for a script. The script would retrieve the web page views data and then put it into a table for the client to read. Compiled programming languages are also called programming languages for short. They are used for more complex programs that complete larger tasks like running a spreadsheet program on your computer. A compiled programming language is used to write a larger program, usually installed on your device as an executable file. Writing code in a compiled language does take longer, but the payoff is that the program's code runs faster because compiled programs are installed on the device. And once the program is coded, the compiled program is grouped into one downloadable file. Remember that client who wanted information about web page views? Now they want a spreadsheet program to view and manage the data. A programmer could use the C programming language to create a compiled program like Microsoft Excel. So, what are the major differences between interpreted programming languages and compiled programming languages? First, there's interpreted programming. These programs are available across multiple platforms or in the cloud. The scripting languages are easier to learn and use, and they're better for websites because they tackle smaller, repeated processes. Then there's compiled programming. These programs are available to users with the same operating system coded in the same language. However, compiled programming languages are more difficult to learn and use because they are larger programs with more parts. And they're better for larger tasks like running the operating system on your computer. To better understand more of the similarities and differences of programming languages, let's take a look at some examples. A few of the most common programming languages are C, C++, and C#. C is a compiled programming language. C is the original language, and C++ and C# are variations. C and its variations are case-sensitive languages. The C programming language is the basis for Windows and other common operating systems. And it takes more time to learn and use for coding, but requires less memory and the code runs faster. Another common programming language is Java. It is a compiled programming language. It is also a case-sensitive, object-oriented programming language. The Java Virtual Machine, or JVM, is required to run the code written in Java. It is the primary programming language for some operating systems, like the Android OS. And a benefit of Java is that it is a cross-platform language, which means it runs the same code on Mac OS, Windows, and Linux. Python is an example of an interpreted programming language. It is also referred to as a scripting language. Python is a popular general-use case-sensitive programming language. It is used with Windows, Mac OS, and Linux operating systems, and with server-side web app code. And it requires the Python engine to interpret code. JavaScript is another interpreted programming language. It is a scripting language that runs on the client side in web browsers. JavaScript is case-sensitive. Simple scripts are run with HTML. Complex scripts are run in separate files. And while it sounds similar, it shouldn't be confused with Java, the compiled programming language. Another example of a common programming language is HTML. It is an interpreted programming language. HTML stands for Hypertext Markup Language. HTML is mostly case-insensitive with some exceptions. And it uses tags to format web pages on client-side web browsers. In this video, you learned that Interpreted programming languages create source code that runs through an interpreter in your device's operating system or on your web browser. Compiled programming languages create executable files that are grouped in programs on your device. Compiled programming languages, like C and Java, are used to write larger programs like operating systems and other executable files. And interpreted programming languages, like Python and HTML, are used to write code that can complete repetitive tasks within a web browser or a computer. Welcome to Query and Assembly Programming Languages. After watching this video, you will be able to compare high-level and low-level programming languages, describe query languages, and describe assembly languages. Let's explore query and assembly programming languages. But first, we need to categorize programming languages into two levels, high-level and low-level. A high-level programming language is more sophisticated and uses the common English language to make its code more understandable and to increase the speed of coding and debugging programs. Examples of high-level programming languages include query languages, such as Structured Query Language or SQL, structured programming languages, such as Pascal, and object-oriented programming languages, such as Python. In contrast, a low-level programming language uses a set of symbols to represent machine code. Examples of low-level programming languages include assembly languages such as ARM, MIPS, and x86. A query is a request for information from a database. The database handles the query and searches its tables for the information requested and returns the results to the querying entity. When querying a database, it is important that both the user application making the query and the database handling the query are speaking the same language. In programming terms, writing a query means using predefined and understandable instructions to make the request to a database. This is achieved using programmatic code, and this is what we refer to as a query language. A query language may also be referred to as a database query language. By far the most prevalent query language for database queries and database management is SQL. However, there are other query languages available, such as AQL, CQL, Datalog, and DMX. In addition to SQL databases, there is another type of database called NoSQL, which stands for Not Only SQL. The key difference between these two types of databases is their data structures. While SQL databases are relational and use structured, predefined schemas, NoSQL databases are non-relational in nature and have dynamic schemas for unstructured data. A query language is predominantly used to request data from a database or to create, read, update, and delete data in a database. You will likely see the term CRUD used to refer to these last four key database operations. Typically, a user enters a command to either make a query or perform a CRUD operation using syntax that is understandable to the database management system hosting the database. And a database typically consists of structured tables made up of multiple rows and columns of data. When a user performs a query, the database retrieves the data from the relevant rows and columns in the table and arranges it into some sort of order ready to be returned and presented in the query results. Database queries are either a select command or an action command such as create, insert, update, or a mixture of both. The term statement is more commonly used to describe these commands. Select queries request data from a database, whereas action queries manipulate data in a database. Query statements can also be used to perform other administrative functions, such as creating users and modifying permissions. This table lists some of the most common SQL query statements. And here are some simple syntax examples of common SQL statements. As mentioned earlier, assembly languages are less sophisticated than query languages, structured programming languages, and object-oriented programming languages. As an assembly language uses a simple set of symbols to represent the zeros and ones of machine code, it is categorized as a low-level programming language. Assembly languages are closely tied to the processor architecture from hardware manufacturers, and therefore each CPU type will typically have its own assembly language. For this reason, there are a large number of assembly languages in use today, which vary among hardware manufacturers. Assembly languages use a simple, readable format for their statements, and they are entered one line at a time with one statement per line. Assembly language statements use the standard format shown here. In this syntax, all fields in curly brackets are optional, and the statement has two main parts. The first part is the instruction, or the mnemonic, and the second part includes the parameters, or the operands. There may also be optional useful comments added on the end of the statement. One other key difference with assembly languages is that they are translated using an assembler instead of a compiler or interpreter, and one statement translates into just one machine code instruction, as opposed to high-level languages where one statement can be translated into multiple machine code instructions. Assemblers translate assembly language into machine code using mnemonics, such as input INP, output OUT, load LDA, store STA, and add ADD. The statements consist of opcodes that tell the processor what to do with the data, and operands that tell the processor where to find the data. In this video, you learned that query languages, structured programming languages, and object-oriented programming languages are categorized as high-level programming languages. Assembly languages are categorized as low-level programming languages. A query language is predominantly used to request data from a database or to manipulate data in a database. The most prevalent query language for database queries and database management is structured query language, or SQL. Select queries request data from a database, whereas action queries manipulate data in a database. You also learned that assembly languages use a simple set of symbols to represent the zeros and ones of machine code. Assembly languages are closely tied to the processor architecture from hardware manufacturers. Assembly languages are translated using an assembler instead of a compiler or interpreter. And assembly language instructions have a one-to-one association with their machine code counterpart. Welcome to Understanding Code Organization Methods. After watching this video, you will be able to explain why code organization methods are important when programming, define the different code organization methods, and identify the benefits of using code organization methods. Organizing is very important when it comes to reading, maintaining, and configuring code. Well-planned out software design, usually using one of several methods, helps programmers write cleaner and more reliable code. Planning out code in a visual format helps improve the code base once it is written and reduces the chance of bugs and errors throughout the lifespan of a project. Organizing code before programming has a positive impact on the quality of the program and helps provide a consistent and logical format to use while coding. There are two main methods of organizing code, flowcharts and pseudocode. The main difference between pseudocode and a flowchart is that the former is a basic high-level description of an algorithm. An algorithm is a step-by-step sequence of solving a given problem. A flowchart is a pictorial representation of an algorithm, showing the steps as boxes of various shapes and colors connected by arrows that indicate their order. Flowcharts are used in designing or documenting a process or program. Pseudocode provides a beneficial bridge to the project code because it closely follows the logic that the code will. Pseudocode also helps programmers share ideas without spending too much time creating code, and it provides a structure that is not dependent on any one programming language. Flowcharts are especially beneficial for smaller concepts and problems, while pseudocode is more efficient for larger programming projects. And flowcharts provide an easy method of communication about the logic, and offer a good starting point for the project because they are easier to create than pseudocode in the beginning stages. A flowchart is the graphical or pictorial representation of an algorithm using different symbols, shapes, and arrows in different sizes and colors to demonstrate a process or a program. The main purpose of using a flowchart is to analyze different methods of solving a problem or completing a process. Several standard symbols are applied in a flowchart, and you can easily highlight certain elements and the relationships between each part in the process. Some traditional flowchart shapes used for programming concepts are start-end, a capsule, process, a rectangle, decision, a diamond, data, a parallelogram, and connectors as arrows. A simple flowchart to represent how to add two numbers is easy to create. The procedure starts with the capsule and has a connector or arrow progressing to the next step, the data input, the parallelogram, in this case, input N1 and input N2. Then another connector or arrow goes to the process, the rectangle of adding the two inputs, sum equals N1 plus N2. Another connector or arrow moves to the data, the parallelogram, showing the result, in this case, print sum. And the last connector or arrow moves to the end of the process, the end capsule. Flowchart software is an application that provides various functionalities to create flowcharts by providing the ability to drag shapes into the desired order using an easy-to-use editor. Flowchart software also provides team collaboration for creating flowcharts. Some of the well-known flowchart software programs include Microsoft Visio, Lucidchart, Draw.io, and Draw Anywhere. Pseudocode is an informal type of programming description that does not require any strict programming language syntax or underlying technology considerations. System designers write pseudocode to ensure that programmers understand a software project's requirements and align code accordingly. Pseudocode is used for creating an outline or a rough draft of a program that summarizes a program's flow but excludes underlying details. Pseudocode acts as the bridge between the programmer's brain and the computer's code executor that provides the ability to plan instructions that follow a logical pattern without including all the technical details. Pseudocode is a great way of getting started with software programming as a beginner without worrying about coding syntax. Pseudocode helps both programmers and non-programmers agree about the program's goal and the basics of how the task should be done. Here's one example of pseudocode written to check if the user entered an odd or even number. The next example displays the pseudocode written in C++. There are many advantages of using pseudocode over flowcharts. The main benefit of pseudocode is that it's simple and explains exactly what each line of an application should do. The coder can focus more on logic than on program language syntax. Removing the distractions of coding when using pseudocode makes the code development stage easier. Words and phrases in pseudocode represent lines of basic computer operations that simplify translation from the pseudocode algorithm to the specific programming language. Pseudocode allows programmers working in different computer languages to interact with each other. Pseudocode can be reviewed by different development groups, easier than real code. Pseudocode is easier for non-programmers to read and enables quick and easy translation to any computer language. Writing pseudocode is more concise and easier to modify, so changes to the design can be easily incorporated. And lastly, unlike some flowcharts, pseudocode is usually less than 1 page. In this video, you learned that organizing and planning out software design enables programmers to write cleaner and more reliable code. And organized code is very important from a readability, maintainability, and scalability standpoint. Two main methods of organizing and planning software code are by developing flowcharts or writing pseudocode. A flowchart is a pictorial representation of an algorithm, showing the steps as boxes of various kinds, connected by arrows that indicate their order. And the main goal of pseudocode is to explain exactly what each line of a program should do, making the code construction phase easier for the programmer. Welcome to Insider's Viewpoints, Types of Languages. In this video, we will hear from experts discussing if they prefer developing in compiled or interpreted programming languages.
Most of the time, it doesn't really matter. It just comes down to personal preference, like what are you going to get moving on the fastest? There are certain situations where it will make a difference if you're compiling ahead of time versus interpreting on the fly. If you're trying to eke out like very small incremental performance benefit.
I prefer compiled code or a language that's compiled language, just because I have more of a guarantee that it will, well, maybe not necessarily work, but will do what I thought it will do, and at least will deploy properly when being rolled out.
But usually, no, it doesn't make that much of a difference to either the development process or the deployment and use process. They definitely have advantages and disadvantages to each of them, but most of the time it doesn't make that much of a difference to what I'm doing. I
think interpreted languages can, there's a lot of flexibility there, and often you can do more creative things, and the compiler, it sort of stops, the buck stops with the compiler, and you can't really avoid compiler errors with the compiled language. With interpretive, there's more interesting runtime possibilities there. So I think it really depends on what environment you're developing for, or what your risk factor is when it comes to being okay with potentially buggy code being out in the wild.
What do you think are the benefits of object-oriented programming over procedural programming?
Anything can be an object, and object-oriented design puts hierarchies and patterns onto those things, and that structure can make it easy to keep designs in mind and keep in mind how the different objects interact with each other. It's also very easy in object-oriented programming to paint yourself into a wall where you have put too much structure around everything, and you now have this explosion of useless boilerplate code. So there's a bit of a, not catch-22, but just a balance that you need to find in between how much structure should your thing have, how much flexibility should it have, and how much should your intentions be imposed on that design and the way that people interact.
I think procedural programming can be, feels more mathematical and more sort of pure engineering in some sense, and I think that that also can lend itself well to someone who is really looking to not just build software, but really wants to sort of feel like they're engineering the code in some sense. It can feel like you're kind of in the machine, if you will. So I know maybe that's a weird answer, but I think it depending on how your brain works too, one can lend itself more easily than the other. So, but I think it's worth trying them both out.
If you get super object oriented, you can get a little too prescriptive with the designs, I think. So that's just whenever you're using objects, it's just a thing to keep in mind, that you can go too far with it. But where that line of too far is kind of depends on exactly what it is that you're building. Sometimes the sky's the limit, just regulate everything. And sometimes the amount of flexibility that you require actually does mean that you can't really have an object of any sort. Both of those situations should be pretty aware. Those would be on the extremes. but most of the time, a few simple objects will do a lot of good, no matter what the rest of your system looks like.
Yeah, I think object-oriented programming to me is for me personally, I think it does lend itself well to like real-world mappings and data models, and the sort of classic examples of you might in your first object-oriented software like demo build something like a library that has books and it has a checkout. So like there's physical objects, and the way you learn it is very much sort of, you think about the software as something real world. So that helps you make the jump from building something physical with your hands to building something with bits and bytes.
Welcome to Branching and Looping Programming Logic. After watching this video, you will be able to describe the two types of programming logic, define Boolean expressions and variables, and list the differences between branching and looping. There are two major types of programming logic, branching and looping. Both types use Boolean expressions and variables. A Boolean expression is a type of programming statement with only two values, either true or false. And variables have assigned values that are passed into a function or subroutine within a more extensive program. Computers use Boolean logic to make decisions. The computer takes one action if a Boolean expression is true and a different action if the expression is false. Typically, a program consists of instructions that tell the computer what to do and data that the program uses when it is running. A variable has a value that can change depending on conditions or information passed to the program. Boolean logic, along with variables, form the basis of programming. Branching logic is where a computer makes a decision following a different set of instructions depending on whether certain conditions are met during the program's execution. Each possible code pathway creates another branch. The branch of code that runs depends on the values assigned to the parameters of the branching procedure, and there is no limit to the number of branches to implement complex logic. The values of these parameters may be input by the user or generated by the output from a previous procedure. Branching contains constructs that occur and are processed to determine the path a program takes when running. Branching statements, also known as constructs, allow the execution flow to jump to a different part of the program. The common branching statements used within other control structures include if then else, switch, and goto. The if statement is a decision-making construct that guides a program to make decisions based on specified criteria. The if statement executes one code set when a specific condition is met, true, or another code set if the condition is not met, false. The if-then-else is a conditional construct that executes its substatement, which follows the then keyword. This only occurs if the provided condition is true. The if-else statement extends the if statement by specifying an action if the if, or true-false expression, is false. With the if-else statement, the program will execute either the true code block or the false code block, so something is always performed with an if-else statement. In computer programming languages, a switch statement is a type of selection control mechanism used to allow the value of a variable or expression to change the control flow of program execution via search and map. Goto is a statement found in many computer programming languages that performs a one-way transfer of control to another line of code. In contrast, a function call typically returns control. Now, let's look at the logic of looping programming. A loop is a sequence of instructions that continually repeats until reaching a specific condition. Typically, a particular process is performed, such as retrieving and changing data, and then some conditions are checked, such as whether a counter has reached a prescribed number. If it has not, the next instruction in the sequence is to return to the first instruction in the series and repeat the sequence. If the condition is reached, the next instruction falls through to the next sequential instruction or branches outside the loop. A loop is a fundamental programming idea commonly used in writing programs. There are 3 basic loop statements: while, for, and do while. In a while loop, a condition is evaluated before processing the body of the loop. If a condition is true, then and only then the body of the loop is executed. In a for loop, the initial value is performed only once. Then the condition tests and compares the counter to a fixed value after each iteration, stopping the for loop when false is returned. And in a do-while loop, the condition is always executed after the body of a loop. It is also called an exit-controlled loop. In this video, you learned that there are 2 major types of programming logic: branching and looping. Both types of logic use Boolean expressions and variables. Boolean expressions have only 2 possible values, either true or false, and variables have assigned values that are passed onto a function or subroutine within a more extensive program. Variables have values that can change depending on conditions or information passed to the program. And branching is deciding what actions to take, while looping is deciding how many times to perform a certain action. Welcome to Introduction to Programming Concepts Part 1. After watching this video, you will be able to describe the purpose and use of identifiers in programming, and describe the purpose and use of containers in programming. To fully understand software programming, there are some fundamental programming concepts you need to know first. The first concepts you will look at are identifiers. Software developers use an identifier to reference a program component, such as a stored value, a method, an interface, or a class, by assigning a custom named label to it. If the identifier stores data, then the data values in the program can be one of 2 types, either a constant or a variable. A constant is a data item whose value does not change within a program. This could be a numerical constant, such as the mathematical value of pi, or it could be a text string that remains constant, such as a player's name within a game. Constants are also referred to as named constants. You assign a value to a constant when you define it. For example, you might want it to refer to a numerical value within your program, such as pi, or a cost price, or a rate of tax, and then, rather than repeatedly retyping the same numerical value, you can just declare a constant for the value instead and name it something meaningful like pi_value, or cost_price, or tax_rate. There are a couple of major benefits to using constants in your programs. One is for ease of readability in your code, and the other is that if the specified value changes in the future, you only need to change it once on the constant, rather than finding every instance of that numerical value within your code and changing it. The other type of identifier used in programming is a variable. As the name suggests, this kind of identifier is not constant. Its value can change during the program's execution, such as a user entering their age in an application or a high score in a game. Variables can be strings of text, numerical values, or any other type of data. Using a variable as an identifier is a useful way to refer to program items that are unknown to you, such as a username, a service, or a file name, for instance. If you don't use a variable, then you will need to hard code all the names and values in your program, which is not considered best practice. Variables can be declared and assigned a data type and initial value as they are defined, or you can decide not to assign an initial value when you define a variable and instead have the value assigned later by instructions within the program. In addition to the identifier data structures already discussed, there are also special kinds of identifiers that can reference multiple elements in a program, and these are referred to as containers. Being able to specify multiple elements means that you don't have to create a variable for every individual element. This makes it faster and more efficient. For example, if you only want to store 6 numerical integers, then you could argue that you could just create 6 variables, one for each. But what if you need to store 1,000 integers or more? In such a case, defining 1,000 variables would obviously be an unwieldy and inefficient programming technique. So in this case, you would use a container. There are 2 types of containers to specify multiple elements: arrays and vectors. The simplest of these container types is an array. In an array, a fixed number of elements of the same type are stored in sequential order starting from index 0. When you declare an array, you specify the data type of the values it contains, such as an integer, or Boolean, or a string, and then the maximum number of elements it can contain. The syntax for declaring an array is to specify the data type first, then the name of the array, then the maximum size of the array in square braces. In contrast to arrays that have a fixed size, vectors have a dynamic size, and they will automatically resize themselves as you add elements to them or remove elements from them. For this reason, you may also see them referred to as dynamic arrays. Because they are dynamic in nature, vectors take up more memory space than arrays, and their elements also take a little longer to access than elements in an array, as they are not stored in sequential memory locations. The syntax for declaring a vector is to specify the container type of the vector first, then specify the data type in angle brackets, then the name of the array. Note that because it is a vector, you do not need to specify a maximum number of values it can contain because the size is not fixed, it is dynamic. In this video, you learned that software developers use an identifier to reference a program component. If an identifier stores data, then it can either be a constant or a variable. A constant is a data item whose value does not change within the program. A variable is not constant, it can change during the program's execution. In an array, a fixed number of elements of the same type are stored in sequential order, starting from 0. And vectors have a dynamic size, and they automatically resize themselves as elements are added or removed. Welcome to Introduction to Programming Concepts, Part 2. After watching this video, you will be able to describe the purpose and use of functions in programming, and describe the purpose and use of objects in programming. Next, let's look at the fundamental concept of functions. Functions are a consequence of the modular programming software development methodology that encourages the separation of a program into multiple modular components, where each performs a specific task within a program. So, a function is essentially a piece of structured, standalone, and reusable code that will perform a single specific action. This enables software developers to take a substantial, complex program and divide it into smaller, more manageable, and focused pieces. Although some programming languages may refer to them as something else, such as subroutines, procedures, methods, or modules, most modern programming languages refer to them as functions. Functions take in data as an input, then process the data, and then return the result as an output. There are essentially 2 types of functions. Standard library functions are the built-in functions provided by the programming language. Common examples include the if, else, while, and print functions. But programming languages also allow you to write your own functions. And once you've written a function, you can use it over and over again. The way that the blocks of code that make up a function are identified is different across programming languages. Some use braces, some use begin and end statements, and others use indentations, for example. There are a few steps to using functions. The first thing you need to do is define or create a function. When you define a function, you provide a function keyword, then give the function a unique name, and you provide the statements that make up the body of the function. Once a function has been defined, it then needs to be called or invoked. When you call a function, the specified actions within the function are performed using any specified parameters. While defining and calling functions are common to all programming languages, some programming languages, such as C and C++, also require you to declare a function. Next, let's look at the concept of objects. Understanding what objects are is key to understanding object-oriented programming. Object-oriented programming, or OOP, is a programming methodology that is focused on objects rather than functions, which is what procedure-oriented programming is focused on. The objects themselves will contain data in the form of properties or attributes, and code in the form of procedures or methods. The key distinction between the two methodologies is that where procedural programming uses methods to operate on separate data structures, OOP packages them both together so an object operates on its own data structure. Consider the real-world objects in your life, such as your car, bike, TV, or your washing machine, and ask yourself the following two questions. What states can the object be in, and what behaviors can the object perform? When you think about your answers to these questions, you will find that the answers to these questions vary across the objects. More complex objects will typically have more potential states they can be in, and will be able to perform more behaviors. In programming, a software object is similar to a real-world object, conceptually speaking, in that they too consist of states or properties and behaviors or methods. Software objects can be anything, such as a Windows service, a user account, a database table, or a system folder. Objects store their properties in fields, referred to as variables in some programming languages, and expose their behaviors through methods, referred to as functions in some programming languages. In this video, you learned that a function is a piece of structured, standalone, and reusable code that will perform a single specific action. The defining and calling of functions is common to all programming languages. Object-oriented programming is a programming methodology that is focused on objects rather than functions. And software objects consist of properties and methods. Welcome to Introduction to Software Architecture. After watching this video, you will be able to describe what software architecture is, explain the importance of well-designed software architecture, explain how software architecture impacts design decisions, such as tech stacks and production environments, and list several artifacts from software architecture design. Software design and documentation take place during the design phase of the SDLC. Software architecture, simply put, is the organization of the system. Software architecture serves as a blueprint for the software system that the programmers use to develop the interacting components of the software. The architecture comprises the fundamental structures of a software system and explains the behavior of that system. The architecture defines how components should interact with each other, the operating environment, and the principles used to design the software. The software architecture captures early design decisions that are often costly to change once implemented, and a software's architecture addresses non-functional aspects of the application, such as performance, scalability, maintainability, interoperability, security, and manageability. Well-designed software architecture is important for a number of reasons. First, it balances the differing needs of the stakeholders and serves as a basis for communication among team members. Next, the architecture represents the earliest design decisions, and those decisions conflate other coding implementation decisions later in the development process. Also, the well-designed architecture allows for agility due to changing requirements. A well-organized architecture increases the lifespan of a software system even when implementation details change. Architectural design also guides the choice of technology stacks used for the system. Remember that architecture addresses non-functional capabilities, so choosing stacks that address these requirements is paramount in the design phase. Recall that a tech stack is a list of all the technologies, including software, programming languages, libraries, and frameworks that will be used to create the system. The architects must be aware of the stack's advantages and disadvantages to anticipate development needs. Much like blueprints communicate design decisions to the builders of a house, there are also several artifacts produced during the architectural design phase that are used to communicate the software design to the stakeholders. These artifacts include a software design document, or SDD, an architectural diagram, and unified modeling language, or UML diagrams. The SDD is a collection of technical specifications that indicate how the design should be implemented. It provides a functional description of the software and design considerations, such as assumptions, dependencies, constraints, requirements, objectives, and methodologies. The architectural diagram displays components, their interactions, their constraints, and their confines. It displays the architectural patterns used in the design. Architectural patterns are general, reusable solutions to commonly occurring problems and will be discussed in more detail in an upcoming video. UML diagrams are diagrams that communicate structure and behavior using common programming language agnostic notation. UML diagrams will also be discussed in more detail in another video. But another topic to be discussed in this module as it relates to software architecture includes production deployment considerations. The architecture drives choices about the environment in which the software is released. The production environment is comprised of the infrastructure that runs and delivers the application to the end user, such as the servers, load balancers, and databases. In this video, you learned that software architecture functions as a blueprint and represents the underlying organization of the application. A good architectural design is important because it serves as a basis for communication among team members. Software architecture represents the earliest design decisions, is hard to change once development starts, and accommodates changing requirements during development. Architectural design influences technology stack choices and the production environment. And artifacts resulting from the design include the SDD, the architecture diagram, and UML diagrams. Welcome to Software Design and Modeling. After watching this video, you will be able to compare and contrast the terms structure design and behavioral models, describe unified modeling language, or UML, and its advantages when designing software, and discuss the purpose of an interaction and a state transition diagram. Software design is a process during which structural components and behavioral attributes of the software are documented before it can be developed. One of the key activities of the design process is modeling the software to express its design. This involves creating visual or diagrammatic representations of the bigger software solution and its subcomponents, as well as the interactions between them. This can be done using simple flowcharts or more standardized methods like UML. A software system can be construed in terms of structural elements. Structured design conceptualizes a software problem into well-organized, smaller solution elements called modules and submodules. Structured design stresses organization in order to achieve a solution. A well-structured design should contain modules that are cohesive and loosely coupled. Cohesion means that all functionality-related elements are grouped together, and coupling is the communication between different modules. For a system to be loosely coupled, the modules should be weakly associated so changes in one component have minimal effect on another. And loose coupling is an architectural principle often used in service-oriented architectures and microservices-based architectural patterns, which will be discussed later in the module. This diagram shows a simplified example billing system. Modules are arranged in a hierarchy and communicate with each other. The rectangles represent the modules and submodules, and you can see that billing is the main module and the other rectangles are submodules to the main billing module. In this example, the submodules are insurance verification, submit claim, and output total. The arrows represent the flow of the data in the system. Behavioral models describe what a system does without explaining how it does it. The overall behavior of a system can be communicated through behavior models. There are a number of different UML diagrams that can be used to communicate the behavior of a system. We will discuss two such diagrams, a state transition diagram and an interaction diagram. When developing a complex software system with interconnected modules, it can be difficult to remember the relationships, behaviors, and hierarchies among different elements. UML, which stands for Unified Modeling Language, is a way to visually represent the architecture, design, and implementation of complex software systems. UML is a standardized modeling language that can be used throughout development processes. UML diagrams can be divided into two classes, either structural or behavioral. UML is programming language agnostic, so software developers can readily interpret and apply it to their work, no matter which language they are developing in. There are several advantages of using UML to communicate architecture, behavior, and structure with development teams. The biggest advantage of UML diagrams is that they allow you to plan out features before any coding takes place, which saves time and money. Secondly, the diagrams can be used to bring new team members or developers switching teams to get up to speed quickly. Also, the diagrams can be used to facilitate communication between technical and non-technical audiences more easily. And finally, having a visual representation of the system allows developers to navigate the source code because they can see the relationships among modules. So there are many types of UML diagrams, but generally, UML diagrams can be classified as either behavioral or structural. We will discuss behavioral models next, and then object-oriented design. The behavior of a system can be explained and represented with the help of a UML diagram called a state transition diagram. The state transition diagram is a collection of states and events that describes the different states that a system has and the events which cause a change of state in the system. The diagram shown is an example of a state transition diagram that models a patient going to see a doctor at a clinic. The different states include waiting, testing, and with the doctor. The arrows represent possible transitions from one state to another and names the event that triggers the transition. An interaction diagram is used to model the dynamic nature of a software system. They help visualize objects and their relationships. A sequence diagram, which is the type of interaction diagram shown here, displays the communication between objects with respect to time. This example shows a patient making an appointment in an online portal, and this is another example of a behavioral UML diagram. In this video, you learned that structured design breaks down a software problem into well-organized, smaller solution elements. Behavioral models describe the behavior of the system without explaining how the system implements the behavior. Developing UML diagrams saves time and money by helping developers quickly get up to speed on a project, plan features in advance of coding, and help developers navigate resource code easily. A state transition diagram is a behavioral model containing a collection of states and events that describe the different states of a system and the events which cause a change of state. And finally, an interaction diagram describes how interacting objects communicate. Welcome to Object-Oriented Analysis and Design. After watching this video, you will be able to explain what objects and classes are, describe the purpose of a class diagram, and explain object-oriented design in relation to software architecture. Object-Oriented Analysis and Design, or OOAD for short, is an approach for analyzing and designing a software system when the system will use object-oriented programming languages to develop it. So, before we discuss OOAD, let's learn a little more about object-oriented programming in languages like Java, C++, or Python. At the heart of OOAD are objects. Objects contain data, and they also have behaviors that prescribe the actions the object can take. I could create an object, for example, that represents a patient. And let's say that patient's name is Naya Patel, and Naya needs to cancel an appointment she made. Before creating Naya, however, we must first create a generic version of a patient object. The generic version of an object is called a class. Let's discuss classes next before we discuss more about Naya. Specific objects, also called instances, are created from classes, which are blueprints or templates for an object. So, from our previous example, considering Naya Patel, Naya would be an instance of the patient class. The class contains the object's generic attributes, the properties and methods, but it is only when the object is created, which is called instantiation, inside the code, that these generic attributes are set to particular values. So, the patient class might have a variable called last name, which is a property, but does not specify what that last name is. Last name is just a placeholder until the object is created and assigned a name. And once the object has been instantiated, its methods can be called to make the object perform some action, such as making or canceling an appointment. OOAD is used for a system that can be broken down into objects that interact with each other. In this way, multiple developers can work on different aspects of the application at the same time. As noted earlier, visual UML diagrams can be created that show both the static structure and dynamic behavior of a system. We've seen a couple of examples of behavioral UML diagrams already, so now let's look at a structural UML diagram called a class diagram next, now that we know what classes are. This is an example of a class diagram. Class diagrams are commonly used to communicate a software system structure in OOAD. The class diagram shows how the classes in an object-oriented design relate to one another. Each box represents a class and shows its attributes. Recall that an object's attributes are both its properties or its data and its available actions, called methods. A class diagram also shows the relationships between classes. A subclass is said to inherit its parent class attributes, meaning it has the same properties and methods as the parent class, but also may add additional properties and methods. In this diagram, the nurse, doctor, and technician classes are subclasses of medical personnel, and the specialist class is a subclass of the doctor class. This means that doctors can do anything medical personnel can do, and specialists can do anything a doctor can do. In this video, you learned that object-oriented analysis and design is the process of planning a software system based on the behaviors of interacting objects. Objects contain data, and they also have behaviors that prescribe the actions the object can take. Classes are blueprints for objects, and a class diagram is a structural UML diagram that shows the relationship between objects. Welcome to Insider's Viewpoints, the importance of design and software architecture. In this video, we will hear from experts discussing the importance of design and software architecture in a software engineering project.
Design and architecture are crucial. If you don't know where you're going, how do you know what you need to do now? you always need to know what your program needs to be prepared to handle and the system that it's operating within. If you are running if you're running a bunch of applications that are all co-hosted on the same server, you can make certain assumptions about the ways those services can interact with each other that do not hold.
I also sometimes think of architecture and orchestration. So you can have like a beautiful, really nice sounding instrument, but if it's not in sync with the rest of the orchestra, it's going to sound like a complete cacophonous mess in the end. So you really need to think about the bigger picture, sustainability, whether what you're building actually makes sense in the larger sort of ecosystems.
And every time, if you spend the time to write your code and then you figure out why it doesn't work, you've wasted a lot of time writing that code. Maybe you've learned some things, not a total waste, but you've spent a lot of time that could have been spent moving forward. And so if you can think about those things ahead of time on a project, and then when you write your code, you're reasonably sure that the code you write is actually going to persist and get used, that's generally speaking a better place to be in. So architecture is very important.
There's a lot of talk about its scale, global availability. Often something you build would work very well in a very hyper-local environment, but not work well when it's expected to be used across the globe, or works well for one user but doesn't work well for a million users.
I'm building the service. I need X, Y, Z pieces of data to come into the function that I want to write. Where are those things coming from? How are they getting passed in? Once I have them, what do I need to do with them? What else needs to access this data? And how am I going to get the data to those other parts also? And if you don't have those questions answered, you end up writing a lot of churny code. If everything is on a separate server somewhere in the cloud, or separate physical servers that are just located somewhere different inside your data center, then you have to incur a network hop to go over them. And that takes time. Your page might start timing out, and your customers might get really upset at you for how long things take. And so if you're building something in like a microservice architecture, the way that you load your data becomes much more important than if everything is hosted together on the same server. But maybe the question of who is using my service? How do I know who you are? That can become an interesting question depending on where your services are running, and what mechanisms are available to you to identify people. If you want your customers to log into a website, how are you doing account management? How do you know who that person is and what they're allowed to do? Or if you have multiple services talking to each other, again, how do you know what that service is, what it's allowed to do? How do you make the call between one and the other? How do you transmit data between different parts of your stack? So architecture is very important. It doesn't always have to be super well-defined, super strictly defined, but you need to have some idea of what things do you need, roughly where they're going to live, and what are they responsible for? Those would probably be the three big questions to ask: what, where, and scope of them. So
these sorts of concepts, you have to think about those things when you're designing or architecting a system. You're thinking like 5-10 years ahead too when you're thinking about architecture and design. You're not thinking about just building something quickly and getting it up. You actually want to plan ahead. So I think a lot of architecture and design is thinking about, how many steps, how many years, whatever in the future, what is it going to look like then? What do you need to do to keep growing the system and evolving it? Because you don't want to make gigantic architecture changes that often. You don't really. When buildings are repaired, there's like tiny bits of things get repaired, and then at some point you tear the thing down and rebuild it. And I think that's a similar model applied to sustainable system architecture. You don't want to re-architect and redesign every few years. You want it to last as long as you possibly can.
Welcome to Approaches to Application Architecture. After watching this video, you will be able to describe component-based architectures and service-oriented architecture, explain the characteristics of a component, differentiate between components and services, and describe the characteristics of distributed systems. A component is an individual unit of encapsulated functionality that serves as a part of an application in conjunction with other components. There are 6 characteristics of components. Components should be reusable, replaceable, independent, extensible, encapsulated, and non-context specific. Let's briefly discuss each of these principles. Reusable implies that components should be designed such that they can be reused in different applications. Replaceable means that a component should be easily replaced with another component. Independent means the component should be designed so it doesn't have dependencies on other components. Extensibility entails the ability to add behavior to a component without changing other components. Encapsulation consists of bundling a component's data and methods to hide its internal state so it doesn't expose its specific implementation. And creating a component that is non-context specific involves designing it so it operates in different environments. Data that sets its internal state should be passed to the component rather than included within or accessed by the component. Let's take a look at some examples of components. An API can be packaged as a component if it can be reused across multiple systems and applications. For instance, a component could be an open-source API that connects a system to a particular database. A component can also be the interface for a database, called a data access object, that switches the user to a different database without the application knowing about the switch. And a controller is a type of component that determines which other components need to be called for a particular event. It controls the flow of data between 2 other components. Component-based architecture, then, focuses on the decomposition of the design into these logical components. Component-based architecture provides a higher level of abstraction than object-oriented designs. A component-based architecture should define, compose, and implement loosely coupled independent components so they work together to create an application. A service is like a component, also a unit of functionality, but it is designed to be deployed independently and reused by multiple systems. A service focuses on a solution to a business need. A key difference between a component and a service is that a service will only have one unique, always running instance with whom multiple clients communicate. This diagram displays the relationship between objects, components, and services in a layered architecture. Services are made of components, and components consist of objects. A service is a type of component. It is meant to be deployed independently of the overall system. Examples of services include checking a customer's credit, calculating a monthly loan payment, or processing a mortgage application. In a service-oriented architecture, or SOA, services are loosely coupled and interface with each other via a communication protocol over a network. SOA supports building distributed systems that deliver services to other applications through the communication protocol. So let's discuss distributed systems next. A distributed system is a system with multiple services located on different machines that coordinate interactions by passing messages to each other via a communication protocol such as Hypertext Transfer Protocol, also known as HTTP. Even though the services on a distributed system operate on multiple machines, a distributed system appears to the end user as a single coherent system. A distributed system shares resources such as hardware, software, and data. They are fault-tolerant, meaning if a node or a service fails, the system continues to run, also implying that the system may change during execution without service interruption. Multiple activities run concurrently on a distributed system, reducing latency and increasing throughput. Another property of distributed systems is that they are scalable as the number of users increases. The computers running the distributed system do not need to use the same kind of hardware or operating systems. And a distributed system may be made up of different kinds of computers and programming languages. Now, a node is any device on a network that can recognize, process, and transmit data to other nodes on the network. A distributed system consists of multiple interconnected nodes where the nodes are running one or more services in an SOA. Distributed systems generally use one or more of the following basic types of architecture: client-server, 3-tier, peer-to-peer, or microservices. These application architectures and their characteristics will be discussed in another video. In this video, you learned that components are reusable, independent, replaceable, extensible, encapsulated, and non-context specific. Component-based architecture is the decomposition of the system into logical, independent components. Services are made of components, and components consist of objects, and services are deployed independently and can be reused by multiple systems. In an SOA, services are loosely coupled and interface with each other via a communication protocol over a network. And lastly, distributed systems run on multiple services on different machines, and they appear to the end user as a single coherent system. Welcome to Architectural Patterns in Software. After watching this video, you will be able to describe different software architectures, such as 2-tier, 3-tier, peer-to-peer, event-driven, and microservices, and provide an example of each architectural pattern. An architectural pattern is a repeatable solution to a problem in software architecture. Patterns highlight common internal elements and structures of a software system. Different architecture patterns may share related characteristics. In this video, we will discuss 2-tier, 3-tier, peer-to-peer, event-driven, and microservices. However, there are many other patterns that will not be covered in this video. These patterns include Model View Controller, Message Broker, Blackboard, Pipe Filter, and Controller Responder. The 2-tier architecture, also called client-server, is a computing model in which the server hosts, delivers, and manages most of the resources and services delivered to the client. The interface resides on the client machine and makes requests to a server for data or services. This type of architecture usually has more than one client computer connected to a server component over a network connection. A 3-tier architecture, or an N-tier architecture, where there are more than 3 layers, is the most common software architecture. The 3-tier architecture is composed of several horizontal tiers that function together as a single unit of software. A tier only communicates with other tiers located directly above and below it. Related components are placed within the same tier, and changes in one tier do not affect the other tier. The 3-tier architecture organizes applications into 3 logical and physical computing tiers: the presentation tier, or user interface; the middle tier, which is usually the application tier, is where business logic is processed; and the data tier, where the data is stored and managed. The peer-to-peer architecture, or P2P for short, consists of a decentralized network of nodes that are both clients and servers. The workload is partitioned among these nodes. Peers make a portion of their resources directly available to other network participants without the need for central coordination by servers. Resources are things like processing power, disk storage, or network bandwidth. Peers both supply and consume resources, in contrast to the traditional client-server architecture, in which the consumption happens strictly by the client and the servers supply the resources. Peer-to-peer architecture is useful for file sharing, instant messaging, collaboration, and high-performance computing. An event is anything that results in a change of state. An event can be thought of as an action that is triggered by the end user, such as a mouse click or another part of the program. Event-driven architecture focuses on producers and consumers of events. Producers listen for and react to triggers while consumers process an event, and the producer publishes the event to an event router. The router determines which consumer to push the event to. The triggering event generates a message called an event notification to the consumer which is listening for the event. The components in event-driven architectures are loosely coupled, making the pattern appropriate for use with modern distributed systems. Microservices are an approach to building an application that breaks its functionality into modular components called services. An application programming interface, also called an API, is the part of an application that communicates with other applications. An API defines how two applications share and modify each other's data. APIs can be used to create a microservices-based architecture. The API gateway routes the API from the client to a service, and orchestration handles communication between services. Let's discuss an example for each of these patterns. A text messaging app is an example of a two-tier pattern. The client initiates a request to send a text message through a server, and the server responds by sending that message to another different client. And another example of the two-tier pattern is database clients connecting with database servers. Many web apps use the three-tier pattern. They use a web server to provide the user interface, an application server to process user inputs, and a database server that handles data management. The functions of these three types of servers will be discussed in more detail in another video. Ride-sharing apps such as Lyft and Uber are examples of event-driven patterns. The customer sends a notification that they need a ride from a particular location to another location, and that event is routed to a consumer. Cryptocurrencies such as Bitcoin and Ethereum use a peer-to-peer pattern. Each computer in the blockchain acts as both server and client. Finally, social media sites are composed of microservices. A user has an account, and that account can request different services, such as adding friends, targeted ad recommendations, and displaying content. Architectural patterns are not necessarily mutually exclusive. In other words, two or more of these patterns can be combined. For instance, a three-tiered architecture can also be microservice-based, or a peer-to-peer architecture can also be event-driven. However, not all architectural patterns can be used in conjunction with others. A peer-to-peer cannot also be two-tier because a single machine in a peer-to-peer architecture represents both a client and a server, whereas a two-tier architecture separates the client from the server. It is up to the system architect to determine which architectural patterns the software system should adhere to. In this video, you learned that an architectural pattern is a repeatable solution to an architectural problem. A two-tier pattern has a client and server. Text messaging apps use a two-tier pattern. A three-tier pattern has three tiers that interact with each other. Web apps use a three-tier pattern. An event-driven pattern has actions that are produced and responded to by a consumer. Ride-sharing apps use an event-driven pattern. The peer-to-peer pattern consists of a decentralized network of nodes that acts as clients and servers. Cryptocurrency is an example of the peer-to-peer pattern. Microservices are loosely coupled individual services that behave as a single system and interact with the client. Communication is orchestrated among services, and social media sites are an example. And finally, two or more patterns can be combined in a single system, but some are mutually exclusive. Welcome to Application Deployment Environments. After watching this video, you will be able to list different types of pre-production environments and state their purpose, differentiate a production environment from other application environments, and compare and contrast deployment options. An application environment is the combination of the hardware and software resources required to run an application. This includes the application code and/or binary executables for its various components or modules, the software stack it requires for running the application, such as modules and libraries it depends on, third-party applications and middleware, and the operating system. Any networking components and infrastructure, as well as any physical or virtual hardware, including computing or processing resources, memory, and storage. There are a variety of environment types, depending on the application's stage in the life cycle. The pre-production environments are those platforms that the application resides on in various forms as it gets prepared for production. Common pre-production environments are development, QA, which stands for quality assurance, and staging. The development environment is the platform on which the application is being actively coded, and in many cases, it may just be the developer's workstation. The QA environment, sometimes called testing, is the environment that allows the QA team to test the application's components. The staging environment is the environment that is as close to replicating the production environment as possible, but is not meant for general users. Now let's discuss the production environment. The production environment, often just called production, includes the entire solution stack, consisting of both hardware and software on which the application runs as additional infrastructure components. The production environment is intended for all users. Unlike the pre-production environments, this robust environment must take the application load into consideration because it is the environment intended for general use, possibly by thousands or millions of people at the same time for enterprise-level applications. Production environments must also take into account non-functional requirements like security, reliability, and scalability. This makes the production environment more complicated than the pre-production ones. Now let's take a look at the production environment infrastructure. There are several options for deploying application environments. In on-premises deployment, the system and its infrastructure resides in-house, within the organization's physical location, often behind a firewall. Firewalls prevent unauthorized access to or from a private network. If an organization desires greater security or control of an application and the data in use by that application, it may deploy the application on-premises. For on-premises software deployments, an organization is responsible for the system, hardware, related infrastructure, and maintenance required to run the application. On-premises deployment is usually more expensive when compared to cloud deployment. So let's discuss cloud deployments next. There are 3 types of cloud deployment models: public, private, and hybrid. The public cloud is when you leverage the software supporting infrastructure over the open internet on hardware owned by the cloud provider. That hardware and the associated services are shared with other companies. Public cloud providers include Amazon Web Services, or AWS, Microsoft Azure, Google Cloud Platform, and IBM Cloud. The public cloud is the most common due to its scalability and cost. With a private cloud, the cloud infrastructure is provisioned for exclusive use by a single organization. The software system can be run on-premises, or the infrastructure could be owned, managed, and operated by a service provider. For example, AWS is also a private cloud service provider. The main advantage of a private cloud is its increased security, but it also allows for more flexibility because it can be fully customized. Now, a mix of both public and private clouds working together seamlessly is called a hybrid cloud model. A hybrid cloud potentially optimizes the advantages of both public and private cloud models with regard to cost, security, scalability, and flexibility. In this video, you learned that application environments include development, testing or QA, staging, and production. Production environments must also take into account non-functional requirements like load, security, reliability, and scalability. And application environments can be deployed either on-premises on traditional hardware or on public, private, or hybrid cloud platforms. Welcome to Production Deployment Components. After watching this video, you will be able to describe components commonly required for deployment in a production environment, describe the purpose of a firewall and a load balancer, and differentiate between different types of servers. Let's consider an N-tier architecture required to deploy an application in a production environment and represent the infrastructure using a diagram. The top tier is the presentation tier, which contains the front-end client applications. All of the other tiers are located behind a firewall. Firewalls and other components mentioned in this diagram will be discussed in further detail later in the video. Now, the next tier is the web tier, which has a web load balancer that distributes incoming traffic to several web servers. The tier below the web tier is the application server tier. This tier contains an app load balancer or a proxy server that routes traffic to different application servers. And the bottom tier is the data tier that contains the database server. A high availability replica of the database is often used to ensure reliability. Some environments may have additional components or tiers. Also, not all of these components are necessary for every deployment. For example, in some environments, there might not be a need for both application servers in addition to web servers. Now, let's look at these components in further detail. A firewall is a security device that monitors traffic between networks. It permits or blocks requested data based on a set of security rules. It acts as a barrier between networks to block viruses, malware, and hackers from accessing the internal network. The purpose of load balancers is to distribute network traffic efficiently among multiple servers, called a server farm, on a network. Load balancers are used to prevent server traffic overload and are located between clients and the servers. A load balancer determines which servers are capable of fulfilling those requirements in a manner that maximizes availability and responsiveness. Load balancers ensure that no one server is overworked. They manage concurrent requests from clients and return the correct data in a fast and reliable manner. Web and application servers are either software or machines that provide services, resources, data, or applications to another computer program called the client. Servers store, process, and manage network data, devices, and systems. A web server delivers content such as web pages, files, images, and videos to a client. And a web server primarily responds to hypertext transfer protocol requests coming from a web browser, such as a user accessing a website. An app server is a server that runs business logic and provides the application to the client rather than the client running the app on their own machine. Its primary job is to enable interaction between the end user and the server-side application code. The application code represents the business logic that determines how data can be created, stored, and changed, and that logic dictates things like transaction results and what data is written to and retrieved from a database. Next, a proxy server is an intermediate server that sits in between two tiers and handles requests between those tiers. A proxy server can serve multiple purposes, such as load balancing, system optimization, caching, acting as a firewall, obscuring the source of the request, encryption, scanning for malware, and more. And a proxy server can improve the efficiency, privacy, and security of data flowing through a network. Finally, a database is a collection of related data stored on a computer that can be accessed in various ways. A database is usually controlled by software, called a database management system or DBMS. The DBMS controls a database by connecting the database to users or other programs. The database server controls the flow and storage of data. The DBMS connects the database server to an application so data stored in the database can be retrieved or manipulated by the application. In this video, you learned that common components needed for a production environment include a firewall, a load balancer, web and application servers, proxy servers, and database servers. A firewall is a security device that monitors traffic between networks. A load balancer distributes network traffic among servers. A web server delivers web content, such as web pages, files, images, and videos, to a client. An application server runs business logic and provides the application to the client rather than the client running the app on their own machine. And finally, a database server stores and controls the flow of data through a database management system. Welcome to Insider's Viewpoints, Deployment Architecture. In this video, we will hear from experts discussing important aspects of software deployment.
I think often you need to think about scale, like the sort of just in general, is your system, how many users will your system has, how much data do you expect to flow through it, how much data do you expect to produce and store, how real-time do you need the data access to be, what is your logging story like, do you have privacy concerns, do you need to ensure that data is anonymized, so you kind of, I think, thinking about the scale, the regionality, is it global, is it local, what is your logging, what are your logging needs both for internal and external data analysis, mapping out the data flows. So these are sort of the things I think we start with as with design principles.
And in terms of choosing infrastructure, like whether you want to go serverless, whether you want to use a hosted backend, or you're hosting your own, these are all design and architectural decisions that will probably, for your first few jobs, already be taken for you.
What's your system of SLOs, your availability look like, service level objectives, right? So you need to just think about sort of those sorts of things. I think ensuring you like what does a healthy system mean to you? What does a well-running system mean to you? You need to define those metrics up front and sort of have those monitored and watch those as your system lives on, and make sure that you're meeting those objectives and goals and have a plan to mitigate them if they fall below where you like them to be. These days, I think microservices and keeping code as modularized as possible to avoid giant sort of bloated behemoth code bases is really important so that people can move fast and deploy fast.
But what I would say is a critical part of the deployment option is when you look at deployment and integrating your code, testing is fundamental. So I would strongly urge all of you to really pay attention to testing and to use test-driven development, TDD, test-driven development, as a development habit that you inculcate in your life as developers and engineers. It'll stand you in very good stead. I think that's the single most important part. You won't always do it, but you should try and do it as much as you can.
You need to think about whether you want to canarying. There's a canary in a coal mine analogy. So there's a process called canarying where you try to roll out new code and test whether it's going to blow things up or break things. And you want to think about you need to think about how quickly you need to release or not, how quickly you may need to roll back your code or not.
Welcome to What Does a Software Engineer Do? After watching this video, you will be able to describe the types of software that software engineers develop and the technologies that they use. Identify the categories of software engineers and the teams they work in, and describe the day-to-day tasks and responsibilities of a software engineer. Software engineers use their talents in engineering, mathematics, and computing to design and develop software that solves real-world problems for their users. If you're an analytical thinker who enjoys problem solving, software engineering might be the career for you. Software engineers develop a plethora of different types of software, from desktop to web applications, to mobile apps, games, operating systems, and network controllers. They use many technologies to do this, including programming languages, development environments, frameworks and libraries, databases, and servers. There are two categories of software engineer: back-end engineers, also known as system developers, who build the computer systems and networks that front-end applications use, and front-end engineers, or application developers, who are more client-focused. They create the software that users will interact with, such as Android, iOS, and Windows applications, and platform-agnostic websites. Software engineers work in a wide variety of settings. You could work in a team developing off-the-shelf software, bespoke software to meet a specific client's requirements, or internal software for users in your organization. And within your team, you might work on data integration layers, which access and load data from a variety of sources into your solution; business logic, which applies real-world business rules to the data in your solution; or user interfaces, which enable users to interact with your solution. On a day-to-day basis, you might undertake tasks such as taking user specifications and designing new software systems to meet their requirements, writing code and testing that it works as expected, evaluating and testing new software programs, optimizing software programs for maximum efficiency, maintaining and updating existing software systems, documenting code so that other developers can understand it, or presenting new systems to users and customers. And some software engineers, such as DevOps practitioners, also integrate and deploy their code onto the underlying infrastructure. As well as building your own systems, you'll also be testing, improving, and maintaining software built by your colleagues. The responsibilities of a software engineer are as many and varied as the tasks which they undertake. In a junior position, you are likely to start out with a limited set of responsibilities focused on writing, testing, deploying, and documenting code, but as your career progresses, this will widen. And in a senior role, you will likely have primary responsibility for multiple areas of the software solution, including the planning and designing phases. In this video, you learned that software engineers design and develop a range of software solutions. Back-end engineers build the computer systems and networks, and front-end engineers build the user interfaces. Software engineers undertake a range of tasks, from designing and writing new software to maintaining and updating existing software. And as your career develops, you will move from being responsible for one small section of code to many areas of one or more products.
Hi, I'm Shelley, and I work as a software engineer for a startup company in North Carolina. When I arrive at work in the morning, I spend some time catching up on my messages and checking my calendar for the day. Before heading to my daily stand-up meeting, I quickly check the status of my code merge request from yesterday. Great! It's got positive feedback from others in the team and some suggestions from my mentor about improvements I could make. I'll work on those later. During our daily stand-up meeting, each member of the team talks about what they achieved yesterday and what they're working on today. Jonathan, my mentor, gives me some more advice about how I can optimize the code I wrote yesterday. After the meeting, I return to my desk, excited to implement the feedback I've received and continue working on my code. Now, it's focus time, when I can concentrate purely on my project work. I use Jonathan's comments on the merge request alongside the notes that I made during our stand-up to re-engineer a couple of methods to run faster. I also use some of our analysis software to compare timings with the previous version, and, when I'm satisfied that there's a marked improvement, I submit a new merge request to gather additional feedback. I then send Jonathan a message to ask if he can review it later today. After lunch, I'm invited to a meeting where the marketing department explains that they need a new feature to monitor the effectiveness of their campaigns. One of the senior software engineers, Marie, mentions that she's previously developed a React-based front end for a management dashboard that we could easily reuse. I'm tasked with creating a minimum viable product, MVP, for a small team in the marketing department to trial and provide feedback on. I've not used React before, but this is a great chance to get some hands-on experience with it while still making a contribution to the team. Learning on the job and developing new skills is an important part of a software engineer's role. On my return from the meeting, I find that Jonathan has reviewed my code and approved the merge request. He's impressed with the speed of the code and with my coding style. It's really helpful to get regular feedback from more experienced members of the team who can suggest alternative ways of solving problems. I've also received a bug report notification for one of the features I was working on last week. When I review the full report, I quickly spot the mistake and begin fixing it. To check that the fix and the original functionality work as expected, I develop and run a test case for the feature. It passes, so I submit a merge request for my fix and resolve the bug. Now I'm free to start researching React. I spend the rest of the afternoon reviewing the React documentation, watching videos, and reading blogs to give me an overview of React. I then contact Marie to ask for access to the front end she developed so I can review the existing solution. This gives me design ideas and inspires me to start planning my dashboard. On my cycle home, my head is buzzing with thoughts about how the new dashboard will look and the functionality I could provide through it. Tomorrow can't come quickly enough.
Welcome to Skills Required for Software Engineering. After watching this video, you will be able to differentiate between hard and soft skills, describe the hard skills needed by a software engineer, and describe the soft skills needed by a software engineer. Hard skills are the practical skills needed to perform a particular role. So, for a software engineer, these will be the technical skills they need to design, build, maintain, and repair software solutions. Hard skills are learned skills. In the case of software engineering, they are usually learned in a school, college, or university environment, or by studying online courses, diplomas, or certificates. Alternatively, they can be gained from years of experience in the field. Hard skills are quantifiable, so it's easy to measure whether an individual can demonstrate a particular skill and to certify them in that skill. Commonly required hard skills in the software engineering sphere include programming languages, version control, cloud computing, testing and debugging, monitoring, troubleshooting, agile development, and database architecture. Now, soft skills, on the other hand, are less tangible. They are your personal characteristics and interpersonal skills. They're the non-technical skills that are part of your personality and, as such, are harder to define, quantify, or certify than hard skills. Because they're not linked to a particular business, though, they are easily transferable between roles and across industries. The job requirements for any role will be a combination of hard skills and soft skills. So let's look at some of the hard skills that are relevant to a software engineer. Software analysis and design skills are essential for a software engineer. You need to be able to analyze your users' needs through a variety of methods and then design effective solutions that meet those needs. You'll also need to be able to develop those solutions. Computer programming and coding are essential development skills. While some job roles require a specific language and/or toolset, employers will sometimes welcome you with experience in any language but expect you to cross-train into their preferred language. The Coding Bootcamp website, Coding Dojo, states that some of the most in-demand languages are currently Java, Python, C#, and Ruby. An understanding of a variety of frameworks and object-oriented principles are also key skills for a software engineer. While you'd hope to always create flawless solutions, it is likely that at times your code will either not work or not work in the way that you intended. You need testing skills to determine whether your code meets the functional specification of the solution and if it's easy to use. And when your code isn't working as expected, you need debugging skills to work out why. And when your solution is complete, you need deployment skills to distribute it to your users. These could include shell scripting, containers, and continuous integration and continuous delivery or CI/CD tools. You'll also need monitoring skills so that you can review the performance of your solutions and troubleshooting skills to resolve any issues that may occur. So now let's look at the soft skills of a software engineer. Teamwork is a key soft skill. Software engineers work in a variety of teams, some based on the project they're working on and some based on their specific role. If you're practicing agile development, you may also work in small teams known as squads. And you might also work closely alongside another developer in pair programming. Working in teams enables you to take advantage of each individual's strengths, as well as providing opportunities for you to gain new knowledge and skills. You'll need to be able to communicate with a wide variety of stakeholders in your project, from technical colleagues to non-technical personnel. For example, you may need to ask your peers for support and ideas, your manager for guidance and direction, your client for clarification of their needs, and your users how they'd best interact with your solution. Software solutions are often time-sensitive projects, and as such, your manager will be keen that you meet their deadlines. Managing your own time is imperative to ensure that you don't cause delays to others waiting for your work. And with increasing numbers of teams working across time zones, what could previously only seem like a small local delay can create a whole day of lost time for someone located elsewhere in the world. Software engineers need great problem-solving skills to succeed. You need them in the design phase to work out how to create an appropriate software solution, in the development phase to work out the code required to perform the task required, in the testing and debugging phase to locate and resolve any bugs, and throughout the lifecycle of the software to manage any issues that may arise. And when those issues do arise, you need to be adaptable to meet the changing needs of the project. Examples of changes include your client requesting a change or addition to the functionality, your manager requesting you to move on to a different area to meet a looming deadline, or your user requesting an alternative method of achieving a specific task. And finally, you need to be open to feedback on your work. Most software teams use some type of peer review system where peers review each other's code. This helps enforce any corporate standards and improves the code. In a junior role, you'll also likely have a mentor who'll provide feedback and pointers where you can improve. And your stakeholders will provide feedback on pre-release and final versions of your solution. Accepting all of this feedback in an open and welcoming way ensures that your solution becomes the best that it can be and that you progress in your role. In this video, you learned that a combination of hard and soft skills are essential to a software engineer. Hard skills are measurable, learned skills such as programming, testing, and troubleshooting. And soft skills are your personality and characteristics, such as communication and problem solving. Welcome to Insider's Viewpoints, Advice to Future Software Engineers. In this video, we will hear from software engineers discussing their advice to those who are considering getting into the field.
Practice. You should practice all the time. You should learn new skills as much as you can. There are a lot of free resources out there that you can use to help you build new projects. I think the best way to continue working on your craft is to not only learn new things, but also use them to build new projects. Doesn't matter if it's something that's been done before. The point is that you're doing it now, and you're using the tools that you've used to build something new.
The most important thing for my career has been finding a business domain that I am interested in that has what look like not low-hanging fruits, but interesting problems to grapple with. The interesting problems for you are certainly going to be different than the interesting problems for me. But if you narrow down the domains that you're interested in, that can really help tailor both the things that you study, the types of jobs that you apply for. I have other friends where the domains that they're super interested in is like machine learning. Like they're just nuts for machine learning, and so they'll do anything that they can exercise like an artificial intelligence kind of thrust to the whatever business problem it is that they're working on. So like find that general domain and then kind of like dive in on that one.
But don't be scared to fail either. I think the beauty about one of the beauties about software engineering and the way that tech is evolving is there are a lot of opportunities, and there will continue to be new opportunities, and there's lots of movement in the industry. So if you take a job and you really are excited about it, but it ends up not working out as well, you can always, I think, move to somewhere else. There's lots of different types of lots of roles, lots of companies, all that sort of people move around. So don't let one potential failure either mean you give up. I think wouldn't be a failure.
Yes, so my best advice for those looking to get into the software engineering industry is to figure out what role you want to get into, make a list of the required skills for that role, and find free resources to start learning online. So when I was exposed to coding in 2018, after trying a few technologies, I decided that I wanted to be a front-end engineer or a front-end developer. And so I made a list of all the skills that I needed, and I started learning those skills using like free or low-cost resources online.
I think being careful about what's sort of hot and new. There's often, this is more specifically to like taking jobs and how do you find like a good role and fit for you. I know a lot of companies will often sort of market themselves as being, we're working with XYZ new technology. It's super hot, and it's like the latest and greatest, and almost use buzzwords as a way to attract people. Be inquisitive and ask clarifying questions. Be wary in that sense too, or cautious when it comes to some of the buzzwords and new things, and just know what you're getting into.
Don't neglect the job hunt process. Pay due attention to that, because if you just study and don't pay attention to the job hunt process, you're going to get frustrated because you're going to finish one phase and then have a long period of frustration and self-doubt after that. So if you can do the job hunt phase in preparation sort of in parallel with the latter half of your learning journey, I think you're going to be prepared to hit the market hard when you're ready. And it's just a question of time after that, time and persistence.
Welcome to Insider's Viewpoints, Advice to Women in Software Engineering. In this video, we will hear from software engineers discussing their advice to women in the field or who are considering getting into the field.
Recently, there have been a lot of good positive momentum and diversification of the industry, and making software engineering a more welcoming place for women in general.
So I come from work environments that are, primarily women, and now I'm in a work environment that is primarily men. I think I've had a pretty good experience with my coworkers personally, but in the beginning, it did very much feel like a little bit kind of like you're alone because, you're either the only or one of 2 or 3 women on your team. I would say just remind yourself that you actually do deserve to be there, that you actually do belong. You do belong there. And everybody started exactly where you are. Everybody who started as an engineer and even at your company started and was like, I do not know what's going on, but you're capable and you'll figure it out.
But if you're a software developer at a company, your main job should be software development. And if your bosses or management or other people in the company want you to do other types of work, you should be getting compensated for it. You should have a title that reflects what it is that you do. I have seen this happen a lot where the woman on the team will be the one who cares about diversity, for instance, and so is part of diversity workshops and clubs at the company, and is participating in diverse hiring events and doing all sorts of like extra training around that side of things. And then review time happens, and as a software developer, if you're getting reviewed on code, you need to make sure that you're getting enough of that code in your life. Everyone needs to contribute. Everyone needs to pull their weight. It can't all go on one person.
Join a team that does make you feel like they do support women and want to elevate women and advocate for women. So I think it's very fair to ask directly to, say, a hiring manager, what is your plan for diversity on your team? What types of programs do you or the organization or company have in place to ensure that women are successful? And be willing and open to speak up if there's something that you think is uncomfortable.
It's not all on you to fix if something is broken. There are other people involved, and they also are adults who should be reasonable human beings and able to take advice and constructive feedback. So let them take that advice and constructive feedback. You don't have to do all the changing.
Never be compelled to join a team where you're not feeling good about it, or you think that there's a risk that it's not a welcoming, so ask other people too. I think it's very fair to just ask for those questions.
Don't stay. Don't stay if you don't like it. The company needs you more than you need them, almost certainly. So leave when you can. If something isn't working out for you, leave. You have that ability. And there are companies that have less of that in their culture and less of that in their engineering teams. It can feel rough trying to find it sometimes, but if you do find yourself at a place that is not a healthy, positive, growing environment for you, leave. It doesn't reflect on you. Again, it reflects on the company.
And I know any company or organization that's even remotely taking diversity and inclusion seriously, specifically with regards to with women, will have programs in place to support women, elevate women, and basically there is an eye on that, and as there should be. There's a lot of effort being put into hiring women and getting women into senior leadership roles, which I think is very important.
Figure out what role you want and find free resources to get into those roles. One thing to bear in mind is, as a woman, we are a minority and we're underrepresented in the tech industry. So there are a lot of free or low-cost programs tailored specifically to women who want to get into computing, or women who are in computing looking to advance their careers.
Welcome to Job Outlook for Software Engineers. After watching this video, you will be able to explain why demand is high for software engineers, describe the job outlook for a software engineer, describe what to expect from a software engineering role, and describe the employment options in software engineering. There are various reasons behind the current high demand for software engineers. Almost all industries need software to compete and grow, and this results in a continuous demand for software engineers. Most organizations require applications and websites for their company to function. Some apps and websites are for internal use, while others are used to interact with customers. The Internet of Things is also driving the need for software that interacts with products. This is a need that will continue to expand for the foreseeable future. All types of software programs, from messaging applications to commerce websites to office software, are available in different flavors from different vendors. Whenever one vendor releases a new version of their particular program, a competing company is likely to also update their program, requiring more software engineers to create the new releases, enhance functionality, and add new capabilities. So, the outlook is bright for software engineers. The U.S. Bureau of Labor Statistics predicts a higher than average 22% job growth rate for software developers, analysts, and testers from 2020 to 2030. That's an average of almost 200,000 openings each year in the United States alone. These roles are likely to be across many industries, from mobile application development to health and insurance. There is also predicted to be a large increase in security software due to the increase in computer security threats and cybercrime. Many software engineers are graduates with degrees in software engineering or computer science. However, increasingly, employers like IBM, Google, and Tesla are starting to hire non-graduates who demonstrate the required skills for the role. This opens software engineering up to a wider range of society, ensuring that the cost of obtaining a degree doesn't preclude candidates from the industry. Salaries for software engineers vary significantly with years of experience in the field. As you acquire more experience and become harder to replace, employers typically provide higher compensation. In the USA, salaries range from $90,000 for a junior role through to $120,000 or higher for an experienced position. The average of $110,000 per annum for a software engineer is more than 2.5 times the average base salary across the USA. This, alongside bonuses and benefits such as medical insurance, gym membership, profit shares, and retirement plans, make a software engineering role an attractive proposition. So, what should you expect from a software engineering role? Dress codes are unlikely to be formal unless you're in a customer-facing situation. Hours are often flexible, sometimes around core hours set in the middle of the day. You may occasionally be required to attend meetings or calls which can dictate a physical or online presence at a particular time of the day. And the number of hours are likely to increase as you get near to product release dates, often without any matching increase in pay. The flexibility to work from home varies across employers, but there is no technological reasons why this cannot be done. In fact, some software teams are spread across the globe, working across all hours of the day. Software engineer employers include almost any type of business that you can imagine, from large technology companies such as Facebook, Amazon, Apple, Netflix, and Google, also known as FAANG, to medium-sized software companies that develop specific software and solutions to small software houses and startups. And almost all large non-technology companies, like banks, retailers, and pharmaceuticals, need software engineers for their own internal or external systems. And lastly, most employers will encourage continual learning, whether that be expanding your technical skills or enhancing your soft skills. They're usually keen to invest in keeping your skills up to date so that you can develop the best software solutions for them. Now, in the software engineering world, regardless of your job title, there are different employment options to suit your lifestyle and situation. Employed roles in a company or organization provide stability and a regular income. These can range from an apprenticeship or internship to a part-time role through to a full-time role. In software engineering, more so than a typical job, there is a huge independent contracting market and opportunities in the gig economy. These can range from simple website development to super specialized skills, languages, stacks, and products. In this type of employment, you can provide contract or consultancy services to organizations on a time-based or project-based model, or you can work on a freelance basis, taking on short-term contracts to work on projects that interest you. And many software engineers also code for free as volunteers, contributing to open source projects. This can help you gain experience, enhance your skills, improve your employment opportunities, and enhance your technical eminence. It also makes you feel good by doing something for a cause or community or social initiative that's important to you. In this video, you learned that the high demand for software engineers is due to increasing needs for software, increasing complexity of applications, and a continuing growth of technology. The outlook for software engineers is promising. The role of a software engineer can be flexible and satisfying, and that employment options for software engineers are flexible and varied from full-time employment through to voluntary activities. Welcome to Career Paths in Software Engineering. After watching this video, you will be able to describe typical career paths for a software engineer and identify the likely roles within career paths. A career path in software engineering opens up as you gain experience and attain new skills. Often it heads in one of two directions, technical or management. If you thrive on working with code and solving problems, then the technical path enables you to continue working closely with technology as your career progresses. Or if you exhibit strong leadership qualities alongside the soft skills of a good software engineer, you might progress onto managing a team of software engineers and the work that they do. So let's take a look at a common career path for a software engineer progressing on the technical or managerial path. Remember that different organizations will use different job titles, but the roles will be similar across the board. You're likely to start out in an entry-level position as a junior software engineer or associate software engineer. At this level, you'll be developing small chunks of software to meet agreed client specifications. You'll be assigned a team leader or mentor who will guide you along the way and provide support when you need it. During this phase of your career, you'll be on a steep learning curve, gaining new skills and experience with every block of code that you write. You could then move on to a software engineer position. In this role, you'll be expected to be more independent and be able to break larger tasks down into smaller, achievable subtasks. You may be learning new programming languages and demonstrating an understanding of the software development lifecycle. At this stage, you might be asked to mentor a junior software engineer or take responsibility for a larger part of a project. The next stage of your career could be a senior software engineer position. In this role, you're likely to have involvement across the whole of a project and with an entire code base. You may be asked to mentor software engineers and to conduct code reviews across the team. And from the experience you've gained in earlier roles, you'll be expected to be able to solve a wide range of problems in an efficient way. If you choose to follow the technical path, then your next role might be as a staff software engineer. In this role, you'll work as part of the technical team, developing, maintaining, and extending software. You'll be responsible for ensuring that the software meets customer and user expectations, and that it uses resources efficiently. If you decide to follow a managerial career path, you could become a technical lead. In this role, you'll manage the team of developers and engineers developing the software in your organization. You could be responsible for the entire development lifecycle and report to the project stakeholders. Continuing along the technical path, you might progress to be a principal engineer or technical architect. At this stage, you'll be responsible for the architecture and design of a software solution, as well as the development of it. You'll be expected to create processes and procedures for your team and provide technical direction. On the managerial path, you could become an engineering manager. In this role, you'll ensure that the entire team is appropriately supported and encouraged to progress in their careers. Becoming a director of engineering could be the next stage in the progression of your career. It is a strategic and technical role. On the strategic side, you'll determine priorities for the projects within the company, identify hiring needs, and define long-term goals. On the technical side of the role, you'll be involved in defining new projects, specifying requirements, and overseeing the project. The lead of an organization's technology arm is likely to be the Chief Technology Officer, or CTO. In this role, you oversee all of the research and development in the company. You'll also monitor the company's systems and infrastructure to ensure that it meets your needs and budget. Even at this level, you'll continue learning. As technology evolves and new products appear on the market, you'll be responsible for deciding which ones meet your business needs and could give your organization a competitive advantage. Of course, not everyone who starts out as a junior software engineer follows these traditional software engineering paths, but you'll find that the skills you gain will benefit you in a wide variety of other roles. If after working on client projects for a while, you decide that you prefer interacting with the clients to writing code, you could transition into a technical sales or customer support role. If you enjoy coding but find working with numbers and data is more appealing, you could transition into a data engineer or data scientist role. And if you find that the data side of your new role is your passion, you could move on to become a database administrator or database developer. And if you enjoy finding and fixing bugs, you might transition to a software tester role. IT is a vast field with an abundance of opportunities across many skill sets. So starting your career in software engineering is a great choice, even if you use it as a stepping stone to move to other technical or leadership roles in the future. In this video, you learned that a career in software engineering is likely to follow a technical or managerial path. At each stage on that path, you will take on more responsibility and a wider range of tasks. And starting out as a software engineer enables you to take on an array of other options at any stage in your career. Welcome to Software Engineering Job Titles. After watching this video, you will be able to list commonly used job titles for software engineers and identify the primary duties of and skills needed for these roles. Job titles such as software engineer and software developer are very broad and can be used to describe a spectrum of roles. As well as these titles, you may come across other titles related to specific subdomains in software engineering. While individual organizations might use company-specific job titles, you'll find that most fit into one of the more generic titles. Types of software engineer roles include front-end engineer, back-end engineer, full-stack engineer, DevOps engineer, software quality assurance engineer, software integration engineer, software security engineer, mobile app developer, and games developer. Front-end engineers focus on developing the user interface, or UI, of a software solution. They're also sometimes referred to as UI developers or web developers. In this type of role, you're responsible for the visual design of the software, including the layout of UI elements and the overall aesthetics of the application or website. It's important for a front-end developer to understand how users interact with software and the principles of user experience design. You'll also need to understand how objects and code run differently on different operating systems, devices, and browsers to ensure that your solution works on the user's chosen system. Key skills of a front-end engineer include web development languages and UX and UI frameworks. Back-end engineers focus on the business logic of a software solution. In this type of role, you're responsible for the core logic of the software, implementing functionality to perform tasks such as accessing data and databases, logging information, and caching systems by using application programming interfaces or APIs. You'll also be responsible for ensuring the scalability and performance of the solution. Key skills of a back-end engineer include programming languages, application frameworks, web servers, app servers, and load balancers, databases, and deployment and containerization tools and technologies. Full-stack engineers work across the whole software solution. In this type of role, you're able to create both the user interface and the back-end functionality of an application or website using the skills of both front-end and back-end engineers. Key skills of a full-stack engineer include web development languages, programming languages, UX, UI, and back-end frameworks, web and application servers, databases, APIs and web services, and deployment and containerization tools. DevOps, or Development and Operations, aims to deliver the software in an agile manner by combining software development and IT operations. DevOps engineers apply agile processes and methodologies to streamline their product development, improvement, and maintenance, as well as transcend the boundaries of the traditionally distinct development and operations teams. In a DevOps role, you need familiarity with both front-end and back-end technologies. The skills, technologies, and products that a DevOps engineer is likely to use include source code management tools, programming languages and frameworks, scripts, and deployment, containerization, and monitoring tools. And depending on the actual job posting, you might use alternative products and services, but they will be of a similar nature to those shown here. Software quality assurance engineers, also referred to as software QA engineers or software test engineers, test, review, assess, and write software to validate the quality of an application. In a QA role, you'll develop automated tests, tools, and procedures to test the functionality of software solutions. You'll use bug tracking software to log any errors you discover and report them to the software development team. The key skills for software QA engineers include programming languages, shell scripting, bug tracking and issue management tools, testing automation tools, and specific software stacks depending on how the application is deployed. Software integration engineers write code to integrate software into hardware products, enabling smart devices and the Internet of Things products. In this role, you'll use programming languages and frameworks to program hardware, such as consumer devices, home security systems, electronics, and other interfaces. The key skills for a software integration engineer include programming languages and proprietary technologies, frameworks, and toolkits. Software security engineers, sometimes referred to as white hat or ethical hackers, work to find security flaws and vulnerabilities in software. As a security engineer, you'll create systems, methods, and procedures to test software solutions and exploit their security weaknesses so that they can be fixed before the solution ships. The key skills for a security engineer include programming languages, reverse engineering, shell scripting, tools for vulnerability and penetration testing, and network security and encryption tools. Mobile app developers design, develop, and implement software solutions for mobile devices, such as smartphones and tablets. You'll use web skills to create front-end apps, as well as learn the various different platforms to write the back-end code interacting with the specific type of device. The key skills for a mobile app developer include mobile operating systems, web development languages, and programming languages, as well as web services and technologies. And games engineers write gaming software for a wide variety of devices, from PCs to smartphones to web browsers to game consoles. As a games developer, you'll work alongside graphic artists, sound technicians, and game designers to create the code used in games. In this video, you learned that there are many different job titles under the umbrella term of software engineering, each of which has specific duties and responsibilities and requires a specific set of skills. Welcome to Insider's Viewpoints, Career Pathways, and Continuing Education in Software Engineering. In this video, we will hear from experts discussing how they became software engineers, their education, and their background.
So I have a non-traditional path into software engineering. My bachelor's degree is in social work, and I worked as a social worker for some time. I was introduced to coding via social media. Randomly on social media, I was scrolling in December 2018, and afterwards I kind of fell down the rabbit hole of learning how to program, and I decided to go to a 10-month-long, very intense coding bootcamp to make the switch into software engineering. And so one thing I have learned over the past three and a half years is that your career doesn't have to be linear, and your career doesn't have to look like anyone else's.
So I just picked computer science. I love math. That's the only thing that I think really drew me to computer science was, if you love math, apparently you'll love computer science too. So I think some of the most successful engineers that worked for me or I've worked with come from backgrounds, not even sort of like mine either, people with non-technical backgrounds who picked up coding on the side. There's so many folks who come from or English majors or philosophy majors or bio, whatever it is, because I think there's this, you can learn all these skills and become a really strong engineer without having gone to a 4-year college or more for computer science specifically or another engineering role.
In college, I ended up taking applied math. I did applied math as my major. I always wanted to work on things that had a practical application, which is why I went into applied mathematics rather than pure mathematics anyway. Yeah, so I did that research program, and as part of that program, we were writing simulations using MATLAB, actually. That was a fun time. So we were writing simulations using MATLAB, and I realized I enjoyed that part more than I enjoyed the mathematical research part of it. And that's kind of what kicked it all off. It's like, oh, computers are a lot of fun. So I ended up graduating college with an applied math major, a computer science minor, and then I've been taking computer science jobs ever since then.
So I received a Bachelor of Fine Arts, actually, so not anything tech related. And I worked in education for a few years. I ended up as an art teacher, and it was during that time that I decided that I wanted to switch paths because I wanted a little bit more freedom with my job, more flexible schedule. I wanted the opportunity to work remotely. So I decided to take a class to see if I would like it at a community college near my house. And I really, really loved that class. And at the same time, kind of just watch videos on Udemy and YouTube and teach myself some things that I wasn't learning in class. I took 32 credits at the community college level. And then after that, I did apply to graduate school. While in grad school, I received an internship offer at my current company. I did a summer internship, and directly following that, I started full-time.
Next, we will hear from these experts regarding how they maintain their skills and keep up with the continuous technology evolution.
I follow people on Twitter who talk about emerging technologies and new technologies. I also subscribe to this newsletter called TLDR, and they pretty much just surmise everything that's going on in the tech industry. That's what I like to do to keep up to date. And I also take various courses on things that are interesting to me.
Yeah, and I think just carving out time to learn, whether it's within your, often companies will give people some amount of time to for personal development and growth, which can mean taking courses to learn new languages or frameworks.
I've found that I learn best if I have a project that makes me need to learn the thing. So I started with Googling. Like, honestly, Reddit threads frequently are the best places to find out about like what are the popular and new technologies these days. If you just search on Google for like best website framework, Reddit 2022, you'll find numerous posts of people debating the pros and cons of different types of frameworks. And then actually another very important thing is debug it. Attach a debugger, put in print statements, do everything you can to be able to inspect the flow of the code that is getting run. Knowing how to debug is about almost equally an important skill as knowing how to write the code.
The way that I kind of keep on top of everything is reading documentation. I have really great coworkers who are always also in the know of like when things are updated, when languages are updated, when to use new technologies. So they help me out a lot there. And we also get Udemy for free, like Udemy Business for free for all employees, which is a really great way to learn new things and also stay on top of new technologies that come out.
Welcome to Software Engineering Code of Ethics. After watching this video, you will be able to state each of the 8 principles in the Software Engineering Code of Ethics and explain each of the 8 principles in the Software Engineering Code of Ethics. The Joint Task Force on Software Engineering Ethics and Professional Practices developed a code of ethics outlining their goals and standards for software engineers engaged in the design and creation of software. The task force was formed by the Institute of Electrical and Electronics Engineers Computer Society, or IEEE-CS, and the Association for Computer Machinery, or ACM, in order to recognize the prominence of computing in global commerce, government, and society. This IEEE-CS-ACM Joint Task Force championed the need to hold software engineers accountable so that the present and future status of the field as a beneficial and respected profession is maintained. The Code of Ethics consists of 8 principles that pertain to the specification analysis, design, development, testing, and maintenance of software, and are dedicated to serving the public interest. These principles are intended for anyone who is in or related to the profession and includes engineers, mentors, instructors, managers, students, and policymakers. Here we will summarize each principle. However, the full text of each principle and its additional clarifying clauses can be found on the IEEE-CS and ACM websites. The principles in the Software Engineering Code of Ethics focus on the following topics: public, client or employer, product, judgment, management, profession, colleagues, and self. The public principle comes first because it is expected that software engineers should act primarily in accordance to positively affect the public good. This includes accepting responsibility for their work with regard to safety, fairness, accessibility, and integrity. Next, software engineers should act in the best interests of both their clients and their employers. They should act honestly and be forthright when it comes to unethical actions such as plagiarism or illegal activities. They should seek consent where necessary and appropriate and honor confidentiality. The third principle relates to the product under production. Software engineers should seek quality while keeping in mind cost and timelines. Now, this next principle outlines how software engineers act with integrity and independence in their professional judgment. They are expected to maintain objectivity and honesty when working with the software and relevant documents they are involved with. Software engineers should not engage in any inappropriate financial activities, such as bribery and double billing, nor may they accept duties that create a conflict of interest. Software engineering managers and leaders should also behave in a manner consistent with these principles where it applies to them and those they manage. They should work to minimize risk and employ security procedures. And managers and leaders should also work to ensure realistic expectations of their staff, provide just compensation, and procure intellectual property rights whenever appropriate. The profession principle describes the duty of software engineers to protect the reputation of the profession by acting with integrity and not elevating themselves at the expense of others. Software engineers should let managers, employers, and clients know they intend to act in compliance with this code of ethics and express concern over violations of the code. Similar to the profession principle, software engineers shall treat their colleagues with respect and fairness. They should encourage their peers to comply with this code of ethics and not take credit for the work of others. The final principle, focused on the software engineer themselves, reminds software engineers about the importance of lifelong learning and professional development. They should endeavor to create quality software and strive to conduct themselves in a professional manner. It should be noted that this code of ethics is not a replacement for conscientious decision-making and common sense, but it can be used as a supplemental guide. Knowing when and where to apply these principles will always be up to the discretion and wisdom of the individual. In this video, you learned that the Code of Ethics serves the public interest to hold software engineers accountable in the analysis, design, development, testing, and maintenance of software. And the 8 principles in the Code of Ethics are public, client or employer, product, judgment, management, profession, colleagues, and self.
Welcome to this course on cloud computing, designed to give you the foundational skills you need to be a cloud practitioner. Today, the cloud represents a huge market that continues to grow at an unprecedented scale. Enormous computational power, once considered a prerogative of large enterprises, is now available at the fingertips of even the smallest of businesses and individual developers, thanks to the cloud. Moreover, the cloud makes all this computational power highly affordable with pay-as-you-go economics. If you look at some of the key emerging technologies of our times, such as artificial intelligence, the Internet of Things, blockchain, and analytics, all of these technologies work with massive amounts of data and need huge storage space and computational power in order to work, making cloud possibly the only viable platform for these technologies. This course is designed for everyone. It doesn't matter if you have a background in cloud technologies. Whether you're an IT person looking to upskill or explore this domain, a fresh graduate looking to make a career in cloud technologies, or an IT decision maker, this course will equip you with what you need to get started. This course will introduce you to the core concepts of cloud computing in the following modules. Module 1, Overview of Cloud Computing. Module 2, Cloud Computing Models. Module 3, Components of Cloud Computing. Module 4, Emergent Trends and Practices. And Module 5, Cloud Security, Monitoring, Case Studies, Jobs, and Final Assessment. In this first module, you will learn about the essential characteristics, the history and evolution, key considerations, and service providers of cloud computing. You will also explore some case studies and emerging technologies like Internet of Things, artificial intelligence, and blockchain associated with cloud computing. The second module will give an overview of the 3 cloud service modules: Infrastructure as a Service, Platform as a Service, and Software as a Service. In addition, you will learn about the cloud development models: public, community, private, and hybrid. In the third module, you will learn about the components of the cloud infrastructure, like virtual machines, bare metal servers, and containers. You will also get an insight on the types of cloud storage, such as file, block, and object. In addition, you will learn about content delivery networks. In the fourth module, you will discuss the emerging trends in cloud computing, such as hybrid cloud computing microservices and serverless computing. You will also explore cloud-native applications, DevOps on the cloud, and application modernization. In the fifth module, you will learn about cloud security and how to manage access and identity. In addition, you will learn about cloud encryption and monitoring. The module will also cover some case studies in different industry verticals. You will get an insight on the job opportunities available in cloud computing. In the final module, you can test your knowledge of what you learned in the course with a final quiz. There's also an honors project where you can apply your skills and knowledge in this hands-on lab. You will deploy an app on the cloud by building a Docker container image, uploading it to IBM Cloud Container Registry, and deploying it using a serverless technology called IBM Code Engine. No programming knowledge is required. So, there is a lot to cover here. To get the most from this course, complete viewing each video, complete all hands-on labs, and check your learning with each quiz. We're very happy to have you with us as you start your cloud computing journey. If you have any trouble with any of the course material, please don't hesitate to contact us in the discussion forum. Good luck, and let's get started. Why would you choose cloud computing over traditional hosting on a local server? Cloud computing offers businesses more flexibility and scalability than hosting on a local server. It is a business model or service that combines technology like virtualization with a few of the latest trends. And if you require extra bandwidth, a cloud-based service can address that need promptly rather than waiting for a complex and costly update to your IT infrastructure. Users can customize their applications using cloud services from anywhere if they have an internet connection. In addition, cloud computing enables efficient marketing of applications, regardless of maintenance and cost. To get a common understanding of cloud computing, let's start with the U.S. National Institute of Standards and Technology, NIST's, definition of cloud computing. NIST defines cloud computing as a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. Examples of computing resources include networks, servers, storage, applications, and services. This cloud model is composed of 5 essential characteristics, 4 deployment models, and 3 service models. Let's start with understanding the 5 essential characteristics of the cloud, which include on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. On-demand self-service, the first characteristic, means you can access cloud resources whenever required. For example, a 24-hour ATM or a vending machine at the office or store. Services are always available on all days of the year, regardless of whether a particular day is a national holiday, weekend, festival day, and so on. There are no exceptions, other than when services are unable due to an outage or security breach. Broad network access means that cloud computing resources can be accessed through the network. Public cloud services could generally be accessible from anywhere and on any device with internet connectivity and browser capabilities. Today, we are open to more than just desktops or laptops for accessing cloud services. There are many other devices, such as tablets, iPads, smartphones, e-readers, smart wearables, and so on. Also, to emphasize again, internet access is mandatory for accessing public cloud services. However, in an on-premises private cloud, an intranet can only suffice for accessing cloud services, provided the organization does not need to reach out to the entire world public. With resource pooling, consumers save on costs when using a shared model. This model provides cloud providers economies of scale, which they can pass on to their customers, making the cloud cost-efficient. Computing resources are pooled to serve multiple consumers using a multi-tenant model. Cloud resources are dynamically assigned and reassigned according to demand, without customers needing to concern themselves with the physical location of these resources. Rapid elasticity implies that you can increase or decrease resources as per your demand because of the elastic property of the cloud. Resources can be scaled up or down vertically scaling or scaled out as in horizontal scaling. An ideal example would be to add resources when there is an increase in demand due to the increase in the number of users while shopping online, like during a holiday sale, and the converse after the sales period. Measured service means that you only pay for what you use or reserve as you go. Measured services, however, do not apply to certain cloud services, such as general email services like Gmail, Hotmail, Yahoo, social media sites like Facebook, Twitter, WhatsApp, and cloud service evaluation on a trial basis like AWS, Azure, and GCP, which are provided for free due to the discretion policies extended by the respective service providers. Measured service is also termed as a utility model of billing, where you are charged after the usage and at the end of the predefined period, like monthly electric charges. We will discuss the deployment and service models later in this module. Welcome to Overview of Cloud Computing, Definition and Essential Characteristics Expert Viewpoints. In this video, we will listen to several cloud-native and application development professionals discuss the definition of cloud computing and cloud computing's unique attributes. How do you define cloud computing, and what are some of its attributes?
As a cloud-native developer, cloud computing basically boils down to two things for me. First, it is on-demand, and second, it is self-serving. So what that means is, as a developer, I should be able to log into a portal and get the exact amount of services that I need. I'm not waiting around for procurement or infrastructure services to assign something or provision something for me. And this is true for the whole stack, ranging from infrastructure to platform to solution as a service.
To me, cloud computing is the ability to deploy code or infrastructure anywhere in the world and at scale. Some of the key characteristics include distribution, high availability, resiliency, and scalability.
Cloud computing refers to the delivery of computing services that can include servers, database, networking, analytics, etc. over internet or cloud. Key attributes of cloud computing are flexible cost, global scale, reduced time to deploy resources, higher productivity and performance, and higher reliability and security.
To me, cloud computing means unlimited compute database, machine learning capacity, and the ability to work with that in an instant. Unlike with data centers, where you need to order all those things, set it up, and manage the availability of it yourself. With cloud computing, the cloud provider manages the physical security of the servers for you, and all you do is manage the stuff on it.
I would summarize cloud computing as a suite of API-driven services to manage all aspects of compute networking resources for enterprise computing. You could think of it as virtualized resources defined by software. Some other key characteristics are the resources are elastic and can grow or shrink with demand. Think of e-commerce on high demand holidays. Also, the computing costs are dynamic. So instead of capital expenditures for hardware, you have operating expenses for cloud resources.
To me, cloud computing is not a yes or no. It's really a scale. And everything uses cloud computing, or almost everything does nowadays. The idea is that you can dip your toes in, just use cloud computing for a little bit, like authentication, use some social login so people can log in with their Facebook or their Google login. Or you can go all the way in and, have your entire project hosted on a cloud-based infrastructure. The point is that both of those leverage cloud technologies. Really, whenever you reach into that void of the cloud and take compute power or something else, storage, it doesn't matter, that is using a cloud technology. And I think that's really important to understand. Almost everything is the cloud nowadays.
There's a joke that cloud computing is just using someone else's computer over the internet. That's only very narrowly true. What cloud computing actually gives you is a degree of availability, consistency, and scalability that you very likely would not be able to achieve running your own machines. At its best, cloud computing allows you to abstract away the management of the things you probably don't care about and focus on the things that you do care about.
With high performance compute in the cloud, you can have extremely fast clusters of computers at your fingertips and only pay for them when you need them. And thanks to the cloud, smaller companies are able to set up high performance compute clusters and innovate rapidly.
Welcome to the history and evolution of cloud computing. Cloud computing is an evolution of technology over time. The concept of cloud computing dates to the 1950s, when large-scale mainframes with high-volume processing power became available. The practice of time-sharing, or resource pooling, evolved to make efficient use of the computing power of mainframes. Using dumb terminals, whose sole purpose was facilitating access to the mainframes, multiple users could access the same data storage layer and CPU power from any terminal. In the 1970s, with the release of an operating system called Virtual Machine, VM, it became possible for mainframes to have multiple virtual systems, or virtual machines, on a single physical node. The virtual machine operating system evolved from the 1950s application of shared access of a mainframe by allowing multiple distinct computing environments to exist on the same physical hardware. Each virtual machine hosted guest operating systems that behaved like they had their own memory, CPU, and hard drives, even though these were shared resources. Virtualization thus became a technological driver and a massive catalyst for some of the most significant evolutions in communications and computing. Even 20 years ago, physical hardware was quite expensive. With the internet becoming more accessible and the need to make hardware costs more viable, servers were virtualized into shared hosting environments, virtual private servers, and virtual dedicated servers, using the same functionality the virtual machine operating system provided. So, for example, if a company needed an X number of physical systems to run their applications, they could split one physical node into multiple virtual systems. A hypervisor is a small software layer that enables multiple operating systems to run alongside each other, sharing the same physical computing resources. A hypervisor also separates the virtual machines logically, assigning each slice of the underlying computing power, memory, and storage, preventing the virtual machines from interfering with each other. So, if, for example, one operating system suffers a crash or a security compromise, the others can keep working. As technologies and hypervisors improved and could share and deliver resources reliably, some companies decided to make the cloud's benefits accessible to users. These users did not have an abundance of physical servers to create their cloud computing infrastructure. Since the servers were already online, spinning up a new instance was instantaneous. Users could now order cloud resources from a larger pool of available resources and pay for them on a per-use basis, also known as pay-as-you-go. This pay-as-you-go, or utility computing model, became one of the key drivers behind cloud computing's launching. The pay-per-use model allowed companies and even individual developers to pay for the computing resources as and when they use them, just like units of electricity. This allowed them to switch to a more cash flow-friendly OpEx model from a CapEx model. This model appealed to all sizes of companies, those who had little or no hardware, and even those that had lots of hardware, because now, instead of making substantial capital expenditures in hardware, they could pay for compute resources as and when needed. It also allowed them to scale their workloads during usage peaks and scale down when usage subsided. And this gave rise to modern-day cloud computing. Every organization's transformation journey is unique, and therefore every organization's cloud adoption strategy is also unique to them. Agility, flexibility, and competitiveness are key drivers for moving to the cloud, provided it is done without creating business disruption or issues related to security, compliance, and performance. Let's look at some key considerations that organizations can use as a guide while working through their cloud strategy. The first consideration is infrastructure and workloads. The cost of building and operating data centers can become astronomical. On the other hand, Low initial costs and pay-as-you-go attributes of cloud computing can add up to significant cost savings. Also, a point to consider is that not all workloads may be ready for the cloud as is. The second consideration is around software as a service and development platforms. Organizations need to consider if paying for application access is a more viable option than purchasing off-the-shelf software and subsequently investing in upgrades. Organizations need to consider speed and productivity, what it means for them to get a new application up and running in X hours on the cloud versus a couple of weeks, even months on traditional platforms, and the person-hour cost efficiencies they gain from using cloud dashboards, real-time statistics, and active analytics. Let's look at some of the benefits of cloud adoption, categorized broadly into flexibility, efficiency, and strategic value. Cloud gives us flexibility. Users can scale back or scale up services to fit their needs, customize applications, and access cloud services from anywhere with an internet connection. Cloud infrastructure scales on demand to support fluctuating workloads. Organizations can determine their level of control with as-a-service options. Users can select from a menu of pre-built tools and features to build a solution that fits their specific needs. And options like encryption and API keys help keep data secure. Cloud also brings great efficiency. Enterprise users can get applications to market quickly without worrying about underlying infrastructure costs or its maintenance. Cloud-based applications and data are accessible from virtually any internet-connected device. Hardware failures do not result in data loss because of backups maintained on the network. Cloud computing uses remote resources, saving organizations the cost of servers and other equipment and paying on use basis. Cloud services give enterprises a competitive advantage by providing the most innovative technologies available while managing the underlying infrastructure, thus enabling organizations to focus on their priorities. While cloud brings great opportunity, it also introduces challenges for business leaders and IT departments. Some of these perceived risks include data security associated with loss or unavailability of data causing business disruption, governance and sovereignty issues, legal, regulatory, and compliance issues, lack of standardization in how the constantly evolving technologies integrate and interoperate, choosing the right deployment and service models to serve specific needs, partnering with the right cloud service providers, concerns related to business continuity and disaster recovery. Organizations can no longer think of cloud adoption as something that is to be looked at in the future. With the right cloud adoption strategies, technologies, services, and service providers, these risks can be mitigated. In the next video, we're going to look at some of the key cloud service providers of our time and the services they offer. Let's look at some numbers and predictions that help us see the scale cloud is predicted to achieve in the coming years. Gartner Inc. forecasts, in the near future, worldwide public cloud spending will grow 20.7% to total $591.8 billion, scaling up from $490.3 billion in previous years. Global spending on desktop as a service will reach $3.2 billion in 2023 as companies shift away from traditional client computing solutions to subscription-based virtual desktop services. In the coming years, enterprises will spend more on public cloud services than traditional IT solutions. What is clear is that cloud is accelerating faster than predicted, adoption is high, and revenues are soaring. The question for businesses today is no longer if they need to adopt the cloud, rather what their cloud adoption strategy should be to best serve their businesses and customers. Keeping up with this technological wave and driving it forward are the cloud service providers with a wide range of services. We will now talk about some of the major cloud service providers in alphabetical order. Alibaba Cloud, while relatively new, is the largest Chinese cloud computing service provider. Alibaba Cloud provides a comprehensive suite of global cloud computing services to power not just their customers' online businesses, but also the Alibaba Group's own e-commerce ecosystem. It offers a host of products and services, such as compute, network, storage, security, monitoring and managing, communication, analytics, IoT, application development, data migration, web hosting, and more. One of the first to enter the cloud computing space, Amazon Web Services, or AWS Cloud, offers an extensive range of infrastructure and platform services to individuals, companies, and governments on a metered, pay-as-you-go basis. The Amazon Cloud provides a wide range of products, services, and solutions ranging from compute, DevOps, data, analytics, IoT, machine learning, networking, content delivery, robotics, serverless computing, and much more. Google Cloud Platform, or GCP, is a suite of cloud computing services, providing infrastructure, platform, and serverless computing environments. Google also uses GCP internally for their end-user products, such as Google Search and YouTube. Google Cloud includes G Suite with products for communication, productivity, collaboration, storage, and more. The Google App Engine is a platform for developing and hosting web applications in Google-managed data centers, automatically allocating and deallocating resources to handle demand. IBM Cloud is a full-stack cloud platform that spans public, private, and hybrid environments with products and services covering compute, network, storage, management, security, DevOps, and databases. Some of their prominent offerings include their bare metal servers, VMware, Cloud Paks for application modernization, virtual private cloud, and the suite of emerging technologies such as AI, IoT, blockchain, data, and analytics. With the acquisition of Red Hat, IBM is also positioning itself as the leading hybrid cloud provider of our times. Microsoft Azure is a flexible cloud platform for building, testing, deploying, and managing applications and services through Microsoft-managed data centers. With its data centers spread out in many regions, Azure provides a global reach with local presence. It provides software, platform, and infrastructure services supporting Microsoft-specific and third-party languages, tools, and frameworks. Oracle Cloud is primarily known for SaaS and Database as a Service, also known as the Oracle Data Cloud. Oracle's SaaS offering includes wide-ranging applications such as ERP, SCM, HCM, marketing, sales, and CX running in the cloud. And the Oracle Data Cloud provides one of the largest cloud-based data management platforms, helping customers personalize their online, offline, and mobile marketing campaigns for targeted audiences. Oracle Cloud also provides some cloud infrastructure and platform services. Salesforce specializes in their software as a service offering that focuses on customer relationship management, supporting businesses to better connect with their customers, partners, and potential customers. Salesforce offers multiple cloud services such as Sales Cloud, Service Cloud, and Marketing Cloud, helping customers track analytics in real time, customer success and support, customer complaints, even listening into customers across social platforms to automatically route them to the appropriate agents for resolution. SAP is known for enterprise software and applications such as ERP, CRM, HR, and finance running in the cloud. There is also an SAP Cloud Platform for building and extending business applications with rapid innovation cycles in a secure cloud computing environment managed by SAP. In the next video, we're going to look at the business case for cloud computing.
Cloud adoption is no longer a thing of the future. From a single individual to a global multi-billion-dollar enterprise, anybody can access the computing capacity they need on the cloud. The lag time from decision to value is no longer a journey of years with high upfront capital. Cloud makes it possible for businesses to experiment, fail, and learn much faster than ever before with low-risk exposure. Businesses today have greater freedom to change course than to live with the consequences of expensive decisions taken in the past. According to an IBM Institute for Business Value study, more than 3/4 of enterprises today are using cloud computing to expand into new industries. 74% have adopted cloud to improve customer experience, and 71% Use cloud to create enhanced products and services while simultaneously downsizing legacy systems and reducing costs. To remain competitive, businesses need to be able to respond quickly to marketplace changes, use analytics to understand customer experience, and apply that understanding to adapt their products and services based on what they learn. Product life cycles have shortened and barriers to entry have become lower. Cognitively enabled workflows, applied exponential technologies such as AI, automation, IoT, and blockchain, applications that span new and legacy solutions, and open, hybrid, and secure multi-cloud infrastructures are today's enablers for growth, agility, and innovation. The power, scalability, flexibility, and pay-as-you-go economics of cloud has made it the underpinning foundation for digital transformation. The International Data Corporation, IDC, predicts that by 2025, the total amount of digital data created worldwide will rise to 163 zettabytes, where 1 zettabyte is equivalent to 1 trillion gigabytes. And 30% of this data will be real-time information. Considering the unprecedented amounts of data being produced daily and the ability to make data-driven decisions crucial to any business, cloud computing becomes essential for businesses to succeed, sustain, and compete in today's markets. A cloud strategy, more than just an IT strategy, is the core component of any business strategy today. Businesses that haven't already or are not currently integrating cloud into their business strategy run the risk of lacking the speed, agility, innovation, and decision-making capacities needed to be competitive, as also their ability to respond to digital disruption. In the next video, we'll look at some case studies that demonstrate the impact businesses have created by adopting cloud.
Welcome to Cloud Adoption Benefits and Use Cases Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss cloud adoption. According to you, what are some of the most compelling reasons for businesses to adopt cloud technologies?
One of the biggest reasons for a business to adopt cloud technologies is the sheer speed it gives you to move forward and enhance your product. For example, every industry has its own needs, and every business has its own specific needs. And a lot of these needs are already met with services and technologies available in the cloud. You can, quite frankly, stand on the shoulders of giants with cloud technologies. You don't need to create AI algorithms yourselves. You can use AI services. You don't need to worry about building a machine, connecting it to the internet. Those are already provided for you. So the best thing about the cloud is how easy and how fast it is to just get going and to get really specialized stuff going without needing that specialization yourself.
By using cloud computing, businesses pay only for services they use, which help in reducing their infrastructure and operating cost. Machines can be deployed and used within a matter of minutes. The infrastructure can be scaled elastically to meet the growing business needs. As cloud computing services run on a variety of secure data centers around the world, there is reduced network latencies for applications and greater economies of scale. Cloud computing also makes data backups and recovery services less expensive, along with providing policies for higher levels of security.
Cloud technologies allow businesses to focus entirely on their core business model and let the cloud handle other components. For example, if my business is not pertaining to databases, then I don't want to worry about managing and deploying a database. I can offload that to the cloud, and I'm guaranteed a highly available and distributed database for my business, allowing me and my engineers to focus on what actually matters for my application and my users.
With high-performance compute in the cloud, you can have extremely fast clusters of computers at your fingertips and only pay for them when you need them. And thanks to the cloud, smaller companies are able to set up high-performance compute clusters and innovate rapidly.
For me, the most compelling reason to adopt cloud technologies is that you typically only pay for what you use. That means there's a very low barrier to entry. You can typically start trying something out with an hourly billing plan and no upfront costs. Another compelling reason is to take advantage of the high level of service that the cloud can provide. So for example, I need access to databases. I want them to be highly available and fast and have regular backups, but I'm not in the business of database management. And if I have the option of getting someone else to manage that for me, I will typically take it.
And finally, time to market pressure to build new products. You know, we're seeing many or perhaps most startups using cloud platforms to build and deploy their products quickly and with less expense. One is your business requires a global footprint, and it's quite likely that your business cannot afford global data centers. So that's one very obvious one. Another one is your business requires elastic resources. Think of retail and e-commerce during high demand holidays. Think of live event ticketing, maybe HR and healthcare annual enrollment. Basically any application where demand is highly variable or spiky. Another interesting one is large-scale analytics or development of data pipelines and machine learning. On-premise physical resources are, possibly too small, too expensive, or underutilized. Another good one is cybersecurity. I think you have to assess whether your organization can really address cybersecurity at the same level as IBM or the other cloud providers.
In this video, we will look at how some of the leading businesses have transformed the way they work to provide better customer service, remove barriers to innovation, achieve enterprise scale, and accelerate growth using cloud technologies. Although the case studies we'll look at are curated from IBM Cloud, similar stories with dramatic impact to business can be found across the spectrum of companies utilizing other cloud service providers as well. Better customer service. In the highly competitive airline industry, customer experience is a major point of differentiation, and digital channels are increasingly important. To become more responsive to customer needs, American Airlines needed a new technology platform and a new approach to development that would help it deliver digital self-service tools and customer value more rapidly across its enterprise. The airline recognized the opportunity to remove the constraints of their existing customer-facing applications based on monolithic code into cloud-native-based microservices architecture on the cloud. The results? Faster development and release of new apps, improved operational reliability, productivity, and end customer response times. Cost savings by avoiding existing upgrade costs via migration to the IBM Cloud. Removing barriers to innovation. As a lean organization with a self-imposed limit on headcount, UBank excels at finding innovative ways to meet demands. Continually challenged to find more efficient ways to operate, UBank's IT team explored a platform as a service, or PaaS, cloud development model. Their need was to give more control to their developers, reduce the need for additional resources, faster speed to market, and removing barriers in going from an idea to production. UBank launched new initiatives in an IBM Cloud Platform environment, including a virtual assistant that incorporates IBM Watson technology to support the bank's online home loan application. The results? Faster time to market made possible through the Cloud Platform framework that streamlines development and empowers product teams. Foster greater innovation with cloud-based development resources that are quick, easy, and cost-effective to deploy. More efficient operations. Demand for enterprise scale. Since its inception in 2008, Bitly has journeyed from a startup that offered intelligent link shortening technology adopted by users to compress lengthy URLs for social media posts to an enterprise product. Seeking an agile, cost-effective IT infrastructure to support this transition, Bitly started planning for cloud migration. Their need was to have a cloud-based model with pay-as-you-go pricing, the ability to scale up and down, a more global presence, and the ability to geo-distribute into more POPs. And they wanted it to be low risk. Bitly migrated to an IBM cloud environment, establishing a scalable hosting platform for low-latency delivery to enterprise customers around the world. The results: 25 billion data-infused links migrated from one hosting site to cloud infrastructure with data center locations worldwide. 1 billion user interaction datasets stored and managed in a flexible, cost-effective cloud object storage environment. Transformed IT operations to scale for growth, control costs, and focus valuable resources on new product development. Accelerating growth. Financial traders demand extreme speed and availability from trading systems. Profitability depends on split-second decisions. As a leading online broker for Forex, commodities, equities, cryptocurrencies, indices, and other financial instruments, Active Trades enables investors to buy and sell on numerous financial markets. Investors need reliable access to accurate market information, combined with the ability to move rapidly to execute trades. As its client base grew, Active Trades wanted to cut latency, accelerate execution, and streamline the delivery of new functions. Active Trades migrated 3 major trading systems from on-premise infrastructure to IBM Cloud for VMware solutions, backed by data storage, networking, and security offerings on the IBM Cloud. The results: up to 3 times performance boost, helping clients seize fleeting opportunities for profit. Security-rich cloud platform with ultra-high availability protects client investments. Hours, not days, to fire up new resources for faster response to emerging requirements. In the next video, we'll look at some of the emerging technologies that are available on the cloud and the opportunities they bring to businesses. In this new era, technologies such as Internet of Things, big data, artificial intelligence, and blockchain are disrupting existing business models and industries while creating unprecedented opportunities for businesses to differentiate themselves and create value for their clients. The power, scale, dynamic nature, and economics of the cloud resources make cloud computing a key enabler for adoption and evolution of these emerging technologies. In this video, we will look at how the Internet of Things, or IoT, powered by cloud, is making a big difference for businesses today. The Internet of Things, or IoT, is a giant network of connected things and people that have changed much of how we live our daily lives, from the way we drive to how we make purchases, monitoring our personal health, and even how we get energy for our homes. Smart devices and sensors are continuously tracking and collecting data. For example, a smart building could have thousands of sensors measuring all kinds of data related to thermal, optical, structural, and environmental stimuli. An unprecedented amount of data is being generated, putting a tremendous strain on the internet. That is where the cloud comes in. By connecting the IoT device user to the cloud, be it for device registration, device identity, storing data, or accessing enterprise data. Data collected through IoT devices is stored and processed on the cloud. Since IoT devices can be in a state of motion, the cloud serves as a collection point in closest proximity, minimizing the latency in reporting up the data points and providing a response back to the IoT application. So, from IoT platforms running entirely on the cloud, to the interfaces used by customers to interact with these devices, to the back-end analytics platforms, cloud computing supports and enables IoT. Cloud service providers also offer specialized IoT services designed to help speed up the development of IoT solutions. Let's look at a case study that demonstrates the use of the IoT on the cloud to combat the poaching of endangered rhinos at Welgevanden by making poaching predictable.
Rhino has become one of the key species that is becoming endangered due to poaching throughout Africa, but now especially in South Africa. Up until now, poachers have been increasing in numbers and they've become more militarized with weapons, and so of course we've had to do the same. This is not sustainable. The only way to do this better is to bring in technology and things that they do not have.
This endangered species is getting help from some unexpected friends. The zebra and antelope. They're wearing IoT sensors connected to the IBM cloud. When poachers enter the area, the animals run for it, which alerts rangers who can track their motions and help stop them before any harm is done. It's a smart way to help increase the rhino population and turn the poachers into the endangered species.
In the next video, we're going to look at how artificial intelligence on the cloud is impacting businesses. Making sense of the endless streams of data is where artificial intelligence, or AI, comes in. Many of the applications where we apply AI today simply wouldn't have been possible without the scalable, on-demand computing offered by the cloud. There is a three-way relationship between AI, IoT, and cloud. Just as AI consumes the data produced by IoT devices, the IoT device's behavior can be dictated based on responses from AI. For example, smart assistants. A common type of IoT device continues to learn about the user's preferences as usage grows, such as songs they like, their home temperature settings, preferred meal times, and over time, they anticipate their actions based on the user's past history. So what we see is a symbiotic relationship between IoT, AI, and cloud. IoT delivers the data, AI powers the insights, and both these emerging technologies leverage cloud scalability and processing power to provide value to individuals and businesses alike. Let's look at how the United States Tennis Association, USTA, is using AI on the cloud to deliver unique digital experiences to millions of fans around the world.
For 2 weeks at the end of every summer, tennis fans around the world turn their eyes to New York City and the US Open.
Hundreds of thousands on site and millions more online. But where you see tennis, IBM sees data. The scores and statistics, the sights, the sounds. IBM integrates and analyzes the data flowing from the court and delivers unique digital experiences to more than 10 million tennis fans around the world. And we do it all in the IBM Cloud.
The IBM Cloud is the digital foundation of the US Open. It scales rapidly to meet a 5,000% increase in web traffic, and it delivers a consistent experience to our fans all around the globe. And with Watson on the IBM Cloud, we can engage fans in unique ways, year after year.
Slam Tracker analyzes more than 26 million historical data points. It gives fans deep insight into featured matches, and it can see the momentum of a match shifting in real time.
AI Highlights uses Watson to process thousands of hours of US Open video. It can hear the cheers of the crowd. It can see a player celebrating, and it knows what makes a great tennis highlight.
And this year, we're putting the power of AI Highlights into the hands of US players and coaches. Watson is analyzing match video so coaches can quickly find the footage they need to guide the development of their players. And if you need to know where to park, find a good burger, or grab the latest US Open gear, you can find the answers with the guest information feature in the US Open app and mobile web using Watson.
We work with IBM because they keep us on the cutting edge of the fan experience. They help us to adopt the latest technology, like cloud and AI. And they bring data to life in a way that's accessible and engaging for our fans.
In the next video, we're going to look at how blockchain and analytics on the cloud are impacting businesses. Blockchain is a secure, distributed, open technology that can help speed up processes, lower costs, and build transparency and traceability in transactional applications. It is an immutable network allowing members to view only those transactions that are relevant to them. The more open, diverse, and distributed the network, the stronger the trust and transparency in the data and transactions. 85% of businesses today rely on multiple clouds to meet their IT needs, with more than 70% using more than 3. These businesses need to be able to move applications and data across multiple clouds easily and securely, leading to the emerging demand to build and manage business applications such as blockchain for the multi-cloud environment. Blockchain and AI, much like IoT and AI, powered by the cloud, also have a three-way relationship, where blockchain technology provides the trusted, decentralized source of truth. AI powers the analytics and decision-making from the data collected, and cloud provides globally distributed, scalable, and cost-efficient computing resources to support both the unprecedented amounts of data being collected and the processing power required to draw insights from this data. Blockchain serves to make AI more understandable by recording the data and variables that go into a decision made in an AI algorithm, leading to greater trust and transparency in the conclusions and decisions made by these algorithms. Let's look at how blockchain on the cloud is helping farmers reduce waste at times of recall by building traceability and transparency in the food supply chain.
For farmers here, this is our life's work. 60% of the nation's lettuce is grown right here in Salinas. When it comes down to how plants are looked at, I really relate back to how humans are raised and nurtured. I want to make sure that everything is safe before it leaves the ranch. But when a recall happens, perfectly good food goes to waste. You have to take all product off your shelf, no matter what age, no matter where it came from. And it takes resources to grow those things. Then now we're actually eating into our future food supply. But we've got a way around that. Blockchain technology on the IBM cloud, we're able to track our product within seconds, giving the consumers instant access where the product came from in case there's any recall. So we don't have to take all the food off the shelves. Having that instant access allows you to reduce the waste. There's a lot of starving people in this world. A nice wedge. I want to be the generation that fixes that. Is that Daddy's lettuce? Yeah, it is.
Analytics technologies on the cloud leverage the flexibility, scalability, and computing resources available on the cloud. From tracking trends on social media to predict future events, to analyzing data to build machine learning models that can be deployed in cognitive applications, cloud provides the integrated environment that is required to leverage data for continuous improvement and accelerated business growth. Let's look at how Kone has invested in cloud and IoT technologies to power a data analytics and predictive maintenance solution for city infrastructure used by more than 1 billion people daily.
At Kone, we manufacture elevators, escalators, auto walks, and doors. All of these devices are streams of data that we are collecting. In order to process those streams, we need a scalable way of handle the amount of data that is coming in. And that's where Cloud Function fits in perfectly. We handle that data with event-driven architecture. We use functions to persist that data and to generate further events on that data that are then utilized and consumed by applications and our customers and users. In our analytics platform, we analyze the set of data and we generate value, predictive in a sense that we can predict the failure rate to a certain percentage that is about to happen in the future for our equipment. And this allows us to perform predictive maintenance. And this is kind of the whole concept that we have behind our 24/7 connected services, which is a promise to our customers that the equipment is connected to the cloud and we are monitoring it. And that's where we generate the real value for our customers from a maintenance perspective. At the moment, we use almost all aspects of the IBM cloud. We use storage from the cloud, we use cloud functions, we use messaging services, we use IoT services. So a number of services are already in use in platform, and that use will only grow as our digital footprint in the industry grows.
In our introductory cloud video, we briefly talked about the 3 service models available on the cloud: infrastructure as a service, platform as a service, and software as a service. Before we dive into the details of each of these service models in the subsequent videos, let's get started with a quick overview of these models.
Hi, I'm Tessa Rhodes, and I'm a designer on IBM Cloud. So let's start with the foundation here with IaaS. IaaS is a set of compute, networking, and storage resources that have been virtualized by a vendor so that a user can access and configure them any way they want. In design, we have a concept of talking about users called personas, and the persona for IaaS is a system admin or an IT admin. Let's jump up to the top with software as a service. That's the easy one. Software as a service is just software that you don't have to install on your machine and you don't have to manually update. And so the user for software as a service could be anyone. In fact, if you're watching this on YouTube right now, then you're a user of software as a service. It's usually charged on a subscription model rather than a one-time license fee. Then that brings us to platform as a service. PaaS takes advantage of all the virtualized resources from IaaS and then just abstracts them away so the user doesn't have to worry about managing any of those virtualized resources. The user for PaaS is not a system admin, usually. It's usually a dev. In IBM, we call this dev Jane. That's the name of our persona. And so this whole metaphor, the pyramid metaphor, is meant to indicate that as you move down, you're increasing complexity in terms of your knowledge and management of infrastructure resources, and you're increasing the ease of use. Another metaphor I use when I'm talking to the designers on my team about PaaS is having to do with a car. So in this metaphor, IaaS is like leasing a car. So if you've ever leased a car, you probably did a lot of research and you care about the specs of the car and their performance. You care about the color of the car, what kind of car it is. And you're the one driving, and you're paying for it. You're also paying for the gas and any tolls or maintenance. With platform as a service, in this metaphor, that's more like renting a car. So say you're on vacation and you just got off the airport and you're going to pick up your rental car. You don't really care what color it is. You don't really even care about the specs of it, but you're still driving and you're paying for the gas and any tolls you go through. Software as a service is, again, the easiest one. That one's more like getting a taxi or an Uber. So with a taxi or an Uber, you don't care at all about what kind of car it is, what color it is, and in fact, you're not even the one driving or paying for gas or any tolls because that's baked into the price.
So let's see what it means in terms of cloud computing and its 3 service models. With IaaS, the cloud provider manages the physical resources, data centers, cooling, power, network and security, as well as computing resources that include servers and storage. With PaaS, the provider, in addition to the computing resources, also manages the platform infrastructure, which includes the operating systems, development tools, databases, and business analytics. In the SaaS model, in addition to the infrastructure and the platform resources, the provider also hosts and manages the applications and data. In the next video, we'll take a closer look at infrastructure as a service, its features, benefits, and some use cases. In this video, we will discuss the infrastructure as a service model in more detail. Infrastructure as a service, commonly referred to as IaaS or simply IaaS, is a form of cloud computing that delivers fundamental compute, network, and storage resources to consumers on demand over the internet on a pay-as-you-go basis. The cloud provider hosts the infrastructure components traditionally present in an on-premises data center as well as the virtualization or hypervisor layer. In an IaaS cloud environment, customers can create or provision virtual machines, or VMs, in their choice of region and zone available from the cloud provider. These VMs typically come pre-installed the customer's choice of operating system. The customers can then deploy middleware, install applications, and run workloads on these VMs. They can also create storage for their workloads and backups. Cloud providers often provide customers the ability to track and monitor the performance and usage of their cloud services and manage disaster recovery. Let's look at the key components of cloud infrastructure. Physical data centers. IaaS providers manage large data centers that contain the physical machines required to power the various layers of abstraction on top of them. In most IaaS models, end users do not interact directly with the physical infrastructure, but experience it as a service provided to them. Compute. IaaS providers manage the hypervisors, and end users programmatically provision virtual instances with desired amounts of compute, memory, and storage resources. Cloud compute typically comes with supporting services like auto-scaling and load balancing that provide scalability and high performance. Network. Users get access to networking resources on the cloud through virtualization or programmatically through APIs. Storage. There are 3 types of cloud data storage: object, file, and block storage. Object storage is the most common mode of storage in the cloud, given that it is highly distributed and resilient. IaaS supports a wide array of use cases. We'll look at some typical use cases here. Organizations today are using cloud infrastructure services to enable their teams to set up test and development environments faster, helping create new applications more quickly. By abstracting the low-level components, cloud infrastructure is helping developers focus more on business logic than infrastructure management. Business continuity and disaster recovery require a significant amount of technology and staff investments. IaaS is helping organizations reduce this cost and make applications and data accessible as usual during a disaster or outage. Organizations are using cloud infrastructure to deploy their web applications faster and also scale infrastructure up and down as demand fluctuates. Organizations are leveraging the high-performance computing capabilities of cloud infrastructure to solve complex problems involving millions of variables and calculations, such as climate and weather predictions and financial modeling. Mining massive data sets to locate valuable patterns, trends, and associations requires a huge amount of processing power. Cloud infrastructure not only provides the required high-performance computing, but also makes it economically viable. While there are some concerns regarding the lack of transparency in the cloud infrastructure's configuration and management, and dependency on a third party for workload availability and performance, infrastructure as a service is the fastest growing cloud model today. In the next video, we will look at platform as a service model, its features, benefits, and some use cases. Platform as a Service, commonly referred to as PaaS or simply PaaS, is a cloud computing model that provides customers a complete platform to develop, deploy, manage, and run applications created by them or acquired from a third party. The PaaS provider hosts everything: servers, networks, storage, operating system, application runtimes, APIs, middleware, databases, and other tools at their data center. The provider also takes responsibility for the installation, configuration, and operation of the application infrastructure, leaving the user responsible for only the application code and its maintenance. Customers pay for this service on a usage basis and purchase resources on demand. With IaaS, the cloud provider offers access to raw computing resources, such as servers, storage, and networking, while the user is responsible for the platform and application software. With PaaS, or PaaS, the cloud service provider delivers and manages the entire platform infrastructure, abstracting users from the lower-level details of the environment. Let's look at some essential characteristics of Platform as a Service, or PaaS. PaaS clouds are distinguished by the high level of abstraction they provide to the users, eliminating the complexity of deploying applications, configuring infrastructure, and provisioning and configuring supporting technologies like load balancers and databases. PaaS clouds provide services and APIs that help simplify the job of developers in delivering elastically scalable and highly available cloud applications. These services typically include a variety of capabilities, such as APIs for distributed caching, queuing, and messaging, file and data storage, workload management, user identity, and analytics, thus eliminating the need to integrate disparate components. The PaaS runtime environment executes end-user code according to policies set by the application owner and cloud provider. Many of the PaaS offerings provide developers with rapid deployment mechanisms, or push-and-run mechanism, for deploying and running applications. PaaS offerings support a range of application infrastructure or middleware capabilities, such as application servers, database management systems, business analytics servers, mobile backend services, integration services, business process management systems, rules engines, and complex event processing systems. Such an application infrastructure assists developers by reducing the amount of code that must be written while expanding the application's functional capabilities. The most important use case for PaaS is strategic. Build, test, deploy, enhance, and scale applications rapidly and cost-effectively. Let's look at some more use cases for PaaS. API development and management. Organizations are using PaaS to develop, run, manage, and secure APIs and microservices, which are loosely coupled, independently deployable components and services. Internet of Things, or IoT. PaaS clouds support a broad range of application environments, programming languages, and tools used for IoT deployments. Business analytics or intelligence. PaaS tools allow organizations to analyze their data to find business insights that enable more informed business decisions and predictions. Business process management, or BPM. Organizations are using the PaaS cloud to access BPM platform delivered as a service. Master data management, or MDM. Organizations are leveraging the PaaS cloud to provide a single point of reference for critical business data, such as information about customer transactions and analytical data to support decision-making. Let's look at some advantages of using PaaS. Scalability, made possible because of the rapid allocation and deallocation of resources with a pay-as-you-use model offered by PaaS. The APIs, support services, and middleware capabilities that PaaS clouds provide assist developers in focusing their efforts on application development and testing, resulting in faster time to market for their products and services. Middleware capabilities also reduce the amount of code that need to be written while expanding the application's functional capabilities. Greater agility and innovation, because using PaaS platforms means that you can experiment with multiple operating systems, languages, and tools without having to invest in these resources. You can evaluate and prototype ideas with very low risk exposure, resulting in faster, easier, less risky adoption of a wider range of resources. Some of the key PaaS offerings available in the market today include AWS Elastic Beanstalk, Cloud Foundry, IBM Cloud Paks, Windows Azure, Red Hat OpenShift, Magento Commerce Cloud, Force.com, and Apache Stratos. PaaS clouds do come with some risks. Risks that all cloud offerings have in general, such as information security threats and dependency on the service provider's infrastructure. Services can get impacted when a service provider's infrastructure experiences downtime. Customers also don't have any direct control over the changes that may take place when a provider makes changes in its strategy, service offerings, or tools. But the benefits can far outweigh these risks. PaaS continues to experience strong growth and is predicted to become the prevailing platform delivery model moving forward. In the next video, we will look at software as a service model, its features, benefits, and some use cases.
Software as a Service, or SaaS, is a cloud offering that provides users with access to a service provider's cloud-based software. SaaS providers maintain the servers, databases, and code that constitute an application. They also manage access to the application, including security, availability, and performance. Applications reside on a remote cloud network, and users use these applications without having to maintain and update the infrastructure. Core business process supported by SaaS today include email and collaboration via offerings such as Microsoft's Office 365 and Google's Gmail, customer relationship management via services such as NetSuite CRM and Salesforce, human resource management via services from Workday and SAP SuccessFactors, financial management, billing and collaboration, and many more. According to Forrester Research, SaaS has overtaken on-premises solutions in categories such as human capital management, HCM, customer relationship management, CRM, and collaboration. Solutions once available with several different deployment options are now SaaS only. Let's look at key characteristics of software as a service. SaaS clouds have a multi-tenant architecture. Infrastructure and code are maintained centrally and accessed by all users. SaaS makes it easy for users to manage privileges, monitor data use, and ensure everyone sees the same information at the same time. Security, compliance, and maintenance are all part of the offering. In SaaS, customizations are often limited. However, some SaaS applications may allow certain types of customizations, like branding. They can modify data fields and enable or disable features within the business process. These customizations are preserved through upgrades. Users pay for the use of the services via a subscription model. The use of a resource can be scaled easily, depending on service needs. Key benefits of adopting SaaS. Businesses can directly procure solutions without upfront capital and assistance from IT, greatly reducing the time from decision to value from months to days. SaaS greatly increases workforce productivity and efficiency. Users can access core business apps from wherever. They can also buy and deploy apps in minutes, reducing the typical obstacles enterprises have to test the products they might use. Using SaaS applications, individuals and small enterprises can spread out their software costs over time. Let's look at some use cases for SaaS. Organizations are moving to SaaS for their core business needs as part of their strategic transformation to reduce on-premises IT infrastructure and reduce capital expenditure. Organizations are leveraging SaaS to avoid the need for ongoing upgrades, maintenance, and patching done traditionally by internal IT resources. Applications run reliably with minimal input. For example, email servers, and office collaboration and productivity tools. Organizations are increasingly opting for SaaS e-commerce platforms to manage their websites, marketing, sales, and operations. With SaaS, organizations are able to take advantage of the resilience and business continuity of the cloud provider. Enterprises are now developing SaaS integration platforms, or SIPs, for building additional SaaS applications, moving SaaS beyond standalone software functionality to a platform for mission-critical applications. SaaS does evoke some concerns as well, primary among them being data ownership and data safety. Security is an important consideration when you're allowing a third party to maintain business-critical data, and application access relies on a good network connection. But the benefits far outweigh the concerns, with SaaS making up the largest segment of the cloud market today. In our introductory cloud video, we briefly mentioned the 4 deployment models for cloud. In this video, we will discuss the public cloud deployment model in more detail. Deployment models indicate where the infrastructure resides, who owns and manages it, and how cloud resources and services are made available to users. The 4 cloud deployment models include public cloud, private cloud, community cloud, and hybrid cloud. In a public cloud model, users get access to servers, storage, network, security, and applications as services delivered by cloud service providers over the Internet. Using web consoles and APIs, users can provision the resources and services they need. The cloud provider owns, manages, provisions, and maintains the infrastructure, renting it out to customers either for a subscription charge or user-based fee. Users don't own the servers their applications run on, or storage their data consumes, or manage the operations of the servers, or even determine how the platforms are maintained. In very much the same way that we consume and pay for utilities such as water, electricity, or gas in our everyday lives, we don't own any of these cloud resources. We make an agreement with the service provider, use the resources, and pay for what we use within a certain period. Public clouds offer significant cost savings in terms of total cost for ownership, TCO, as the provider bears all the capital, operational, and maintenance expenses for the infrastructure and the facilities they are hosted in. It makes scalability as easy as requesting more capacity. However, with a public cloud, the user does not have any control over the computing environment and is subject to the performance and security of the cloud provider's infrastructure. There are several public cloud providers in the market today, such as Amazon Web Services, Microsoft Azure, IBM Cloud, Google Cloud Platform, and Alibaba Cloud. While all providers include a common set of core services, such as servers, storage, network, security, and databases, they also offer a wide spectrum of niche services with varied payment options. Let's talk about some of the characteristics of a public cloud. A public cloud is a virtualized multi-tenant architecture enabling tenants or users to share computing resources, residing outside their firewalls. The cloud provider's pool of resources, including infrastructure, platforms, and software, are not dedicated for use by a single tenant or organization. Resources are distributed on an as-needed basis offered through a variety of subscription and pay-as-you-go models. Public clouds have significant benefits. We'll go over some of these benefits here. Vast on-demand resources are available, allowing applications to respond seamlessly to fluctuations in demand. Considering the large number of users that share the centralized cloud resources on demand, the public cloud offers the most significant economies of scale. The sheer number of server and network resources available on the public cloud means that a public cloud is highly available. If one physical component fails, the service still runs unaffected on the remaining available components. It's also important to note some concerns users have regarding public clouds, key among them being security and data sovereignty compliance. Security issues such as data breaches, data loss, account hijacking, insufficient due diligence, and system and application vulnerability seem to be some of the fears users continue to have concerning security in the public cloud. With data being stored in different locations and accessed across national borders, It has also become increasingly critical for companies to be compliant with data sovereignty regulations governing the storage, transfer, and security of data. A service provider's ability to not just keep up with the regulations, but also the interpretation of these regulations is a concern shared by many businesses. Let's look at some common use cases for public cloud. Organizations are increasingly opting to access cloud-based applications and platforms so their teams can focus on building and testing applications and reducing time to market for their products and services. Businesses with fluctuating capacity and resourcing needs are opting for the public cloud. Organizations are using public cloud computing resources to build secondary infrastructures for disaster recovery, data protection, and business continuity. More and more organizations are using cloud storage and data management services for greater accessibility, easy distribution, and backing up their data. IT departments are outsourcing the management of less critical and standardized business platforms and applications to public cloud providers. In the next video, we will look at the private cloud model, its features, benefits, and some use cases.
The National Institute of Standards and Technology defines private cloud as cloud infrastructure provisioned for exclusive use by a single organization comprising multiple consumers, such as the business units within the organization. It may be owned, managed, and operated by the organization, a third party, or some combination of them, and it may exist on or off premises. Private cloud platforms can be implemented internally or externally. When the platform is provisioned over an organization's internal infrastructure, it runs on premises and is owned, managed, and operated by the organization. When it is provisioned over a cloud provider's infrastructure, it is owned, managed, and operated by the service provider. This external private cloud offering that resides on a cloud service provider's infrastructure is called a virtual private cloud, or VPC. A VPC is a public cloud offering that lets an organization establish its own private and secure cloud-like computing environment in a logically isolated part of a shared public cloud. Using a VPC, organizations can leverage the dynamic scalability, high availability, and lower cost of ownership of a public cloud while having the infrastructure and security tailored to the organization's unique needs. Virtual private clouds are offered by most public cloud providers, such as IBM and Amazon. A private cloud is a virtualized environment modeled to bring in the benefits of a public cloud platform without the perceived disadvantages of an open and shared public platform. Users of a private cloud, such as developers and business units in an organization, still get to leverage benefits such as economies of scale, granular scale, operational efficiencies, and user self-service, while exercising full control over access, security, and compliances specific to their organization and business. Private clouds provide you with 1. The ability to leverage the value of cloud computing using systems that are directly managed or under perceived control of the organization's internal IT. 2. The ability to better utilize internal computing resources, such as the organization's existing investments in hardware and software, thereby reducing costs. 3. Better scalability through virtualization and cloud bursting. That is, leveraging public cloud instances for a period of time but returning to the private cloud when the surge is met. 4. Controlled access and greater security measures customized to specific organizational needs. 5. The ability to expand and provision things in a relatively short amount of time, providing greater agility. Organizations may choose to opt for private cloud because of various reasons. Because their applications provide a unique competitive advantage, there are security and regulatory concerns, or because their data is highly sensitive and subject to strict industry or governmental regulations. Let's look at some common use cases for a private cloud. 1. A private cloud is an opportunity for organizations to modernize and unify their in-house and legacy applications. Moving these applications from their dedicated hardware to the cloud also allows them to leverage the power of the compute resources and multiple services available on the cloud. 2. Using the private cloud, organizations are integrating data and application services from their existing applications with public cloud services. This allows them to leverage their private cloud's compute capability for the larger jobs while pulling data into an application on a private cloud to leverage public cloud services, essentially opening their data centers to work with cloud services. 3. Application portability is a key feature of cloud platforms. Using the private cloud gives organizations the ability to build applications anywhere and move them anywhere without having to compromise security and compliance in the process. 4. Some of the key reasons that may prevent an organization from moving to a public cloud include security and regulatory concerns and data sensitivity. A private cloud offers these organizations the benefits of on-demand enterprise resources while exercising full control over critical security and compliance issues from within the environment of their dedicated cloud.
Hybrid cloud is a computing environment that connects an organization's on-premise private cloud and third-party public cloud into a single, flexible infrastructure for running the organization's applications and workloads. The mix of public and private cloud resources gives organizations the flexibility to choose the optimal cloud for each application or workload. Workloads move freely between the two clouds as needs change. Organizations can choose to run the sensitive, highly regulated, and mission-critical applications or workloads with reasonably constant performance and capacity requirements on private cloud infrastructure, while deploying the less sensitive and more dynamic workloads on the public cloud. With proper integration and orchestration between the public and private clouds, you can leverage both clouds for the same workload. For example, you can leverage public cloud instances for a period of time, but return to the private cloud when the surge is met, also known as cloud bursting. The key tenets of a hybrid cloud are interoperability, scalability, and portability. Hybrid cloud is interoperable, which means that the public and private cloud services can understand each other's APIs, configuration, data formats, and forms of authentication and authorization. When there's a spike in demand, a workload running on the private cloud can leverage the additional public cloud capacity, making it scalable. A hybrid cloud is also portable. Since you're no longer locked in with a specific vendor, you can move applications and data not just between on-premise and cloud systems, but also between cloud service providers. Hybrid is about taking the best of both worlds. There are two common types of hybrid clouds: hybrid monocloud and hybrid multi-cloud. A hybrid monocloud is a hybrid cloud with one cloud provider, while a hybrid multi-cloud is an open standards-based stack that can be deployed on any public cloud infrastructure. The difference lies in the flexibility that the hybrid multi-cloud offers organizations to move workloads and environments from one vendor to another. There is also a variant of hybrid multi-cloud called the composite multi-cloud, which makes this flexibility even more granular as it distributes single applications across multiple providers, allowing you to move application components across cloud services and vendors as needed. Hybrid cloud offers significant benefits in areas of security and compliance, scalability and resilience, resource optimization, and cost saving. A hybrid cloud lets organizations deploy highly regulated or sensitive workloads in a private cloud while running the less sensitive workloads on a public cloud. Using a hybrid cloud, you can scale up quickly, inexpensively, and even automatically using the public cloud infrastructure, all without impacting the other workloads running on your private cloud. Because you're not locked in with a specific vendor and also don't have to make either or decisions between the different cloud models, you can make the most cost-efficient use of your infrastructure budget. You can maintain workloads where they are most efficient, spin up environments using pay-as-you-go in the public cloud, and rapidly adopt new tools as you need them. However, hybrid clouds are complex and challenging to deploy and maintain since they involve synchronization, redirection, latency, security, portability, interoperability, and compatibility of policies, applications, and data, and so on. A typical organization will have a range of applications and workloads spread across private, public, and traditional IT environments. This represents a range of opportunities for optimization via a hybrid cloud approach. Let's look at some increasingly common hybrid cloud use cases. Software as a service integration. Through hybrid integration, organizations are connecting software as a service applications available in the public cloud to their existing public cloud, private cloud, and traditional IT applications to deliver new solutions. Data and AI integration. Organizations today are creating richer and more personal experiences by combining new data sources on the public cloud, such as weather, social, the Internet of Things, CRM, and ERP, with existing data and analytics, machine learning, and AI capabilities. Enhancing legacy apps. An increasing number of organizations are using public cloud services to upgrade the user experience of their on-premises applications and deploy them globally to new devices, while incrementally modernizing their core business systems. VMware migration. More and more organizations are lifting and shifting their on-premises virtualized workloads to a public cloud without conversion or modification to reduce their on-premises data center footprint and position themselves to scale without added capital expense. Leveraging public cloud services. Using the private cloud, organizations are integrating data and application services from their existing applications with public cloud services. This allows them to leverage their private cloud's compute capability for the larger jobs, while pulling data into an application on a private cloud to leverage public cloud services, essentially opening their data centers to work with cloud services.
Hi everyone, my name is Sai Venom, and I'm a developer advocate with IBM. Today, I'm excited to introduce a 3-part video series on hybrid cloud architectures. Hybrid cloud is a concept that's been around for quite some time, but we're finding that it's becoming increasingly used to architect and modernize existing or legacy applications. According to research, we found that 75% of non-cloud applications will be moving to the cloud in the next 3 years. This goes to say that if you're not already thinking about your hybrid cloud strategy, you may be falling behind. If you want to learn more about the basics of hybrid cloud, check out my Hybrid Cloud Explained video where I cover the basic concepts of all hybrid cloud architectures. In this 3-part series, I want to dive deeper and hit on key concepts that make up a hybrid cloud architecture. And to do that, we're going to start with part 1 of this video series, which is going to be Connect. Connectivity and interoperability are core concepts of hybrid cloud architectures. You can imagine that you have existing applications that may be running on-prem, working with maybe a private cloud, and you can also imagine you'd be taking advantage of public cloud as well. And you have services that are running across all of these environments. We need a way to securely connect them to one another. So taking advantage of solutions, open source solutions that we have, things like Linux-based containers, Kubernetes, Istio, as well as multi-cluster management tools, message queues, brokers. The list is endless, but there's a lot of solutions out there, when used properly, help you hit that connectivity that you need with hybrid cloud architectures. In part 2, we want to talk about modernization. So we'll be switching gears a little bit here. You can imagine that with existing applications that you might have a monolithic application that you want to break apart and move to a public cloud. And that might allow you to take better advantage of scaling that public environments offer. That's a very simple use case, and one of many when it comes to modernizing your applications. In part 2, I'm going to hit on strategies to modernize those legacy applications, which is a core part of hybrid cloud architectures. In part 3, we want to talk about security. We're finding that every year you're hearing about a different data breach, and we're hearing about privacy regulations that are becoming increasingly more strict being imposed on companies. The fact is, moving to hybrid cloud might scare some folks, but we have the right solutions to ensure that you can take advantage of your existing on-prem assets, the security and the ease of use that you have there, while securely moving some of your assets to a public or even a private cloud. This allows you to kind of have the comfort of taking advantage of all the resources you have on public cloud while still maintaining the security that's required of your architectures. I believe that this three-part series is going to help tackle the three major issues that you may have when architecting your hybrid cloud applications. As always, we're always checking for your comments and your feedback. And if you have any other topics that you'd like us to cover in lightboarding videos, please let us know below. Be sure to subscribe and stay tuned for future videos in this series. And if you want to get started on your hybrid cloud architecture journey right now, go ahead and check out some of the links that we have below and the videos that we have lined up. Thank you.
Welcome to Cloud Computing Service Models Expert Viewpoints. In this video, we will listen to several cloud experts discuss the choice and adoption of different cloud models. Can you talk about use case scenarios or considerations for choosing the right cloud model for your organization? Model as in LaaS, SaaS, or PaaS, or public, private, or hybrid.
When choosing a cloud model for your organization, you want to consider where is your organization at in the cloud journey. So if they have a lease that's about to expire at the data center, then they might not have time to rewrite the application to be cloud native. They might just have time to take the application exactly as it is on the virtual machines in the data center and move them onto virtual machines in the cloud. And that's called infrastructure as a service. If you have more time, you could consider re-platforming, and that means putting it on a platform as a service, such as containers, or a service that operates the operating system for you, patches the operating system for you, and all you have to do is install extra dependencies yourself. Or if you want to move really fast and you have a brand new product that you're just starting to write, why not start with the latest approach, which is functions as a service? Use serverless functions and you can move really fast because you don't have to manage any underlying infrastructure. The security of the operating system is handled for you by the cloud provider.
Generally, my answer is to stay as high on the stack as you can to meet your business requirements. So, SaaS applications provide the business value with little or no technology resource investment beyond the subscriptions. So if that works, that's great. Platform as a service, as I mentioned, allows developers to focus on building and deploying new applications without having to grapple with the details of cloud infrastructure. And if in a lot of cases that will save money and investment and allow you to focus on building your products more quickly in time to market. Infrastructure as a service, though, is the right answer when you need control, specific control of all the compute and network resources to achieve your business goals. So in many cases, that'll make sense too.
While choosing the right cloud model, organizations should consider what are their business needs, the level of control that they would like to have, and the cost. If your business needs an out-of-the-box software like email, CRM, event management tool, etc., then choose software as a service. It will offer access from anywhere and any device, automatic software updates, lower cost and easy adoptions. You will need a vendor to manage the software. If you require a platform for building products, then choose platform as a service. It is a perfect choice for software development companies as it provides developers with reduced development time, different programming language support, easy collaboration with teams, and reduces the cost. If your business simply needs a virtual machine, then opt for infrastructure as a service. Scenarios for using infrastructure as a service can be hosting a website, virtual data centers, or performing data analysis. Infrastructure as a service is more expensive than SaaS or PaaS, and all issues related to virtual machine management is business's responsibility. However, it is more reliable and secure as data is kept at designated data centers.
As you move down the layers of abstraction from software as a service all the way to infrastructure as a service, the trade-off is that you take on more management responsibilities yourself, with the advantage of having more control over how your resources are configured. I'll typically only take that trade-off when I have to. So let's say I'm building a website. I'll typically default to a software as a service option, let's say WordPress. But then maybe it turns out the website I'm building is somewhat complicated and I want it to be a React app. I might host that app on a platform as a service. But then let's suppose I have a requirement that my app needs to run in an operating system that is not supported by the platform as a service. At that point, I'll have to just provision some VMs myself and figure out how to run it myself.
After choosing the cloud service model and the cloud type offered by vendors, customers need to plan the infrastructure architecture. The infrastructure layer is the foundation of the cloud. This layer consists of physical resources that are housed in regions, zones, and data centers. A cloud provider's IT environment is typically distributed across many regions around the world. A cloud region is a geographic area or location where a cloud provider's infrastructure is clustered and may have names like NA South or US East. The cloud regions are isolated from each other, so that if one region was impacted by a natural disaster, like an earthquake, the cloud operations in other regions would keep running. Each cloud region can have multiple zones, or availability zones, or AZ for short, which are typically distinct data centers with their own power, cooling, and networking resources. These zones can have names like DAL-09 or US East 1. The isolation of zones improves the cloud's overall fault tolerance, decreases latency, and avoids creating a single shared point of failure. The availability zones, and data centers within them, are connected to other AZs and regions, private data centers, and the internet using very high bandwidth network connectivity. A cloud data center is a huge room or a warehouse containing cloud infrastructure. These data centers contain pods and racks, or standardized containers of computing resources such as servers, as well as storage and networking equipment, virtually everything that a physical IT environment has. Computing resources. Cloud providers offer several compute options: virtual servers, bare metal servers, and serverless computing resources. Most of the servers in a cloud data center run hypervisions to create virtual servers or virtual machines, also called VMs for short, that are software-based computers based on virtualization technologies. Other servers in the racks are bare metal servers that are physical servers that aren't virtualized. Customers can provision VMs and bare metal servers as and when they need them and run their workloads on them. Cloud users can also run their workloads on serverless computing resources, which are an abstraction layer on top of virtual machines. We will talk about all three compute options in greater detail in subsequent videos. Storage. Information and data can consist of files, code, documents, images, videos, backups, snapshots, and databases, and can be stored in many different types of storage options on the cloud. Bare metal servers and virtual servers are provisioned with default storage in local drives. Networking. Networking infrastructure in a cloud data center includes traditional networking hardware like routers and switches, but more importantly for users of the cloud and cloud providers have software-defined networking, or SDN, options, where certain networking resources are virtualized or made available programmatically through APIs. This allows for easier network provisioning, configuration, and management in the cloud. When servers in the cloud are provisioned, you need to set up their public and private network interfaces. The public network interfaces, as the name suggests, connect the servers to the public internet, whereas the private ones provide connectivity to your other cloud resources and help keep them secure. As in the physical IT world, network interfaces in the cloud need to have IP addresses and subnets either assigned automatically or configured. In a cloud environment, it is even more important to configure which network traffic and users can access your resources, which can be done by setting up security groups and access control lists, or ACLs. For further security and isolation of your resources in the cloud, most cloud providers provide virtual local area networks, VLANs, virtual private clouds, VPCs, and virtual private networks, VPNs. Some of the traditional hardware appliances, such as firewalls, load balancers, gateways, and traffic analyzers, can also be virtualized and made available as services in the cloud. Another network capability provided by the cloud providers is content delivery networks, or CDNs, that distribute content to multiple points throughout the world, so users accessing the content can access it more quickly by getting it from a point nearest to them. We will learn more about some of these cloud networking options and terminology in subsequent videos. Cloud infrastructure is constantly advancing and improving. In the next video, we explain virtualization and virtual machines.
Hi, my name is Kaylee Bovey with the IBM Cloud team, and today we're going to be talking about virtualization. As you know, virtualization is a fairly old technology, but it's still super relevant to building your cloud computing strategy today. So first off, what is virtualization? Simply put, virtualization is the process of creating a software-based or virtual version of something, whether that be compute, storage, networking, servers, or applications. And what makes virtualization feasible is something called the hypervisor. So we're going to write that here. And what a hypervisor is it's simply a piece of software that runs above the physical server or host. And there are a couple different types of hypervisors out there. And what they do is essentially pull the resources from the physical server and allocate them to your virtual environments. There are two main types of hypervisors out there, one being type 1, very simple to remember, and two, you guessed it, type 2. So let's start with type 1. A type 1 hypervisor is a hypervisor that is installed directly on top of the physical server. They're also called bare metal hypervisors, so we'll write that up here, just so you can remember. These are the most frequently typed of used hypervisors, and they're most secure, they lower the latency, and these are the ones that you'll see in the market the most. Some examples would be VMware ESXi, or Microsoft Hyper-V, or even open source KVM. The other type of hypervisor is a type 2 hypervisor over here. And what makes these different is that there is a layer of host OS that sits between the physical server and the hypervisor. So, by that nature, they are also called hosted. These are a lot less frequent. They're mostly used for end-user virtualization, and you might see some in the market that are called like Oracle VirtualBox or VMware Workstation. Again, they're a lot less frequent. They're a bit more, they have a higher latency than a type 1 hypervisor. So once you have your hypervisor installed, you can build virtual environments or virtual machines, or simply put, VMs. So let's spin up some environments. So what makes a VM a VM? A VM is simply a software-based computer. They run like a physical computer, they have an operating system and applications, and they're completely independent of one another, but you can run multiple of them on a hypervisor. And the hypervisor manages the resources that are allocated to these virtual environments from the physical server. So, because they're independent, you can run different operating systems on different virtual machines. So you could run Windows here, or Linux here, or Unix here, for example. And because they're independent, they're also extremely portable. You can move a virtual machine from one hypervisor to another hypervisor on a completely different machine almost instantaneously, which gives you a lot of flexibility and a lot of portability within your environment. So looking at all of this, this is the core of virtualization as a process. So let's talk about a couple key benefits that you want to take away from this. One, cost savings. When you think about this and the fact that you can run multiple virtual environments from one piece of infrastructure means that you can drastically reduce your physical infrastructure footprint. This is consolidation at its core, and the fact that you don't have to maintain nearly as many servers, run as much electricity, save on maintenance costs means that you save on your bottom line at the end of the day. Number 2 would be agility and speed. So like I said, spinning up a virtual machine is relatively easy and quick. A lot more simple than provisioning an entire new environment for your developers if they say they want to spin up a new environment so that they can run a dev test scenario. Whatever it might be, virtualization makes that process a lot simpler and quicker. And 3, lowers your downtime. So let's say that this host goes out unexpectedly. The fact that you can move virtual machines from one hypervisor to another on a different physical server means that you have a great backup plan in place, right? So if this host goes down, you can simply move your VMs very quickly to another hypervisor on a machine that is working.
Virtualization and VMs are at the center of cloud computing and provide many benefits. In the next video, we will discuss the types of virtual machines. Virtual machines, or VMs, are also known as virtual servers, or virtual instances, or simply instances, depending on the cloud provider. The various cloud providers make VMs available in a variety of configurations and deployment options to serve different use cases. When you create a virtual server in the cloud, you specify the region and zone, or data center, you want the server to be provisioned in, and the operating system you want on it. You can choose between shared, that is, a multi-tenant VMs, or dedicated, that is, a single-tenant VMs. You can also choose between hourly or monthly billing and select storage and networking options for the virtual server. Now let's look at a few different types of VMs that can be provisioned in the cloud. Shared or public cloud VMs are provider-managed multi-tenant deployments that can be provisioned on demand with predefined sizes. Being multi-tenant means that the underlying physical server is virtualized and is shared across other tenants or users. To satisfy different workloads, cloud providers offer predefined sizes and configurations ranging from a single virtual core and a small amount of RAM to multiple virtual cores and much larger amounts of RAM. For example, there can be configurations for compute-intensive workloads, memory-intensive workloads, or high-performance I/O. Rather than pick from only predefined sizes, some providers also offer custom configurations that allow users to define the number of cores and RAM and local storage characteristics. Public VMs are usually priced by the hour, or in some cases, even seconds, and configurations start as low as pennies per hour. Some providers also let you get monthly VMs, which can result in some cost savings if you know you will run the VM for at least a month. But if you decide to decommission the VM in the middle of the month, you will still be charged for the full month. Transient or spot VMs take advantage of unused capacity in a cloud data center. Cloud providers make this unused capacity available to users at a much lower cost than regular VMs of similar sizes. Although the transient VMs are available at a huge discount, the cloud provider can choose to deprovision them at any time and reclaim the resources for provisioning regular, higher-priced VMs. Because you run the risk of losing these VMs when capacity in the data center decreases, these VMs are great for non-production workloads such as testing and developing applications. They are also useful for running stateless workloads, testing scalability, or running big data and high-performance computing workloads at a low cost. Reserved virtual server instances allow you to reserve capacity and guarantee resources for future deployments. You reserve desired amount of virtual server capacity, provision instances from that capacity when you need them, and choose a term, such as 1 year or 3 years, for your reserved capacity. You're guaranteed this capacity within the data center of your choice for the life of the contract term. By committing to a longer term, you can also lower your costs compared to hourly or monthly instances. This can be useful when you know you require at least a certain level of cloud capacity for a specific duration. If you exceed your reserved capacity, you can always choose to supplement your unplanned usage and capacity requirements with hourly or monthly VMs. Note, however, that not all predefined VM families or configurations may be available as reserved. Dedicated hosts offer single-tenant isolation. This means that only your VMs run on a given host, so they can make exclusive use of full capacity and resources of the underlying hardware. When provisioning a dedicated host, you need to specify the data center and pod in which you want your host placed. You then assign instances or virtual machines to a specific host. This allows for maximum control over workload placement. Dedicated hosts are typically used for meeting compliance and regulatory requirements or meet specific licensing terms. Virtualization and VMs are at the center of cloud computing and provide many benefits. In the next video, we will discuss bare metal servers, what they are, and what they provide. A bare metal server is a single-tenant, dedicated physical server. In other words, it's dedicated to a single customer. The cloud provider actually takes the physical server and plugs it into a rack in a data center for customers. The cloud provider manages the server up to the operating system, or OS, which means if anything goes wrong with the hardware or rack connection, they will fix or replace it and then reboot the server. The customer is responsible for administering and managing everything else on the server. Bare metal servers are either pre-configured by the cloud provider to meet workload packages, or they can be custom configured as per customer specifications. This includes the processors, RAM, hard drives, specialized components, and the OS. Customers can also install their own OS and can install certain hypervisors that aren't available from the cloud provider, and thus create their own virtual machines and farms. With bare metal servers, you can also add GPUs, which are designed for accelerating scientific computation, data analytics, and rendering professional-grade virtualized graphics. Because bare metal servers are physical machines, they take longer to provision than virtual servers. Pre-configured builds of bare metal can take 20 to 40 minutes to provision, and custom builds can take around 3 or 4 hours. But these provisioning times can vary by cloud provider. As bare metal servers are dedicated for use by a single client at any given time, they tend to be more expensive than similarly sized virtual machines. Also note that unlike virtual servers, not all cloud providers provide bare metal servers. Since bare metal servers are fully customizable, they can do what a customer wants in the most demanding environments. Bare metal servers are dedicated and intended for long-term, high-performance use in highly secure and isolated environments. Clients have full access and control of bare metal servers because there's no hypervisor required. As there is no sharing underlying server hardware with other customers, bare metal servers fulfill the demanding needs of high-performance computing, or HPC, and data-intense applications that require minimal latency-related delays. These servers also excel in big data analytics applications and GPU-intensive solutions. Some workload examples that bare metal servers satisfy are ERP, CRM, AI, deep learning, and virtualization. If you use any applications that require high degrees of security control or apps that you've typically run in an on-premises environment, then a bare metal server is a good alternative in the cloud. When comparing bare metal servers to virtual servers, some of the most important considerations are found in customer need. Bare metal servers work best for CPU and I/O intensive workloads, excel with highest performance and security, satisfy strict compliance requirements, and offer complete flexibility, control, and transparency but come with added management and operational overhead. Whereas virtual servers are rapidly provisioned, provide an elastic and scalable environment, and are low cost to use. However, since they share underlying hardware with other virtual servers, they can be limited in throughput and performance. As cloud environments gain greater adoption and digital data invites rapidly increasing cybersecurity threats, building secure networks on the cloud is crucial. Let's look at how we can build a secure cloud networking presence. As one might expect, the notion of building a cloud network is not much different from deploying a network in an on-premises data center. The main difference stems from the fact that in the cloud, we use logical instances of networking elements as opposed to physical devices. For example, network interface controllers, or NICs, would be represented by vNICs in cloud environments. In the cloud, networking functions are delivered as a service rather than in the form of rack-mounted devices. To create a network in the cloud, one starts by defining the size of the network or the IP address range that establishes the boundaries or the cloud network. Cloud networks are deployed in networking spaces that are logically separated segments of the networks using options, including virtual private cloud, or VPC, that in turn can be divided into smaller segments called subnets. Logically segmented cloud networks are private carve-out of the cloud that offer customers the security of private clouds and the scalability of public clouds. Cloud resources, such as VMs or virtual server instances, VSIs, storage, network connectivity, and load balancers are deployed into subnets. Using subnets allows users to deploy enterprise applications using the same multi-tier concepts used in on-premises environments. Subnets are also the main area where security is implemented in the cloud. Every subnet is protected by access control lists, or ACLs, that serve as a subnet-level firewall. Within the subnet, one could create security groups that provide security at the instance level, such as VSIs. Once you build a subnet, then it is time to add some VSIs and storage to it so that you could run your applications. Let's say you have a 3-tier application that requires web access VSIs, application tier VSIs, and back-end database VSIs. In this case, we would place the web-facing VSIs into one security group, the application VSIs in a second security group, while the database VSIs in a third security group. It goes without saying that the web-facing VSIs need internet access. A public gateway instance is added to the network to enable users access to the application in the internet tier. While public gateways are great for internet access to the cloud, enterprises are interested in extending their own on-premises resources to the cloud by securely connecting them using virtual private networks, or VPNs. When building many subnets and deploying several workloads, it becomes necessary to ensure that applications continue to be responsive. That is achieved with load balancers that ensure availability of bandwidth for the different applications. Enterprises with hybrid cloud environment find using dedicated high-speed connections between clouds and on-premise resources is a more secured and more efficient way than public connectivity solutions. Some cloud service providers offer such connectivity, such as IBM Cloud and its direct link solution that enables extending on-premises resources to the cloud as needed. Building a cloud network entails creating a set of logical constructs that deliver networking functionality that is akin to the data center networks that all IT professionals have come to rely on for securing their environments and ensuring high-performing business applications. Containers are an executable unit of software in which application code is packaged, along with its libraries and dependencies, in common ways so that it can be run anywhere, whether it be on desktop, traditional IT, or the cloud. Containers are small, fast, and portable, and unlike virtual machines, they do not need to include a guest OS in every instance, and can instead simply leverage the features and resources of the host OS. In the rest of this video, we will see how container-based technology really works.
Hi everyone, my name is Cy Venom, and I'm a developer advocate with IBM. Today, I want to talk about containerization. Whenever I mention containers, most people tend to default to something like Docker, or even Kubernetes these days. But container technology has actually been around for quite some time. It's actually back in 2008 that the Linux kernel introduced C groups, or control groups, that basically paved the way for all of the different container technologies we see today. So that includes Docker, but also things like Cloud Foundry, as well as Rocket, and other container runtimes out there. Let's get started with an example, and we'll say that I'm a developer and I've created a Node.js application, and I want to push it into production. We'll take two different form factors to kind of explain the advantages of containerization. So let's say that first we'll talk about VMs, and then we'll talk about containers. So first things first, let's introduce some of the things that we've got here. So we've got the hardware itself, just a big box. We've got the guest, or rather the host operating system, as well as the hypervisor. The hypervisor is actually what allows us to spin up VMs. Already, let's take a look at this shared pool of resources with the host OS and the hypervisor. We can assume that some of these resources have already been consumed. Next, let's go ahead and take this JS application and push it in. And to do that, I need a Linux VM. So let's go ahead and sketch out that Linux VM. And in this VM, there's a few things to note here. So we've got another operating system in addition to the host OS. It's going to be the guest OS, as well as some binaries and libraries. So that's one of the things about Linux VMs, that even though we're working with a really lightweight application, to create that Linux VM, we have to put that guest OS in there and a set of binaries and libraries. And so that really bloats it out. In fact, I think the smallest Node.js VM that I've seen out there is 400 plus megabytes, whereas the Node.js runtime and app itself would be under 15. So we've got that. We go ahead and let's push that JS application into it. And just by doing that alone, we're going to consume a set of resources. Next, let's think about scaling this out, right? So we'll create 2 additional copies of it. And you'll notice that even though it's the exact same application, we have to use and deploy that separate guest OS and libraries every time. And so we'll do that 3 times. And by doing that, essentially we can assume that for this particular hardware, we've consumed all of the resources. And there's another thing that I haven't mentioned here, but this JS application, I developed it on my MacBook. So when I pushed it into production to get it going on the VM, I noticed that there were some issues and incompatibilities. This is the kind of foundation of this big he said, she said issue, where things might be working on your local machine and work great, but when you try to push it into production, things start to break. And this really gets in the way of doing agile DevOps and continuous integration and delivery. That's solved when you use something like containers. There's a 3-step process when kind of doing anything container related and pushing or creating containers. And it almost always starts with, first, some sort of a manifest. So something that describes the container itself. So in the Docker world, this would be something like a Docker file. In Cloud Foundry, this would be a manifest YAML. Next, what you'll do is create the actual image itself. So for the image, if you're working with something like Docker, that could be something, that would be a Docker image. If you're working with Rocket, it would be an ACI, or application container image. So regardless of the different containerization technologies, this process stays the same. And the last thing you end up with is an actual container itself, that contains all of the runtimes and libraries and binaries needed to run an application. That application runs on a very similar setup to the VMs, but what we've got on this side is, again, a host operating system. But the difference here, instead of a hypervisor, we're going to have something like a runtime engine. So if you're using Docker, this would be the Docker engine. And different containerization technologies would have a different engine. Regardless, it's something that runs those containers. Again, we've got this shared pool of resources, so we can assume that that alone consumes some set of resources. Next, let's think about actually containerizing this technology. So we talked about the three-step process. We create some, a Docker file, we build out the image, we push it to a registry, and we have our container, and we can start pushing this out as containers. The great thing is these are going to be much more lightweight. So deploying out multiple containers, since you don't have to worry about a guest OS this time, you really just have the libraries as well as the application itself. So we've scaled that out 3 times. And because we don't have to duplicate all of those operating system dependencies and create bloated VMs, we actually will use less resources. So choose a different color here. And scaling that out 3 times, we still have a good amount of resources left. Next, let's say that my coworker decides, hey, for this JS application, let's take advantage of a third-party, let's say a cognitive API to do something like image recognition. So, let's say that we've got our third-party service, and we want to access that using maybe a Python application. So he's created that service that accesses that third-party APIs, and with our Node.js application, we want to access that Python app to then access that service. If we wanted to do this in VMs, I'm really tempted to basically create a VM out of both the JS application and the Python application, because essentially that would allow me to continue to use the VMs that I have. But that's not truly cloud native, right? Because if I wanted to scale out the JS but not the Python app, I wouldn't be able to if they were running in the same VM. So to do it in a truly cloud native way, essentially I would have to free up some of these resources, basically get rid of one of these VMs, and then deploy the Python application in it instead. And that's not ideal. But with the container-based approach, what we can do is simply say, since we're modulars, we can say, okay, just deploy 1 copy of the Python application. So we'll go ahead and do that. Here's a different color here. And that consumes a little bit more resources. And then, with those remaining resources, the great thing about container technology, that actually becomes shared between all the processes running. In fact, another advantage, if these container processes aren't actually utilizing the CPU or memory, all of those shared resources become accessible for the other containers running within that hardware. So with container-based technology, we can truly take advantage of cloud-native-based architectures. So we talked about things like portability of the containers. We talked about how it's easier to scale them out. And then overall, with this kind of 3-step process and the way we push containers, it allows for more agile DevOps and continuous integration and delivery.
Containers streamline development and deployment of cloud-native applications. In the next lesson, we will cover cloud storage.
Welcome to Components of Cloud Computing Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss some of the factors considered in deciding between computing resources in the cloud. For example, a bare metal server versus a virtual server versus containers.
Virtual servers are basically running a different OS inside of another operating system. Like an example would be running Windows on top of Linux. And as such, they contain their own complete OS. So VMs look and act very much like physical servers. And because they contain the whole OS, they're typically gigabytes in size, quite large. VMs are far less portable because of their dependence on the operating system, the application, and library versions. So that's a consideration with virtual machines.
When it comes to deciding between containers, virtual servers, and bare metal servers, I'm almost always drawn to containers to start because of their scalability and their cost efficiency. However, that doesn't mean they're always the best option. For example, you might not be able to tolerate your containers running on the same VM as another customer's for security reasons. And in that case, you might decide to provision your own virtual server. Or perhaps you just consistently need the best performance possible and you don't want to deal with the hypervisor tax or noisy neighbor effects. And in that case, you'll go with bare metal.
Containers are based on a Linux-based shared image that can be shared across environments, dev, QA, and production. And this is one very big advantage of containers. It's also possible to spin up containers very fast, milliseconds instead of seconds for virtual machines. They're lightweight, typically megabytes in size. And the key technologies here are Docker, Kubernetes, and OpenShift for container orchestration. And some of the compelling use cases here are where workloads can be broken into, the smallest serviceable units. Here you could think about microservices, for example. And this is perhaps a foundational technology for what's referred to as cloud native architecture.
If you want to have something that doesn't cost as much and only runs when needed, that's a perfect use case for serverless functions, because on some cloud providers, they only charge you as little as by the millisecond of usage. And serverless functions help you not use any time on work like patching the operating system. And if you want to be cloud agnostic, meaning you want to have a hybrid cloud setup, meaning be on different cloud providers at the same time, then containers can be a really good choice because Docker runs the same anywhere.
So in the past few years, I've actually seen containers come quite a long way, especially in the enterprise space. With Kubernetes and OpenShift and other things, quite frankly, containers can run almost any workload you might want to throw at it. There are some exceptions. Sometimes you need a special video card in a bare metal machine, or need to access, kernel level settings and the like, which you can't in a container. But for the most part, I would say you're going to use containers or serverless unless you have a specific need not to.
Bare metal servers are basically a single tenant dedicated hardware server. This is our legacy hardware approach. Advantages: you can optimize the server according to the specific needs for performance, security, and reliability. The disadvantages, however, are limits on on-demand scalability, that the hardware has a fixed capacity, and flat monthly pricing for bare metal servers. Use cases: there are use cases where bare metal servers make sense. Some of these might be things requiring very high performance. Think about gaming or real-time analytics. Or situations where regulatory or compliance requirements dictate a dedicated compute environment, or applications that use steady and continuous compute resources.
If you need extreme speed and a lot of processing power, let's say you're iterating over a design for a supersonic jet and you need to model how it would act in a wind tunnel, and you need to do that 500 times. That's a whole lot of data to process, and you want to use the most powerful machines in a cluster and have them be as close together as possible. So that's bare metal machines.
Cloud storage is where you save data files in the cloud. Certain storage must be attached to a compute node before the storage can be accessed, whereas other storage types can be directly accessed either through the public internet or a dedicated private network connection. Cloud providers host, secure, manage, and maintain the cloud storage and associated infrastructure to ensure you have access to your data when you need it. Cloud storage services allow you to scale your capacity as you need, so you only pay for what you provision, usually on a per gigabyte basis. The cost of storage will vary by type, but in general, the faster the read-write speed of the storage, the higher the per gigabyte cost. Cloud storage is available in 4 main types: direct attached, file storage, block storage, and object storage. Direct attached storage, sometimes referred to as local storage, is storage which is presented directly to a cloud-based server and is effectively either within the host server chassis or within the same rack. This storage is fast and normally only used to store a server's operating system, although it can have several other use cases. The main 2 reasons why direct attached storage is not so great for other uses besides to store the operating system is that it's typically ephemeral, meaning that it only lasts as long as the compute resource it's attached to. It cannot be shared with other nodes, and while you use RAID techniques, it's not as resilient to failure as other types of storage. File storage is typically presented to compute nodes as NFS storage. NFS stands for Network File System and means that the storage is connected to compute nodes over a standard Ethernet network. NFS mounted storage is commonplace, but it tends to be slower than either direct attached storage or block storage because the data travels over an Ethernet network. It also tends to be lower cost than either direct attached or block storage. One advantage of file storage is that it can be mounted or used on multiple servers at once. File-based storage is a simple, straightforward approach to data storage and works well for organizing data in a hierarchical folder structure that desktop users are familiar with. Block storage is presented to compute nodes using high-speed fiber connections, which means that read and write speeds are typically much faster and reliable than with file storage, making block storage suitable for use with databases and other applications where disk speed is important. You typically provision block storage in volumes, which can then be mounted onto a compute node, which it then effectively sees as another hard drive. Volumes can normally only be mounted onto one compute node at a time. With both file and block storage, you may also hear the term IOPS. IOPS stands for Input-Output Operations per Second and relates to the speed of the storage, or, to put it another way, how quickly data can be read from or written to the storage. We'll cover this in a little more detail in a later video. Persistence is a term that is used when provisioning file or block storage and relates to what happens to the storage once the compute node it is attached to is terminated. If the storage is set to persist, then it will not be deleted along with the compute node, meaning that it and its data are preserved and available to mount onto another compute node, though you will continue to pay for the storage. You can also, in some cases, set the storage so that it is automatically deleted with the compute node that it is mounted onto. In this case, as we know, it becomes ephemeral storage. Here, you will also stop paying for the storage, but you will lose any data unless it is backed up somewhere. There are several ways to back up data in the cloud, but one way to back up both file and block storage is to take a snapshot, that is the image of the storage, at a particular instant. Snapshots are usually fast to create. They don't actually write any data, or rather, they create metadata. Don't require downtime, and subsequent snapshots record only changes to the data. They are great for returning storage to the way it was at a particular snapshot, though note, they cannot be used to recover individual files. The fourth kind of storage is object storage. This is a different type of storage in so much as it's not attached to a compute node, rather, it is accessed via an API. Of all the storage types, object storage is by far the cheapest and also the slowest in terms of read and write speeds, but it is infinite in size to the end user. Unlike file and block storage, where you provision a certain storage capacity and it fills up over time, with object storage, you can keep adding files to it and it never fills up. You just pay for what you use. This makes object storage a fantastic repository for all sorts of unstructured data types, large and small, including documents, video, logs, backups, data from IoT, application binaries, and virtual machine images. In the following videos, there will be more detailed information on the different types of storage. In this video, we're going to talk about file storage in greater detail. Like direct attached storage, file storage must be attached to a compute node before it can be accessed and have data stored on it. However, file storage can be less expensive, more resilient to failure, and involve lesser disk management and maintenance for you as the user to do as compared to direct attached storage. You can also provision much larger amounts of file storage and present it as a disk to a server. File storage is mounted from remote storage appliances. That is, the physical disks are contained in a separate, specialized piece of hardware, and they are then connected to the compute node via the underlying infrastructure in the data center. These storage appliances are not only extremely resilient to failure, the data is also far more secure in them as these storage appliances provide services such as encryption in transit. These applications are all managed by the service provider. File storage is mounted to compute nodes via an Ethernet network, the same kind of network that you might receive email or browse the internet over, although this Ethernet network is normally dedicated to the task. This means it can sometimes be referred to as network attached storage, network file storage, or simply NFS. One of the issues with Ethernet networks is that their speed can vary. The more loaded an Ethernet network is, the more likely it becomes that its speed or bandwidth will be affected. Of course, cloud providers build their storage networks to handle very high volumes of traffic, but even so, consistent speed cannot be guaranteed. Therefore, file storage tends to be used for workloads where consistently high network speeds are not a requirement. In terms of workloads, file storage can typically be mounted onto more than one compute node at a time, where the mounted disk or volume looks just like another drive on the compute node. The ability for file storage to be mounted to multiple compute nodes at a time make it an ideal solution where some sort of common storage is required. For example, a departmental file share, a landing zone for incoming files that needs to be processed by an application, or a repository of files that a web service might access. In these applications, the potential variance in the speed of the connecting network is not really an issue. Of course, where cost is an issue, you can use file storage for other applications such as databases, but the trade-off is speed. When you provision file storage, one consideration you need to take into account is the IOPS capacity of the storage. IOPS stands for Input-Output Operations per second and refers to the speed at which the disk can write and read data. Note, this is not the speed of the network between the storage and the compute node. The higher the IOPS value, the faster the speed of the underlying disk. A higher IOPS will also normally cost more. Understanding IOPS is important because if the IOPS value is too low for your application, the storage can become bottlenecked and cause your application to run slowly. Alternatively, if the IOPS is too high, you will probably be paying more than what you need for your storage. For example, a file share may be mounted on 30 different compute nodes, and an application writes and requests data to and from that share 60 times per minute. You can average that out to one operation per second. With this simple example, you can see that each application has different IOPS requirements. In the next video, we're going to talk more about block storage, how it compares with file storage, and when you will typically use one over the other.
In this video, we will discuss block storage and how it compares to file storage in the cloud. Block storage breaks files into chunks or blocks of data and stores each block separately under a unique address. Like direct attached storage and file storage, block storage also must be attached to a compute node before it can be utilized for your workloads. Block storage, like file storage, can be mounted from remote storage appliances, making it extremely resilient to failure and keeping data far more secure in them on account of encryption in transit and encryption at rest services available on these appliances. Block storage is mounted as a volume to compute nodes using a dedicated network of fibers through which signals move at the speed of light. These fiber optic networks are more expensive to build than the Ethernet ones which deliver file storage, which is one reason why block storage tends to have a higher price point. However, since the traffic is moving faster and with speed consistency, they are perfect for workloads that need low latency storage to work effectively. In terms of workloads, it is important to note that unlike file storage, which can be mounted onto 80 compute nodes or more, block storage is normally mounted onto only one compute node at a time. Since these disks run at a consistent high speed, they are perfect for workloads that need consistently fast storage, such as databases and mail servers. Block storage is not suitable for workloads where there needs to be some level of disk sharing between compute nodes. For block storage, as it is for file storage, you need to take the IOPS capacity of the storage into account. Most cloud providers will allow you to specify IOPS characteristics when you provision storage, and in some cases, adjust the IOPS of your storage as you need. So if the requirements or usage behavior of an application changes, you can adjust accordingly. So, to summarize the commonalities and differences between these two storage types, block and file storage is taken from appliances which are maintained by the service provider. Both are normally highly available and resilient and will often include data encryption at rest and in transit. File storage is attached to a compute node using an Ethernet network, so it is sometimes called network attached or NFS storage. File storage is very reliable, but the speed of the connecting network can vary based on load. Block storage is attached via a high-speed fiber network, which is very reliable and consistent. File storage can be attached to multiple compute nodes at once. Block storage can only be attached to one node at a time. File storage is a good choice where file shares are required, where workloads do not require lightning-fast connectivity to storage, or where cost is a factor. Block storage is a good choice when supporting an application that needs consistent fast access to disk, such as databases. Remember to consider the IOPS requirements of the application when provisioning either file or block storage.
Hey guys, my name is Amy Blea. I'm on the offering team here with IBM Cloud, and today I want to talk to you about some traditional types of storage, file and block storage, kind of give you an overview of what they are, and then give you some tips on how to decide when to use one over the other. So let's get started with block storage. Block storage is storage where data is written in raw blocks on the storage, and it's accessed by the servers that you have through a storage area network. So you have all of your servers, they can either be on the same network with each other or in a different network, but they all connect through this storage area network. Now, some of the advantages of using block storage is that block storage provides the lowest possible latency for your applications, and you can also use it for those applications that require high performance or lots of IOPS. Another thing you'll find with block storage is that in general it is highly redundant. Most block storage services provide a capability that's built in where your data is redundant across the volume, so that there should be either a volume should go down or a disk should go away, you can recover your data from another place without having any kind of impact to your application. Now, file storage is connected to your servers a little differently than block storage is. Everything is connected on the same network, so you have all of your files, or your file share here. Those are all the files. And they can all be accessed on the same network by any of the servers on that network. So it's network attached storage. File storage is highly scalable. So you can have multiple file shares on your network and have all of your servers attached to that at one time. It's accessible to multiple runtimes. So here in this illustration, we have a single file share that has multiple servers accessing it all at once. And you can also have multiple simultaneous reads and writes going to your file share all at one time without having to worry about your data being overwritten. So how do you know when is the right time to choose either block storage or file storage for your application? Well, first of all, you need to think about what you're using it for. So for example, let's say you have a VMware configuration where you have multiple virtual servers with VMware on them, and you need boot volumes. Well, in that case, you would use block storage. If you have workloads such as transactional databases or relational databases that require very low latency and high performance, you would choose block storage. In situations where you have a mix of structured and unstructured data, for example, a web hosting server where you have both text files as well as media files, then you would choose file storage. And then if you have a collaborative space where you need to have multiple users accessing it all at one time, working together, doing reads and writes all at the same time, you would choose file storage. So, like I mentioned in the beginning, block and file storage are very traditional types of storage. They're not as flashy and shiny and exciting as some of the new storage services that have entered the market, but they are still very relevant and useful for the different types of workloads that you have, whether it's on-premise or in the cloud. Thanks for checking out this video on the differences between file and block storage with me today. If you have any questions or comments or ideas for other videos, just put something in the comments below, and then if you'd like to see more videos like this in the future, subscribe.
In the next video, we'll start to look at object storage. In this video, we're going to start to understand what object storage is, how data is stored in object storage, and how it differs from the more traditional storage types such as file and block storage. The first thing to note about object storage is that you do not connect it to a particular compute node in order to use it. Instead, you provision an object storage service instance and use an API, or Application Program Interface, to upload, download, and manage your data. This means you can directly use object storage with anything that you can call an API, and you don't need an underlying compute node. The second thing to note about object storage is that it's less expensive than other cloud storage options. Its per gigabyte cost is typically a couple of US cents per month, and in some cases, even less, depending on the storage tier used. More on storage tiers later. The third and possibly most important thing to note about object storage is that it's effectively infinite. With file and block storage, you specify the size of the storage you want in gigabytes or terabytes, and then pay a fee based on the size you provisioned. With object storage, you just consume the storage you need and pay per gigabyte cost for what you use. You can keep uploading files, and the storage will never run out. So when would you use object storage? Well, object storage is great for storing large amounts of unstructured data. By unstructured, this means that the data is not stored in any kind of hierarchical folder or directory structure. Object storage uses buckets, and objects are stored within these buckets in a structurally flat way. A bucket is a bit like a folder, in the sense that you can give them meaningful names, and of course have different buckets for different object types, but you cannot place a bucket within a bucket. When an object is placed in a bucket, it also has some metadata, data about the data, added to it, such as an object ID. This metadata helps applications to both locate and access the object, as well as provide information on the time that the data was stored or last accessed. When you create a bucket, you don't need to provide or define any sizing information. The bucket will just hold the data that you place inside it, and the service provider ensures that there is sufficient storage capacity available. Buckets can hold as little as a few bytes of data, right up to multiple petabytes, and you can build up the amount of data stored as slowly or quickly as you like, as well as shrink it back down again. The service provider also takes care of resilience and making sure that the object storage solution is highly available. Some cloud providers offer different types of buckets within different levels of resilience. For example, they offer buckets which are resilient, but the data is only stored in one data center. This is a good option where data needs to reside in a particular geographical location, or in situations where high availability is less of an issue. They will then offer buckets which are highly available across regions, where the data is stored multiple times in different data centers or zones in the same region or even in multiple regions. These options usually cost more, but they provide both the highest level of resilience as well as availability for your data. Object storage has a very flat storage structure, which we'll explain in the next lesson. This data can be anything from text files to audio files and video files, from IoT data to virtual machine images, from backup files to data archives. Pretty much any data which is static and where fast read and write speeds are not necessary would make a good fit for object storage. Object storage would, however, not be suitable for running operating systems, nor applications such as databases or anything else where the contents of the files changes. So, to summarize what we have learned in this lesson, object storage is used to store files, or objects, which are static. The data that you can store using object storage can be anything from text files to audio and video files, from IoT data to virtual machine images, from backup files to data archives. You cannot run operating systems or other applications, such as databases, using object storage. Objects are stored in buckets. You can have multiple buckets, but you cannot place buckets within buckets. You do not need to specify a size for a bucket. You can just use as little or as much space as you need. Many providers offer different types of buckets with different charges for each. Some are based on resilience and availability, while others are based on the frequency at which the objects inside are accessed. In the next video, we'll be diving into object storage data tiers and object storage APIs. In this video, we're going to look more closely at object storage data tiers and object storage APIs. Object storage buckets also have storage tiers, or classes, associated with them, and these tiers are based on how frequently the data is accessed. A standard tier bucket is where you would store objects that are frequently accessed. This tier tends to have the highest per gigabyte cost associated with it. A vault or archive tier is where you might store documents that are only accessed perhaps only once or twice a month or less, and this will be offered at a lower storage cost, whereas there may also be cold vault tier where you would store data that is typically accessed only once or twice a year. This storage often costs just a fraction of a US cent per gigabyte per month. Often, you can also set up automatic archiving rules for your data, meaning that if an object isn't accessed for a period of time, it will automatically be moved to a cheaper storage tier. The rule uses some of the object's metadata to determine when it should be archived. Note that object storage does not come with IOPS options. Object storage tends to be very slow in comparison with file or block storage, where downloads typically take seconds, if not longer, to complete. Where providers offer cold vault buckets, data retrieval from these tiers can sometimes even take hours because the storage is kept offline. If your application needs fast access to files, then object storage may not be a good option. We've mentioned that object storage is priced per gigabyte used, but there can also be other costs related to retrieval of the data. These costs are similarly low, but access charges can be higher for data that is in a vault or cold vault tiers, so it is important to ensure that the data is in the correct tier based on its frequency of access. Object storage does not need to be attached to a compute node for you to access it. Rather, you access object storage through an application program interface, or API. The most common API for object storage is called the S3 API, which is a standard based on the S3 object storage offered by AWS. Many providers offer APIs to their object storage, which is S3 compatible, which is useful because it means developers can write code which is able to access multiple vendors' object storage. The API itself is an HTTP-based RESTful API or RESTful web service. The API call allows applications to manage object storage and buckets as well as put upload, or get, download objects to and from them. Object storage is not just for new applications, but can be used to meet requirements for existing ones. It can also be used as an effective solution for backup and disaster recovery as a replacement for off-site tape-based solutions, reducing the time to restore data. Many backup packages now include the ability to back up data up into the cloud using object storage. Object storage is more efficient than tape backup solutions, which require tapes that need to be physically loaded into and removed from tape drives and moved off-site for geographical redundancy. So, to summarize what we have learned in this lesson, object storage has different tiers, with different charges for each. Some are based on the frequency at which the objects inside are accessed. Object storage is priced per gigabyte of storage used per month, plus some charges for data retrieval. Object storage is much cheaper than file or block storage. Object storage is very slow in comparison with file and block storage. You can often create rules which allow the automatic archiving of objects to cheaper tiers when they are infrequently accessed. Object storage is accessed using an API. Many object storage providers have an S3-compatible API, which means developers can create code that will work against multiple vendor object storage solutions. Object storage in the cloud offers an effective backup and disaster recovery solution. In the next video, we will be covering Content Delivery Network, or CDN, which is driven by block storage. A Content Delivery Network, or CDN, is a distributed server network that delivers temporarily stored or cached copies of website content to users based on the user's geographic location. A CDN stores this content in distributed locations and reduces the distance between your website visitors and your website server. In the rest of the video, we'll learn more about content delivery networks.
Hi, I'm Ryan Sumner. I'm a Chief Network Architect with IBM Cloud, and today I'm going to help you answer what is a content delivery network. So in short, a content delivery network, or CDN, is a service that accelerates internet content delivery. So in other words, the main benefit of a CDN is that it makes your website faster. So before I get into describing to you how it accomplishes that and some of the other benefits, first, I want to talk to you about some of the challenges that we have where we have users all around the world, but we don't have servers all around the world, and the experience that those users have due to that dynamic. So I've got a simple diagram here showing a server hosted down in Dallas. This is my website. And then I have users all around the world. So in Sydney, I might have 5. In London, I've got 5. New York, I might have 10. LA, I might have 10. I've got 30 users around the world that are accessing my server and my website down in Dallas. So let's kind of follow a set of these users in their journey. Let's look at their users down in Sydney. They make a request to the website. They've got an 8,600-mile hike to Dallas and then an 8,600-mile hike back. The amount of time that that takes is usually measured in milliseconds, and just that round trip might be about 170 milliseconds. For our users up in London, that might be about 100 milliseconds. Our users in New York City can probably experience about a 40 millisecond round trip time, and over in LA, about 30. So as you can see, the further you're away, the longer it takes, ultimately, the slower the website will be for you. So this is where the CDN comes into play, and this is how it actually accomplishes the increase in speed, which is by reducing the amount of distance between the user and the content, or the server providing the content. So what it does by doing that is it places these content delivery network endpoints in as many locations around the world as possible, and in our case, we're going to assume we've got one in just about every location where our users exist. So now when the user in Sydney or London or New York City or LA tries to access some content, it's first retrieved by the Content Delivery Network service and then distributed around the world. So we have a single request down to the Dallas server. It's now then distributed all around the world, and our users in London now, instead of going all the way to Dallas, they're able to retrieve that content directly from their closest geographical location, drastically reducing the amount of time that it takes to retrieve that content. So as you can see here, it's very basic how a CDN is able to provide the benefits of to the end user by reducing the amount of time that it takes to deliver the service. But what you're not seeing here is an indirect benefit is the reduction in the amount of traffic that actually hits the Dallas server. So the indirect benefit is that you actually see a reduction in the load or a reduction in the amount of capacity that you need in Dallas to serve all these users. So another indirect benefit, because of there's just much less validity and so much less stuff happening in Dallas, because all these users aren't having to make these trips, and I'm also not having to communicate with users so far away, the Dallas environment may also see an increase in uptime. And then lastly, because the users are not really directly communicating with the servers down in Dallas, you have the indirect benefit of an increase in security through obscurity. So it's pretty basic to understand how a CDN works, in the end, to provide a better benefit to the end user.
Welcome to Cloud Storage Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss the factors for selecting cloud storage. Can you talk about some of the factors you consider while deciding on the most appropriate cloud storage for your needs?
So when I'm looking to get cloud storage for my projects, I'm looking at three main things. First, how much is it going to cost me? Second, what is the speed of data input-output from the storage? And third, how long is it going to be available to me?
Storage can actually be quite complicated. Often you have to use different types of storages. But the first question you need to ask is, what is the storage being used for? How fast does it need to be? How many people are using it? How often? Very important to consider how much is it going to cost. And cost can actually be tricky because it's not only the amount of storage you use, but often how often and how much you access it. So I would say really understand what you need to use this storage for, and then factor in all those different things into your answer. And it'll hopefully help lead you to the right storage or multiple storages you need to use to solve your problem.
So factors to consider when deciding on your cloud storage needs include cost, performance, security, and operational ease of use.
When you're deciding on cloud storage, you're typically deciding between file, block, and object storage. File storage will have the interface that's most familiar to most people. It's essentially a file system, just like the one that you have on your local computer. It supports multiple clients mounting it for concurrent access, and that's typically been the reason that I've went with it in the times that I have. Block storage does not support concurrent access, but it has very low latency, and it's typically the storage of choice for performance-intensive applications like databases. Object storage, on the other hand, tends to be the go-to for when you have large, unstructured data that is not modified very often. So, for example, large data sets, video files, database backups, that kind of thing.
Storage can be characterized a number of ways, depending on the type of storage. One type is object storage. A second type is block storage, file storage such as NFS, or database storage, SQL or NoSQL services.
Now, there are different classes of storage or categories of storage that you can get on cloud computing. If I'm working with an application and I want to store end user data or some sort of configuration, then I'm looking at cloud object storage. So cloud object storage, while slow, gives me this unlimited space or buckets that I can create within the cloud object store. If I'm looking for a little bit faster, where speed is of importance, for example, storage for a database, then I might look at block level storage. This storage works on fiber networks, and so it's a little bit faster than working off of the internet, like in cloud object storage. And then there's the third category is the file storage. The downside of file storage is it's a little bit slower than block storage. However, because file storage is mounted on a certain server, I'm able to use it as a common storage for multiple applications and for multiple servers on my end.
With object storage, you may get nice and low cost, but you might not get the highest or the lowest latency, because with object storage, every time you're updating a tiny amount of a file, you're just updating, let's say, one letter of a file. You have to update the whole object, and so you're paying for all of that updating, and you're also you also have to wait for that entire object to be updated. Whereas if you have file storage, you are able to make insertions in the data, and usually that file storage is attached more closely to your actual compute, and you can get much lower latency that way. And then another type of storage is block storage, and you can, in the cloud, choose block storage optimized virtual machines that have extremely low latency between the block storage and the server. So for extreme low latency, that can be a great solution.
So some of the considerations here are security and encryption. I mean, ideally, you're looking for data to be encrypted at rest and in flight. Some other factors to consider include data access frequency, from very active with low latency to less frequent to infrequent or cold storage, or even archive for long-term storage. Another factor is cost. I mean, more frequent access and lower latency is generally going to be more expensive, those services. And business requirements, that data is perhaps immutable or protected such that it cannot be modified or deleted. And another is data lifecycle and how to automate policies to retain, move, archive, or delete old data.
And then some cloud provider is actually coming out right now with a storage area network, so that you can have a whole bunch of block storage as one storage area network that you can access from your cloud virtual machines. Another thing to consider is, what are the encryption options? So fortunately, most storage solutions in the cloud right now have the ability to encrypt your storage, but you want to make sure that that's a feature. And then another option is content delivery network. And for content delivery networks, that is an option if you want to have media, for example, stored as close to your end user as possible, so that when they load your website and look at the images, those are loaded in an instant, because the media is replicated across all the areas.
Hybrid cloud, as we covered in the previous lesson, is a computing environment that connects an organization's on-premise private cloud and third-party public cloud into a single infrastructure for running the organization's applications. Multi-cloud is a cloud adoption strategy that embraces a mix of cloud models from different service providers, public, private, and managed, across infrastructure, platform, or software services. For example, A business may consume email as a service from one provider, a CRM application from another, and infrastructure from yet another provider. So essentially, a hybrid multi-cloud implies you're able to leverage the best of cloud models and services across different service providers, and have your applications and workloads working seamlessly across multiple different clouds. In this video, we will look at some use cases for why a business may want to use a hybrid multi-cloud approach.
In this video, I want to touch on a few of those use cases for why a business may want to use hybrid or multi-cloud. Let's start with the basic one, cloud scaling. Now, most of us are probably familiar with this. It's one of the main reasons for adopting the cloud. Now, let's say we have a flower delivery service that is able to hit a certain bottom line of users. They have on-premise infrastructure, and it can hit a certain amount of user load. So visualizing this here throughout a calendar year, you can imagine that their load maybe goes up and down in response to specific holidays. Now, to hit those peaks, they could scale up their on-premise architecture, but that's met with upfront costs and costs of upkeep. Now, instead, what they'll instead do is take advantage of cloud. That allows them to scale up in response to that load and then automatically deprovision resources when they no longer need them. Now, this concept is kind of general to cloud computing, not just hybrid or multi-cloud. But that brings me to my next topic. And here, we're going to be talking about how it can be used to build a composite cloud. So essentially, this is going to be applications that are spread across multiple cloud environments. So back to the flower delivery service, let's say they have on-premise architecture that allows them to run 3 major components of their app. So let's say they have the web UI, they have some billing APIs, as well as a rewards framework. Now, let's say that this service is actually based in EU, and their European customers are happy. But for their North American or American customers, specifically around Veterans Day or Thanksgiving, they're noticing that the system is bogging down. And so they decide to take advantage of a hybrid cloud or multi-cloud architecture by composing their application across multiple cloud environments. So they'll take advantage of data centers in America, and essentially they've identified that although the rewards framework can stay on-prem in their European side, they want to move the billing and the UI capabilities over. So they'll move just those two to a cloud platform of their choice in a North American or American data center. This kind of allows them to scale up portions in response to, say, American holidays while keeping their EU portions individually scaled. So in this example, the flower delivery service is able to take advantage of scaling at a global level by using the hybrid or multi-cloud architecture. Next, let's talk about the airline or travel industry. So we can first start with an example of modernization. Now, in the past, we've seen that reservation systems may have been difficult to work with, or you might have had to call in, but almost all the airline companies now have a mobile application. So most of the time, and we've actually found that it's about, in general, not just in the travel industry, but 80% of all enterprise applications are actually still on-prem. And that's likely the case in this industry as well. So in this specific example, let's say they have a reservation system that's running on-prem. But to create new experiences for their end users, let's say they've created a mobile application. That mobile app, of course, has a mobile backend that's maybe running in a public cloud. And that in turn works with the reservation service. So again, the mobile app can hit the mobile backend, and that in turn works with the reservation capabilities. So in this case, they've modernized and new user experiences are possible. But let's take that a step further. Now, a source for a lot of dissatisfaction for users is whenever their flights are delayed. So when a flight is delayed, they may have to rebook new flights. The solution is almost always the same. The traveler wants to get to his destination in the easiest way possible. So what airline industries have been doing is taking advantage of the cloud to create maybe a recommendation feature. So it allows them to book new flights as soon as a delay is recommended or as soon as a delay is incurred. And that's going to connect up to that mobile backend service, allowing users to be able to book flights through their phone the second a flight is delayed. This not only improves the bottom line for the airline industry, but leads to happier users. So that's one way the modernization has been done. Next, let's take it even a step further and talk about data and AI. For data and AI, the airline industry has been taking advantage of lots of historical data. So over the decades that a company has been around, let's say they have historical data of when unplanned maintenance has happened on their airline. In fact, 30% of all delay time in the airline industry is actually when unplanned maintenance happens. So by taking advantage of, let's say, machine learning or AI capabilities, they could hook into all of the legacy data that they have, large volumes, and connect them up to machine learning and AI capabilities. This allows airline industries to take advantage of predictive analytics and get insights before errors or before the unplanned maintenance ever occurs. This again improves their bottom line, leading to happier users and a more efficient airline industry. Now, today we talked about 4 major use cases for hybrid and multi-cloud platforms. So cloud scaling and composite cloud in the Flower delivery service, as well as modernize and data and AI for the airline industry.
Another reason for adopting hybrid multi-cloud strategy is to prevent lock-in to a specific vendor's cloud platform and having flexibility of being able to move workloads from one cloud platform to another as the need arises. In the next video, we will understand what a microservices architecture is, its features, benefits, and use cases. Microservices architecture is an approach in which a single application is composed of many loosely coupled and independently deployable smaller components or services. These services typically have their own stack running on their own containers. They communicate with one another over a combination of APIs, event streaming, and message brokers. For a business, what this means is that application components can be developed and updated more efficiently by multiple developers working independently. Teams can use different stacks and runtime environments for different components. Components facing too much load can be scaled independently, reducing the waste and cost associated with having to scale entire applications. In this video, we'll look at how microservices have shaped application development and also look at a use case that illustrates microservices in action.
The way developers work to build applications is changing. In the past, software was built as large monolithic applications, where a team of developers would take months to construct a large application built on a common code base. These developers would write every part of the application from start to finish. Now, after decades of software development, there are vast amounts of code already out there that developers can use as the base of an application, meaning they no longer have to create every line of code from scratch. Cloud development platforms provide developers with an ecosystem of code that can be easily and securely integrated into applications. Now, instead of building one huge application on one team, developers break into small, independent teams where they write smaller amounts of code called microservices. Microservices break down large applications into their core functions. For example, search, recommendations, customer ratings, or product catalogs. Each is developed independently of one another, yet work together on the cloud development platform to create a functioning application. A container is the distribution method for each microservice, meaning it delivers the code where it needs to go. Containers are plug and play, so if one microservice isn't working for an application, developers can take it out and put in a different one without disrupting how the rest of the app functions. Check out microservices in action with Ron. Ron is a soccer fan who uses an online streaming media service called Dream Game. Last night, he missed watching his team play their crucial semi-final match. Luckily, he can watch the match tonight on Dream Game. When he logs in, he sees the most popular content among all Dream Game users. After some searching, He finds the match he's looking for. What he would really like is to find his game with one click. Luckily, the Dream Game development team is using microservices to develop a better user experience for viewers like Ron. The first microservice is a content catalog, housing the millions of games that Dream Game offers. The small team of developers organizes each piece of content with metadata that describes them. This metadata feeds into a second microservice, the search function, which ensures that Ron's search results are captured and compared to the Dream Game catalog. The third microservice, recommendations, captures data about the most popular content among all Dream Game users. This is what generates the homepage that Ron saw when he first logged in. These three microservices are all in their separate containers, ready to join the application. But before they can work together, they have to find one another. They do this by using something called service discovery, which creates a roadmap for these and many other microservices to communicate. When microservices find each other, they communicate using an application programming interface, or an API. So when Ron searches for his favorite soccer team, the search microservice is communicating to the content catalog, in an API, about what Ron is looking for. Now back to the goal at hand, to get Ron to his soccer game with just one click. The development team working on the recommendations microservice is updating the code, adding an analytics algorithm. Using analytics, the recommendations microservice will compare Ron's viewing history and preferences to popular content among other users, including soccer fans and viewers in Ron's geographical region and demographic. Since the developers didn't need to create the code from scratch, they are able to deploy this new functionality in a matter of days. These updates happen behind the scenes as the rest of the microservice containers function normally. The next time Ron checks Dream Game, instead of just seeing the most popular or newest content, he sees a personalized playlist that will continue to refine itself as the system learns more about his viewing habits and preferences. The result? Ron finds his favorite team's latest game right away. The microservice approach lets developers quickly innovate applications in parallel, and lets users like Ron focus on the things that really interest them. And when those interests are changing and growing faster every day, microservices help businesses keep up and grow with their customers.
Serverless is an approach to computing that offloads responsibility for common infrastructure management tasks, such as scaling, scheduling, patching, and provisioning application stacks to cloud providers, allowing developers to focus their time and effort on the code and business logic specific to their applications or process. Serverless doesn't mean there are no servers, only that the management of the underlying physical or virtual servers is removed from their users. The serverless computing environment allocates resources as needed for the applications. Let's look at some key attributes that distinguish serverless computing from other compute models. The serverless model requires no provisioning of servers, installation of application stacks and software, or operation of the infrastructure by the developer. Serverless computing runs code only on demand on a per-request basis, scaling transparently with the number of requests being served. Serverless enables end users to pay only for resources being used, never paying for idle capacity, which is unlike virtual servers on the cloud, where end users pay for VMs as long as they are running, even if idle. Effectively, serverless abstracts the infrastructure away from developers. Code is executed as individual functions, where each function runs inside a stateless container. No prior execution context is required to serve a request, and with each new request, a new instance of the function is invoked. Let's look at a scenario. You could, for example, have a serverless platform between the front end of your website and your storage layer running individual functions. The serverless app could be translating text files and storing it in a cloud-based storage service. Using the front end of your website, you send text files to a serverless app. The app creates translations in different languages, and then stores these translated files in a cloud storage, and sends you their links back to you. Some of the key serverless computing services today include IBM Cloud Functions, which is based on Apache OpenWhisk, AWS Lambda, and Microsoft Azure Functions. It is important to note that serverless may not be the best fit for all applications or scenarios. You need to evaluate application characteristics and ensure that the application is aligned to serverless architecture patterns. Applications that qualify for a serverless architecture include some of the following characteristics: short-running stateless functions, seconds or minutes; seasonal workloads with varying off-peak and peaks; production volumetric data that shows too much idle time; event-based processing or asynchronous request processing for implementing use cases; microservices that can be built as functions that are stateless. Serverless architectures are well suited for use cases around data and event processing, IoT, microservices, and mobile backends. Given its inherent and automatic scaling, rapid provisioning, and a pricing model that does not change for idle time, supporting microservices architecture has become one of the most common use cases of serverless computing today. Serverless is well suited to working with structured text, audio, image, and video data around tasks such as data enrichment, transformation, validation and cleansing, PDF processing, audio normalization, thumbnail generation, and video transcoding. Parallel tasks such as data search and processing and genome processing are also well suited to be run on a serverless runtime. Serverless is also well suited for working with all sorts of data stream ingestions, including business data streams, IoT sensor data, log data, and financial market data. And finally, let's look at some challenges worth considering about serverless. Serverless workloads are designed to scale up and down in response to workload. But for workloads characterized by long-running processes, managing a traditional server environment might be simpler and more cost-effective. The serverless application architecture can be vendor-dependent, and so there is a potential for vendor lock-in, particularly involving platform capabilities such as authentication, scaling, monitoring, or configuration management. Because serverless architectures scale up and down in response to workload, they also sometimes need to start up from zero to serve a new request. For certain applications, this delay isn't much of an impact, but for something like a low-latency financial application, this delay wouldn't be acceptable. Simply put, a cloud-native application is an application developed from the outset to work only in the cloud environment, or an existing app that has been refactored and reconfigured with cloud-native principles. A cloud-native application consists of microservices working together as a whole to comprise an application, yet each can be independently scaled and iterated through automation and orchestration processes. These microservices are often packaged in containers, which are executable units of software in which the application code is packaged along with its libraries and dependencies so that it can be run from anywhere. The independence enables frequent iterative improvement of cloud-native applications without disrupting the experience of end users. Cloud-native applications are unlike traditional or monolithic applications that are built out of one huge piece of software. Applications that tightly couple the user interface, business logic layer, and data layer. Let's take the example of how a cloud-native application might be used on a travel website. Each topic covered by the site, flights, hotels, cars, specials, is its own microservice. Each microservice may roll out new features independent of the other microservices. Specials and discounts can also scale out independently. While the travel site is presented to customers as a whole, each microservice remains independent and can be scaled or updated as needed without affecting other services. Whether creating a new cloud-native application or modernizing an existing application, developers adhere to a consistent set of development principles. Follow the microservices architecture approach by breaking applications down to single-function microservices. Rely on containers for maximum flexibility, scalability, and portability. Adopt agile methods that speed the creation and improvement process through quick iterative updates based on user feedback. In this video, we'll take a closer look at the key concepts of cloud native, its benefits, and use cases.
Hi, I'm Andrea Crawford and I'm with IBM Cloud. So today we're going to talk about cloud native apps. In the heritage world, we have our lumpy, monolithic apps. And in the new world, we have our microservices living on the cloud. If we take a look at this diagram here, we see we have cloud infrastructure. This is your private, your public, and your enterprise infrastructure. Cloud native apps apply to hybrid and multi-cloud situations. We also have our scheduling and orchestration layer. This layer is all about control planes like our Kubernetes. We also have our application and data services layer. This layer is all about backing services and being able to integrate our application code with existing services that may be available on other clouds or even on-premise. We have our application runtimes. These are what were traditionally or conventionally known as middleware. And over here, well, that's where we have our cloud native apps. This is the sweet spot right up here. So our application code is actually designed, built, and delivered very differently for cloud native than it would be for conventional monolithic lumpy apps over here. So let's talk a little bit about why cloud native apps can actually leverage benefits like enabling innovation, business agility, and most importantly, from a technology perspective, the commoditization of this solution stack over here. So as time has progressed and technologies have matured and emerged, a lot of the services are actually being refactored lower down in this stack. This means that core services are starting to have a lower center of gravity, freeing up innovation at this level over here. So what are our use cases for when to build a cloud native app? Star everything. Everything that lives in the cloud should have a cloud native app design and approach. This means our application code needs to be instrumented with things like standardized logging, standardized events, and being able to match those logging and events to a standard catalog that multiple microservices and cloud native apps can use. The last thing we want to do is have our development squads have to figure out what their log and event messages should be. Let's standardize that because we want to be able to commoditize that as well. We also need to have things like distributed tracing. When we get over into the microservices world over here, we have a lot of moving parts. This means we're going to need to leverage services core to the system like load balancing, service discovery, and routing. These are the kinds of things that are commoditized in this layer here with things like Istio and with the emergence of newer projects like Knative. And so, if we were to recognize the benefits for cloud native apps and to sum it all up, we are all about enterprise and engineering at scale.
In the next video, we'll take a look at DevOps. Development teams need to design, develop, deliver, and run software as reliably and efficiently as possible. Operations teams need to identify and resolve problems as soon as possible by monitoring, predicting failure, managing the environment, and fixing issues. Combining development and operations with the ability to monitor and analyze and optimize bottlenecks gives us DevOps, a collaborative approach where business owners and the development, operations, and quality assurance teams collaborate to continuously deliver software. A DevOps approach applies agile and lean thinking principles to all stakeholders in an organization who develop, operate, or benefit from the business's software systems, including customers, suppliers, partners. By extending lean principles across the software supply chain, DevOps capabilities improve productivity through accelerated customer feedback cycles, unified measurements and collaboration across an enterprise, and reduced overhead, duplication, and rework. Using the DevOps approach, developers can produce software in short iterations on a continuous delivery schedule of new features and bug fixes in rapid cycles. And businesses can seize market opportunities and reduce time to include customer feedback in their products. The DevOps process involves continuous delivery, which is about delivering small, well-designed, high-quality increments of software to customers. Continuous integration, creating packaged builds of the code changes released as immutable images, where immutable implies that when modifications are needed, the entire component is replaced with an upgraded version. Continuous deployment, which involves progressing each new packaged build through the deployment lifecycle as rapidly as possible. Continuous monitoring, with tools that help developers understand the performance and availability of their applications even before they are deployed to production. Delivery pipeline, which is an automated sequence of steps that involves the stages of ideation, coding, building, deploying, managing, and continuous improvement, which loops back to the ideation phase in the delivery pipeline. While DevOps can apply to applications anywhere, there is especially a compelling case for DevOps when it comes to cloud-ready and cloud-native applications. With its near limitless compute power and available data and application services, cloud computing platforms come with their own risks and challenges. DevOps tools, practices, and processes are helping tackle some of the complexities and challenges posed by the cloud and allowing solutions to be delivered quickly and reliably. Let's look at some core capabilities that DevOps provides to help building and running applications in the cloud a lot more manageable. DevOps best practices make it possible to programmatically provision servers, build middleware, install application code, and fully automate the installation process in a way that is documented, repeatable, verifiable, and traceable. Application deployments often involve considerable complexity. The DevOps practices of continuous integration and continuous deployment help create a fully automated deployment pipeline, which is important all through the application development lifecycle. Cloud-native applications form a complex, distributed system with multiple moving parts, independent tech stacks, and rapid release cycles. DevOps principles are essential to define how people work together to build, deploy, and manage applications in a cloud-native approach. With the DevOps best practices of automated provisioning and continuous deployment, developers, quality professionals, and other stakeholders can test in low-cost, production-like test environments that were previously not available, enhancing both productivity and quality. When systems are compromised or struggling to recover from natural disasters, DevOps best practices make it possible to rebuild these systems quickly and reliably. DevOps provides a powerful set of principles, practices, and tools to realize the full potential of cloud-native computing, as well as for modernizing existing applications to leverage cloud benefits. Many organizations have huge investments in existing applications that are often siloed in legacy systems and are very difficult and expensive to update and maintain. Modernizing these applications can unlock great benefits for these organizations, such as accelerating their digital transformations, enabling them to take advantage of new technologies and services, and becoming more responsive to their customers' needs and changing market dynamics. Cloud computing is one of the 3 main ingredients in application modernization. In the rest of this video, we will see how and what else application modernization entails.
Hi, I'm Eric Minnick with IBM Cloud, and I want to talk about application modernization and 3 huge transformations that have been going on together. So we've got 3 things going on, they're interrelated, and this is what we're seeing, this change in how we're doing architecture, infrastructure, and our ways of working, how we deliver. And if we go back in time a little bit, we saw applications that were very monolithic. They were running on physical servers, and we used waterfall style development where we'd have long plans and we'd say, okay, this is going to be our planning phase, our development phase, our testing phase, and we could plan out a year as a project. And that's really what we've gone away from. So if we look at how most organizations are working today, architecturally, they've got some sort of distributed architecture. It's usually related to like a service-oriented architecture, the big buzzwords a few years ago. But it's some sort of distributed architecture. We have a bunch of web services, they're talking to each other, we got some databases on the back end, and then some front ends that kind of go through all that. On an infrastructure level, they're running on some sort of a virtual machine, right? So we said, we could probably do better than having to order a new server every time we have a new service. Let's virtualize this stuff. And we need a little more density along the way. And from a way of working, agile development, pretty normal. And then trying to figure out a little bit of what happens downstream. So this kind of takes us up to where a lot of teams are today, but not really where they're going. And so if we look at kind of that next phase, we're taking another pass at this service-oriented architecture and really shrinking the sizes of the services, taking advantage of the more dynamic infrastructure we have. And we're calling these now microservices, right? Microservices. So we got a microservice architecture. So very small, very focused services, moving away from a lot of the heavyweight XML-based communication we saw in SOA, towards more REST-based communication, things like that. But same idea, let's keep breaking into smaller and smaller pieces. We have more independence of what we ship, more rigor in saying, this service needs to be independent from another service so I can change these things by themselves. On the infrastructure side, cloud. Cloud's pretty popular. And this could be public cloud. This could also be private cloud. I'm painting with a very broad brush when I say cloud here. And then from a delivery and a way of working, we could say that DevOps is really key. And I would include in this approaches like site reliability engineering, SRE. More the ways of working we have today. Now, that's fine and interesting, but what do these things have to do with each other? And I'd argue that what we're really seeing is modernization in how the applications are delivered and how they're built, what they are. And while you could walk into any large enterprise today and you'll find someone who says, we are going through a cloud transformation. And you'll often find someone who says, yes, I'm in charge of leading the DevOps transformation. And you'll walk into enterprise architecture and they'll say, yes, we are pushing microservice architectures. Individuals think that they're going through 3 separate transformations, but they're really tied, right? If I'm doing microservices, right, and I have new microservices all the time, and in order to get a new microservice up and running, I'm over here and I have to order a new physical server and then rack and stack it a couple months later, I'm not going to get any time to market benefits. The resilience benefits that I'm going to normally look for from microservices are going to be modest at best. Right? Microservices want cloud infrastructure. You want to be able to say, I've got a new microservice. Let me put it in a container and just run that container right now and scale that dynamically. Similarly, cloud really likes running microservices. Right? The benefits of being able to dynamically scale are really cool when you have a lot of small things that you might need few of or a lot of. It's not as interesting when I've got a monolith that isn't even distributed. How do I scale that? I get a bigger cloud server? And then all of this is kind of baking in this idea of speed and resiliency. And DevOps brings that together, right? The developers who have always wanted speed, the operations people who've always wanted that resiliency, they're going to be programming that cloud, right? The programmable infrastructure that cloud provides needs operations people who understand resiliency, but bring some of that development skill in. And to really take advantage of these new infrastructures, the new architectures, you need these new ways of working. And you also are going to say, if this is going to give me time to market benefits, I can't be back here and say, yeah, no, we've got a one-year project plan that we're just going to execute. I need to be able to be more agile and adapt in my planning and my responsiveness to the business. I need to better wire up my applications so they can be more easily monitored and more resilient. We have to have the application in a way that it knows when one of these services is failing and we can spin up another. So this is really, for me, fascinating, that you walk into these organizations everywhere and they're undergoing these 3 different transformations, but they're always doing them together. And when they don't, it doesn't quite work. So you've got these 3 transformations going on at once. And you'll hear us talk a lot about application modernization, right? See that written across the top here. And when I think of application modernization, I think it's just this. It's this transformation right here. Going from these kind of monoliths or service-oriented architectures to microservices, adopting cloud, modernizing our ways of working towards DevOps and SRE. That's AppMod, right? And it's a really exciting time, and it's really great when you're able to go after it in a holistic fashion.
Welcome to Cloud Computing Emerging Trends and Technologies Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss trends and technologies in cloud computing.
The top 3 trends that I see coming in the next couple of years are as follows. First is this idea of a hybrid cloud. As IBM has predicted, a lot of companies and clients will move from a single cloud provider to multiple cloud providers. That could be multiple public clouds or a public cloud and on-premise private cloud. Second, I see this big surge of edge computing becoming more prominent in cloud computing. Now, the terms may seem quite different from each other and disjointed, but in many sense, the cloud computing will go on the edge. The numbers state that quite overwhelmingly. There's 75 billion devices that are supposed to come up online by 2075. And the edge computing, in order to be able to communicate between devices and back to the server, is going to be very crucial. And lastly, it's the usage of machine learning and artificial intelligence to make decisions for us in the cloud computing space. So these are my top 3 trends that I see coming in the next couple of years.
So one of the emerging trends in cloud computing is serverless. And that's the area of cloud computing where all you need to do is give the cloud your application logic. And that means you don't need to patch any servers, you don't need to manage the high availability of your infrastructure, you don't have to put in multiple availability zones. The cloud provider takes care of all of those operational issues for you, and all you do is give it the code, and it runs it on demand. So every time you have an event triggered, let's say it's a voice assistant, and every time you talk to it, it triggers a cloud function. That's what serverless is. And so developers love it because with serverless, you don't need to do all the undifferentiated work, the work that does not make your app unique. You can focus on the logic that makes your app unique.
So in terms of emerging technologies, one of the big ones is cloud native architecture. And that includes the trend towards microservices, basically dividing up monolithic applications, what would have been monolithic legacy applications, into granular microservices. And this affords a whole range of advantages. Another one is containers and container orchestration systems, and most notably the Docker and Kubernetes technologies. Another is serverless services, where some functional code can be spun up with very low latency without the need to manage any virtual servers. The term cloud native architecture really encompasses some combination of all of these. In terms of emerging trends,
so I'd like to discuss a couple trends I see all the time in cloud computing right now. First of all, we have serverless computing, and that's the idea that you don't have to worry about anything other than writing the code for your application. You don't need to know, are you deploying Kubernetes? Do you need to know IP addresses? Is this Linux? Nothing. And I really see this as the future, because you don't want to have to worry about how it's deployed, managing RAM, managing CPU, any of that stuff. You just want to create code. And the easier that it is to get your code from written to deployed and running well, the better, and it's a win for everybody.
Another area that's emerging in cloud technology is DevOps. And with DevOps, you have the developers a lot more integrated with operations. So you've got a CI/CD pipeline where the developers can push their own code and see it live on the servers or the serverless functions. And that, DevOps is a term that has a lot of different definitions. One definition I've enjoyed hearing is that it means the developers are talking with operations and vice versa, that there's a dialogue going on, and it's not just how it was in the past where the developers hand over the code, but the developers really see the life cycle through to it being maintained in production.
In terms of emerging trends, we're seeing comprehensive cloud services for building data pipelines, data science in general, and artificial intelligence services. And specifically, we're seeing, low-level AI services to build AI solutions from the ground up, along with higher-level pre-trained AI solutions for things like image recognition, speech applications, just to name a few. Another whole area of advancement is in the area of cybersecurity. It's obvious that cybersecurity is something that we have to be constantly aware of and improving all the time. And we're seeing a constant stream of improvements to secure your network perimeter, compute resources, and data in the cloud.
Another emerging trend in cloud computing is application modernization. So with cloud providers coming out with all these amazing services that do a lot of things for you, the companies are thinking, wait a second, the cloud provider is doing certain features of our application better than we are. And instead of continuing to maintain that part of our application ourselves, let's rewrite the application to take advantage of these cloud native services. For example, there are services now that do transcription or image recognition. And rather than have your own inference and training servers that you manage, and you use open source, machine learning models that you host, and you train those models on data that you give it. Don't do any of that. Just drop the images in a image recognition service of a cloud provider, and you're not managing any service. You just get the data.
Welcome to What is Cloud Security Part 1. Today, organizations are moving towards digital transformation with the introduction of cloud computing. They are changing their infrastructure and incorporating cloud-based tools and technologies. This transition to cloud-based environments can have several adverse consequences. If cloud-based technologies are not used securely, the organizations can be subjected to external threats that can be a danger to their business security. Thus, to gain the maximum benefit, enterprises when using interconnected cloud technologies require the best cloud security procedures and technology. A cloud computing environment offers different as-a-service models that enable organizations to offload many time-consuming IT-related tasks. Examples are Infrastructure as a Service, IaaS, Platform as a Service, PaaS, and Software as a Service, SaaS, computing models. However, while using these services, organizations may encounter many challenges related to data security. Although third-party cloud computing providers follow security best practices and ensure the integrity of their servers, data asset management is still the responsibility of the organization availing these services. With the evolution of cloud computing environment, security threats have also become more advanced. These threats target cloud computing providers because of a lack of transparency in the data movement and access across the cloud. Thus, organizations need to be compliant and have the right approvals when managing client data stored on the cloud. A successful deployment of the cloud infrastructure is dependent on the countermeasures to secure against modern-day cyber attacks. You should have adequate cloud security solutions in all cloud environments, whether they are private, public, or hybrid, to ensure business continuity and security. Identifying the right cloud security solution requires various considerations. Let's discuss them. First is lack of visibility in a public cloud environment. It is difficult to keep track of who is accessing your data and which cloud service they are using outside your organization. Second is multi-tenancy in a public cloud environment. Multiple client infrastructures might be hosted by the same cloud computing provider. Your services might get compromised by malicious attackers when targeting other businesses. Another challenge is access management and shadow IT. You may find it difficult to restrict unfiltered access to your services from any device and geolocation in a cloud environment. Finally, misconfigurations of assets are also accountable for breached records in a cloud environment. They include inappropriate privacy settings or retaining default administrative passwords. Next, let's discuss some evolving threats and risks in cloud computing. Insider threats are caused by current or former employees, business partners, contractors, or anyone who has had access to systems or networks in the past. They can at any time abuse their access permissions. This category of threats is invisible to external security systems and thus are more dangerous. Another prevalent attack on the cloud computing system is distribute denial of service, DDoS. A DDoS attack targets the server on the enterprise by overloading it with traffic from multiple synchronized systems. The attack works through Simple Network Management Protocol, SNMP, used for modems, printers, switches, routers, and servers. The cloud faces another critical risk, and that is data breach. A breach can be due to a leak in the cloud security measures used by your organization. Malicious users may gain access to sensitive data and misuse the information. A breach can cost the organization a financial and reputation loss. Now, let's understand the different security models used in cloud computing. A shared responsibility model is a cloud security framework where the organization hands off certain IT security responsibilities to the cloud computing provider. Each party, the cloud provider and the user, are accountable for different aspects of the security, and they work together for the full security coverage. There are different types of shared security models for IaaS, PaaS, and SaaS. In IaaS, the provider looks after the physical security of the infrastructure at their data centers. IaaS users are responsible for the security of the software, including the OS required to run their applications and their data. In PaaS, the provider secures the platform, including the OS, user subscriptions and login credentials, but the user is responsible for the security of any code or data or other content produced on the platform. However, in SaaS, the provider is responsible for almost every aspect of security, including underlying infrastructure, service application, and the data the application produces. Users still have some security responsibilities, such as protection of login credentials. Welcome to What is Cloud Security Part 2. Organizations are migrating their workload to a hybrid cloud environment, increasing the threat attack surface. This expansion can result in new data security and compliance challenges. Thus, you require a robust, data-centric cybersecurity program to protect your data. In addition, you require centralized visibility and monitoring against unauthorized access, exposure, or data theft across your enterprise data environment. Let's discuss some data security capabilities that you can implement to protect your data. To secure data, you can improve maturity across people, process, and technology. Identify your most critical data assets, who has access to them, and how they are protected. You can prevent data loss by detecting, preventing, and enforcing policy violations to avoid accidental data loss. Implement data security governance by establishing process, metrics, and continuous steady-state data discovery and classification. In addition, it is critical to monitor database security by enforcing data protection and compliance policies across hybrid cloud environments. Your next focus in a cloud environment should be the management of access controls and authentication. You need to develop cloud identity and access management, IAM, strategies that provide and work on zero-trust architecture, risk protection, and constantly authenticate any user to any resource. An organization should consider the following points while building the IBM cloud. Modernize at your own pace, matching your business requirements. Retain your existing investments and on-premises applications while slowly inducting the right cloud IAM architecture to complement or replace your framework. Establish a zero-trust implementation that will provide a centralized access control, preserve client confidentiality, reduce insider threats, and secure your remote resources. Zero-trust model and plan use an environment that securely connects the right users to the right data at the right time, under the right conditions, while also protecting your organization from cyber threats. Enable scalability for your cloud IAM for millions of users or transactions without a major modification of the infrastructure. Another element of cloud security is cloud network security, which refers to the security measures, technology, policies, controls, and processes used to protect data on public, private, and hybrid cloud networks. There are many security implications when you extend your network to a cloud environment. To meet modern network security requirements, organizations need to deploy and manage network security built directly on the cloud. The benefits of cloud network security are centralized security monitoring and management, easy management and updating of granular policies, real-time detection and powerful prevention against intrusions, DDoS, and other web-based attacks, automated configuration and management, helping to eliminate misconfiguration errors and maintain control over traffic, encryption services to protect data at rest and in transit, centralized protection and management of identity and access. Let's summarize the best practices you can follow for cloud security. There are some critical steps under 3 phases that you can follow. First is identifying your cloud usage state and risks. Second is protecting your cloud system. And third is responding to attacks. The first phase comprises identifying how your data is accessed, detecting unknown cloud usage, checking your configurations for cloud services, monitoring for signs of malicious usage of cloud data. In the second phase, you can protect your cloud system by assigning protection policies, encrypting sensitive data, formulating policies for data sharing, restricting data sharing to unknown devices, implementing a bot protection and mitigation solution, using a proper anti-malware solution. The third phase offers best practices for responding to attacks and attempts to attack. Add additional authentication and verification steps for high-risk access scenarios. Add new policies for new cloud services. The National Institute of Standards and Technology, NIST, has made a list of best practices and principles that establish a secure and sustainable cloud computing framework. These principles are NIST's 5 pillars of cybersecurity framework: identify, protect, detect, respond, and recover. Another emerging technology in cloud security that supports cybersecurity framework is Cloud Security Posture Management, CSPM. CSPM solutions are designed to address a common error in many cloud environments, that is, misconfigurations. CPSM also addresses issues by helping in the deployment of the core components of cloud security. They include Identity and Access Management, IAM, Regulatory Compliance Management, Traffic Monitoring, Threat Response, Risk Mitigation, and Digital Asset Management. The colossal increase in cloud adoption across the cyber world will motivate cybercriminals to target organizations in the cloud environment. Although organizations are taking adequate security measures, they are still vulnerable to cyber attacks. The current major trend in cloud security includes multi-cloud strategies such as cybersecurity mesh, zero-trust security models, hybrid and multi-cloud environment, cloud-native tools and applications, deployment of DevSecOps, securing remote workforces, and AI and machine learning for threat detection. The focus is on privacy and data protection regulations.
According to the Cloud Security Report by Cybersecurity Insiders, the top cloud security concern of cybersecurity professionals is data loss and leakage. Unauthorized access through misuse of employee credentials and improper access controls is the single biggest perceived vulnerability to cloud security, followed by insecure interfaces and APIs. In this video, we will look at how identity and access management, also known as access control, works as the first line of defense, allowing you to authenticate and authorize users and provide user-specific access to cloud resources, services, and applications. A comprehensive security strategy needs to encompass the security needs of a wide audience, including organizational users, internet and social-based users, third-party business partner organizations, and vendors. There are 3 main types of users: administrative users, developer users, and application users. Administrative users include cloud platform administrators, operators, and managers, roles that typically create, update, and delete application and service instances, and also need insight into their team members' activities. An attacker on an administrative account can steal data from production database service instances, deploy malicious applications inside the customer's domain, or even deface or destroy existing applications. Developer users include cloud application developers, platform developers, and application publishers. Developer users are authorized to read sensitive information and to create, update, and delete applications. The third type of user is the application user. These are the users of the cloud-hosted applications. Let's look at the key components of identity and access management and how they work. Authentication, or the identity service, enables applications deployed to the cloud to authenticate users at an application level, based on a range of identity providers such as the Cloud Directory, social identity providers such as Google, LinkedIn, Facebook, and Twitter, enterprise-hosted identity provider, and cloud-hosted identity provider. Sometimes API keys, or unique identifiers, are passed into an API to identify the calling application or user. Multi-factor authentication is used to combat identity theft by adding an additional layer of authentication for application users, such as single-use passwords or PINs, certificates, tokens, risk-based authentication, such as changes in the user's location, past activity, and preferences. Cloud Directory services are used to securely manage user profiles and their associated credentials and password policy inside a cloud environment. A directory service within a cloud means that applications hosted on the cloud do not need to use their own user repository. Reporting helps provide a user-centric view of access to resources or a resource-centric view of access by users. Reports typically give information about which users have access to which resources, which users have changes in access rights, which access is being exploited by each user, and under which conditions. Audit and compliance is a critical service within Identity and Access Management framework, both for cloud provider and cloud consumer. Auditors use these processes to validate implemented controls against an organization's security policy, industry compliance, and risk policies, and to report deviations. User and Service Access Management capability enables cloud application and service owners to provision and deprovision customer, partner, and vendor user profiles with minimal human interaction. This streamlines access control based on the role, organization, and access policies defined by the owner. User accounts of administrators or developers give access to sensitive information. In order to mitigate the risks of these accounts being hacked into, you require maximum control over the whole lifecycle of these users. Some of the controls that can help secure these sensitive accounts include provisioning users by specifying roles on resources for each user, password policies that control the usage of special characters, minimum password lengths, and other similar settings, multi-factor authentication like time-based one-time passwords, and immediate deprovisioning of access when users leave or change roles. Cloud providers offer identity access and management services, typically including the ability to create access groups, add users to access groups, and manage access for existing users. An access group is a group of users and service IDs created so that the same access can be assigned to all entities within the group with one or more access policies. Access policies define how users, service IDs, and access groups in the account are given permission to access account resources. Policies include a subject, which can be users, service IDs, or access groups, a target, which is the resource or provision service offering to which you want to provide access, and role, which defines the actions allowed on the target of the policy, that is, the resource to which the access is being granted. Access groups provide a more streamlined access assignment process as compared to assigning individual access to each user and help reduce the number of policies in an account. In this video, we learned how identity and access management work as the first line of defense to secure the cloud. Given the concerns around data security and privacy, especially in public cloud environments, encryption plays a key role and is often referred to as the last line of defense in a layered security model. This protection not only encrypts data, but also provides robust data access control, key management, and certificate management. In this video, we will take a closer look at cloud encryption. Encryption is defined as scrambling data in a way that makes it illegible. There are two parts to an encryption system, the encryption algorithm and the decryption key. The encryption algorithm defines the rules by which data will be transformed so that it becomes illegible, and the decryption key defines how the encrypted data will be transformed back to legible data. Encryption ensures that only authorized users have access to sensitive data, and when accessed or intercepted without authorization, data is unreadable and meaningless. Cloud providers offer various cloud encryption services. This could be limited encryption of data that is identified as sensitive, or end-to-end encryption of all data uploaded to the cloud. Data is encrypted upon receipt, and encryption keys are passed to the customers to decrypt data when needed. Keys need to be managed securely. If you lose your keys, you will not be able to read your data. Data needs protection in 3 states: at rest, in transit, and when it is in use. Encryption at rest protects data while it is physically stored in a database or the storage layer. Depending on the application and business requirements, there could be multiple options for encrypting data at rest, such as encryption for block and file storage, built-in encryption in object storage, and database encryption services. Encryption in transit protects data while it is transmitted from one location to another. Encryption in transit includes encrypting the data before transmission, authenticating endpoints, and decrypting and verifying data on arrival. Secure Sockets Layer, or SSL, and Transport Layer Security, TLS, are commonly used protocols for encryption in transit. They are not only used when accessing websites securely, but also for data moving between servers and services within the cloud. Encryption in use protects data when it is in use in memory for computations. It allows computations to be performed on encrypted text without needing to decrypt the data. Cloud storage encryption could be server-side or client-side. Server-side encryption occurs after cloud storage receives your data, but before the data is written to disk and stored. For server-side encryption, you can either create and manage your own encryption keys, known as customer-supplied encryption keys, or you can generate and manage your encryption keys using key management services offered by the cloud storage provider, known as customer-managed encryption keys. Client-side encryption occurs before data is sent to cloud storage. This way, users can utilize encryption keys and algorithms that are not visible to the cloud provider, making it virtually impossible for cloud providers to decrypt hosted data. Given that a majority of enterprises today operate in multi-cloud environments, there is a need to implement a singular data protection strategy across an enterprise on-premise, hybrid, and multi-cloud deployments. Some cloud providers offer multi-cloud data encryption services with a range of features such as data access management, integrated key management, and sophisticated encryption that combine to deliver the scalability and flexibility to help protect the most sensitive workloads across the enterprise, regardless of where the data resides. Using a multi-cloud data encryption console, you can define and manage access policies, create, rotate, and manage encryption keys, and aggregate access logs. Encryption does not eliminate data security risk. It separates the security risk from the data itself by moving security to the encryption keys. These keys need to be managed and protected against threats in order to keep the data secure. Key management services offered by some cloud providers help perform lifecycle management for encryption keys that are used in cloud services or customer-built applications. They enable customers to encrypt sensitive data at rest and to easily create and manage the entire lifecycle of cryptographic keys that are used to encrypt data. Since the keys remain in possession of the customer, the data is protected from cloud service providers as well as from other users. Some of the best practices for encryption key management include storing encryption keys separately from the encrypted data, taking key backups off-site and auditing them regularly, refreshing the keys periodically, implementing multi-factor authentication for both the master and recovery keys. Cloud-based deployments can be complex. Monitoring performance across an entire stack of applications and services can be time-consuming and draining on internal resources. This is where cloud monitoring solutions come in. Cloud monitoring solutions assess data, application, and infrastructure behaviors for performance, resource allocation, network availability, compliance, and security risks and threats. Cloud monitoring is not just about automated tools. It includes the strategies, practices, and processes that need to be in place for analyzing, tracking, and managing cloud-based services and applications. It also serves to provide actionable insights that can help improve availability and user experience. Cloud monitoring helps to accelerate the diagnosis and resolution of performance incidences, control the cost of your monitoring infrastructure, mitigate the impact of abnormal situations with proactive notifications. Get critical Kubernetes and container insights for dynamic microservice monitoring. Troubleshoot your application and infrastructure. Cloud monitoring solutions are designed to give organizations visibility and control over their entire cloud-based infrastructure. They provide data in real time with round-the-clock monitoring of virtual machines, services, databases, and applications. Multi-layer visibility into application, user, and file access behavior across all cloud-based applications and services. Advanced reporting and auditing capabilities for ensuring regulatory standards are being met. Large-scale performance monitoring integrations across multi-cloud and hybrid cloud environments. One way to categorize cloud monitoring tools solutions is to break them down into infrastructure, database, and application performance monitoring. Infrastructure monitoring tools help identify minor and large-scale hardware failures and security gaps so that the developers and administrators can take corrective action before problems affect user experience. Database monitoring tools help track processes, queries, and availability of services to ensure the accuracy and reliability of database management systems. Application Performance Monitoring, or APM, measures application availability and performance, providing tools needed to troubleshoot issues in an application's environment. APM solutions help improve user experience, meet application and user service level agreements, or SLAs, minimize downtime, and lower overall operational costs. To get the most benefit from your cloud-based deployments, you can follow some standard cloud monitoring best practices. Leverage end-user experience monitoring solutions to capture the performance of an application from the point of view of its end users. These solutions monitor user journeys to track parameters such as application response time and frequency of use under varied conditions. These insights will help you to improve customer experience significantly. Consider moving all aspects of your infrastructure, whether in private, public, or hybrid clouds, under one unified monitoring platform. This can help you to manage all your KPIs in one place with complete visibility into performance optimization. Use monitoring tools that can help you track the usage and cost of your cloud resources and services. Increase cloud monitoring automation. This can help you gain significant operational efficiencies. Simulate outages and breach scenarios to evaluate how well your monitoring tools capture and alert against failures. Cloud monitoring needs to be a priority for organizations looking to leverage the benefits of cloud technologies. It will help you manage and optimize your cloud resources for cost and performance and create better customer experiences. In this video, we will look at some case studies that demonstrate the use of cloud computing in real business scenarios and the ensuing impact on these businesses and the customers they serve.
The weather company's mission is to map the atmosphere of the Earth and based on that generate the most accurate and hyper-local forecast which can be served out to all our consumers and devices, which number in millions across the globe.
Weather is unpredictable, and we need to be able to spin up and spin down as fast as weather happens.
Our normal day-to-day load is 30 million unique users, and when we peak into severe weather, that can go north of 100 million across our products.
So we generate forecasts on demand, and our forecast on demand system is responsible for generating forecasts at a resolution of 1 square kilometer grid.
We deliver forecasts on demand to the tune of 250 billion per day.
On the backside of that is our API platform, and that system operates at the scale of about 150,000 requests per second. If our products don't work and don't work fast, people's lives are in danger.
Imagine a hurricane is approaching east coast of the United States. As it is approaching the coast, usage of my weather data goes up tremendously. It can go up from anywhere from 2 times to 5 times.
It took us 6 months to migrate into IBM Kubernetes from our previous provider, and what we've noticed is some real efficiencies with DevOps. It's reduced our workflow and pipeline by about 80%.
With the latest hurricane, we were able to scale with IBM Cloud very easily, very seamlessly. IBM's Kubernetes service allows us to scale as fast as the weather happens.
As we migrated our web platform to IBM Cloud Kubernetes services, one of the biggest advantages is that this is a managed service,
which allows our team not to have to babysit our system, enables them to do other work.
With the migration to IBM Cloud Kubernetes, we've gained the ability to have automation, security baked in. This was a feature and a component that was very manual for us in the past.
IBM's security team proactively now notifies us of any security vulnerabilities.
The tools and the investment that the company's made gives us capabilities that we would have never had before. It gets us very excited, and it gives our developers and engineers opportunities to build new things that they wouldn't have otherwise been able to do. The global reach that IBM and the IBM Cloud, together with our technology, with our capabilities for forecasting, give us the ability to extend our products and services to keep people safe all over the world.
Good afternoon, ladies and gentlemen. Welcome aboard. Captain speaking. Pretty much anticipating on-time arrival.
In the scenario where there's a flight cancellation or some other off-schedule operation, we've had a system where we find new seats and flights availability for those customers. But I think oftentimes customers didn't necessarily know that that was the best option for them. What we wanted to do was create a system where they could actually see alternate options.
The goal was to facilitate a better experience for our customers on how to get to their destination in an automated fashion on the channel of their choice. In our business, hurricanes, storms, other natural events impact our customers on a fairly regular basis. What happened, and this is a true story, the hurricanes hit, and everybody said, this is ridiculous. Our customers were being impacted by the hurricanes immediately. Why are we mitigating risk of a traditional rollout when we have the power of the cloud? And this is exactly the scenario that our customers need this capability.
I think people now realize that these kind of activities and integration are much easier when we can use cloud technology, and especially microservices, we can break problems into much smaller problems, and those get much easier to wrap your head around and develop.
This is the technology that we need to be adopting now in order to keep pace with our customer expectations.
What I loved about my job at Cementos Pacasmayo is that it challenges me every single day. Technology moves so agile that I have to keep up with it. And what I love is that the company is also on that same road, driving towards its digital transformations. Our customers are now demanding quicker time to market and also a more broad portfolio of products. We need to keep up and deliver like the best service and the best products that they can get in the least amount of time. We implemented SAP S/4HANA on IBM Cloud since it brings us a cost-effective infrastructure and also it's quite scalable. Cementos Pacasmayo is now turning from a product-driven company to a service-driven company. The accounting area now has real insights on real time of our financial statements that they didn't used to have. And also on our supply chain area, especially on the procurement. They now have the dashboard that helps them take decisions right on time.
My name is Mukesh Sharma, and I'm the Senior Manager of IT at Welch Food. Welch's started as an organization 150 years ago, and pretty fast it became the national drink. We're owned by the farmers. It's a co-op. and we value the sweat equity our farmers put into it. So that's what drives us every day, that our farmers are working out on the farms, and we are working here to make sure the organization gives the best benefit of each dollar spent back to them. Welch's IT is the heart of the business. All the manufacturing systems, any manufacturing data which comes in through different processing, ERP systems, and you name it. So we started this journey with the private cloud, and then at the same time, we have started the process of asking ourselves on any new application request, can it be run in the public cloud? The approach we have taken is slowly and steadily start to move these non-mission critical systems, which can be done better by somebody else, let them run outside, let them spend time on it while we spend time on our core values.
Liquid Power is a company that sells products that when you inject them into crude oil or gasoline pipelines, it changes the flow characteristics to such a point that you can either, one, increase the flow of those fluids, or secondly, use less energy to actually push the fluids down the pipeline. We needed to become a standalone company under Berkshire Hathaway. Without any experience in running our own infrastructure, or SAP, we had to come up with the solution that was best for our business to operate as a standalone company. So there were many decisions we had to make. Do we go cloud? Do we stay on premise? How do we create our own infrastructure and back office? And what's the best decision for us, not only today and now, but in the future going forward? So I talked to some CIOs and IT professionals. If you had a blank sheet of paper, what would you do? Cloud or go on premise? Without a doubt, all of them say cloud. This whole process and the migration to the cloud is giving what we believe is a competitive advantage. And what I really love about having IBM with SAP on the cloud is it's scalable. We can do it much faster and change in a much faster time period than we could otherwise.
Cloud computing is a key part of an enterprise's digital transformation strategy. As more and more companies are moving critical business processes and applications to a mix of cloud infrastructures, qualified cloud computing professionals are in high demand. With a compound annual growth rate of 14.1%, Grand View Research estimates that the cloud computing market will reach a revenue of $1,554.94 billion in 2030. Employer demand is outpacing the number of qualified candidates available. Gartner Talent Neuron's database of more than 1 billion unique job listings scores the hiring scale for jobs requiring cloud computing skills at 78, which means employers are finding it difficult to get the right applicants for open positions in cloud technologies. There are many specialization areas within this domain. Here's a look at some of the common roles available currently. 1. Cloud developers, or cloud software engineers, work through all phases of the software development lifecycle, writing, testing, and maintaining the code. They work with the front and back end of applications, as well as platforms and systems that their applications run on. Cloud developers need to have a mix of technical skills, business knowledge, and experience with at least one of the major cloud providers. Technical skill for a cloud developer would typically include knowledge of data structures, distributed systems, operating systems, and algorithms. Experience with databases. Proficiency in commonly used web application development languages, such as Python, JavaScript, Java, HTML, and CSS. 2. Cloud integration specialists are responsible for integrating new cloud services, applications, and infrastructure into the organization's portfolio of internal systems and existing cloud services. These specialists assess the implications and trade-offs between different solutions as they relate to the integration between external and internal systems, optimize integration and user experience, and ensure that performance standards adhere to service-level agreements set with the enterprise. 3. Cloud data engineers are responsible for designing, developing, and deploying scalable data pipelines and data services. They look at integrating new data management technologies and software engineering tools into existing infrastructure. Their responsibilities include understanding existing systems to recommend automated integration of disparate data sets, collaborating with data scientists and researchers to develop predictive models and proofs of concept, promoting best practices that enable teams to accelerate their consumption and understanding of data, improving overall efficiency by introducing new engineering processes and tools. 4. Cloud security engineers provide expertise around the systems and processes needed to protect the confidentiality, integrity, and availability of an organization's systems and application data. They determine security requirements, plan, implement, and test security systems, perform threat simulations to detect possible risks, recommend innovative technologies that will enhance the security of cloud-based environments. Cloud security engineers need to have deep knowledge of cloud platforms and services, software design patterns, and DevOps tools and methodologies. 5. Cloud DevOps engineers collaborate with development and operations teams to create reliable and rapid release pipelines for software and updates. This may typically involve creating custom automation tools, building and maintaining configuration and deployment frameworks, tracking design bugs and automating the debugging process for developers, maintaining and deploying web-based applications, monitoring security issues, measuring performance against expected business outcomes. Containerization expertise is increasingly a must-have for DevOps engineers. 6. Cloud solutions architects work to translate business requirements into application architecture and design. Some of the technical skills as required for a cloud architect role include deep knowledge of cloud platforms and services, deep understanding of software design patterns, knowledge of DevOps tools and methodologies, good understanding of networking, a high-level understanding of key security concepts. Solution architects work closely with cloud developers, networking specialists, security engineers, integration specialists, and DevOps engineers to architect and design solutions. There are several resources available for learning cloud technologies in a variety of delivery methods, including instructor-led courses, self-paced online courses, online videos, books, and also technology-focused community forums. Many cloud providers have dedicated learning portals with extensive resources available on the complete range of cloud technologies and services they provide. They offer learning paths, which make resources available as per specific career roles, hands-on learning labs with interactive learning resources that can be filtered by role, level, or product, free trials on their suite of products and services. Welcome to Job Market for Cloud Computing Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss the job market and the nature of opportunities available in cloud computing for people aspiring to get into this field. They will also discuss what they foresee as the future of opportunities in this field.
With more companies adopting some sort of cloud and becoming more cloud aware, there is no lack of opportunities for aspiring software developers. You could get into this field as a cloud architect, where you're thinking about how to architect applications, which, by the way, look a lot different than if you were developing applications, monolith applications on a single server, versus developing applications for the distributed cloud. So that is a very prominent role. Another role could be that of a data engineer, where you're looking at building pipelines for data to flow from the source databases and other storage into perhaps data science models that are deployed at scale on cloud. Another very important role is that of a cloud security engineer. And in that role, it'll be your responsibility to see that all of the different layers of your cloud are secure for your developers and your end users.
So there are so many opportunities for people thinking about getting into cloud computing. You'd be surprised how many companies are still not in the cloud. And it's very clear that they're all going to go to the cloud eventually, because it's just so much better for so many reasons that we've talked about. And there is not enough talent right now to fill all of that demand, and that demand will just keep coming. And really, there are so many things to know about the cloud. One person can't know them all. So if you just learn one or two things about the cloud really well, you're already going to be really valuable to some company. Let's say you just know a storage service and one compute service really well, or even just decently. That is really valuable to many companies. And if you're just getting started, I would recommend get a certification. I had zero experience in the cloud, and I got a certification. And by getting that cloud certification, I was instantly more visible to recruiters, and I got a job. And so if you don't have the experience on your resume, start off by getting a certification.
Depending on your area of interest, you can get into different fields under cloud computing. If you like programming, you can be a cloud application developer. You should have knowledge of front-end and back-end technologies like Python, Java, Angular, React, etc. It would also require you to have database skills in relational databases like SQL and MySQL, as well as NoSQL databases like Hadoop, MongoDB, etc. There is a rapidly increased demand for machine learning and artificial intelligence. You need to have good understanding of machine learning concepts and should have the ability to handle and process big data. You can choose the career path of being a big data scientist, machine learning engineer. There is also need for cloud professionals with specialization in cloud security skills. These professionals should understand cloud security and also leverage the cloud security tools offered by organizations. Another opportunity for cloud computing is in the area of DevOps. DevOps engineer will need understanding of DevOps tools like Docker, Kubernetes, GitHub, etc. They should also focus on understanding the CI/CD pipeline and automating the process of development and deployment.
Suffice it to say, there are a myriad of career paths in the cloud technology space, including professional career path options for people with and without a BS degree or a non-technical college degree. Companies cannot find enough trained people in cloud technology, so opportunities and demand are definitely out there. In addition, companies are focusing on training their current employees, both reskilling and upskilling to meet this demand internally. So Coursera is committed to helping people without college degrees or people that are making career changes to access these job opportunities that exist in cloud technology.
Welcome to your Career in Cloud Computing Expert Viewpoints. In this video, we will listen to several cloud application professionals discuss career opportunities in cloud computing. For example, cloud developer, architect, SRE, or networking specialist.
First of all, the cloud native landscape is very diverse and it's very intimidating. So when you see the Cloud Native Computing Foundation map of different layers and different solutions in each layer, it can get quite scary very fast. So my first advice to anybody entering cloud computing field would be to really get a solid foundation and understanding of the basics. How is developing for cloud different than developing something on your laptop or on a single server or a small cluster? So think about how you would architect your application differently for the cloud computing world. How would you split it up into smaller services that talk to each other instead of creating a big monolith? And why does that matter?
So if you want a job in a cloud-related profession, I would realize for the first part that almost all the tools that the actual professionals use are available. Many are open source and many have free versions just out there on the internet. So I think the most important thing is just go and get your hands dirty. Use the tools that the professionals use. Start learning. There's so much free education out there and so many resources in the internet, quite frankly, to get you almost all the way there. But reading only gets so far. So use the tools, run the code, create the code, do whatever you need to do. And honestly, if you start creating projects, that's going to be one of the most attractive things to a recruiter, in my personal opinion.
I think it's really important to never stop learning and to always apply what you learn to projects, whether they're at home, at work, or at school.
My second advice to beginners would be to try different cloud platforms and see how an application is approached or architected in these different platforms. You can learn a lot by looking at different architectures.
To start a career in cloud-related professions, start learning on your own from different sources. You can start by learning basic cloud concepts. Learn about the various career opportunities that cloud computing has to offer. Once you know which profession interests you the most, enroll in a specialized course for the same. Get hands-on knowledge by creating some projects on your own and hosting them on your GitHub repository. Once you are confident of your skills, it is always a good idea to get certified. Keep yourself informed about the different opportunities in companies and keep applying.
The advice I would give to someone who's thinking about a career as a cloud architect is, if you don't have any years of experience, just get a certification to start out with, or get a few. You'll instantly become validated in front of recruiters. And even if you don't have the battle experience of making mistakes yourself in production, you will be able to understand the high level of the services and then get into the weeds when the time comes. One thing you gotta be comfortable with cloud development is learning all the time, because all the services are changing all the time, and you can't be an expert at anything really, because it's changing all the time. So be comfortable with all the ambiguity.
Here are a couple of suggestions for you. One is to get certified from one or more of the cloud providers, IBM, AWS, Microsoft, or Google Cloud. And to do that, I would recommend taking advantage of cost-effective online courses like those offered by Coursera to assure that you gain the knowledge you need to both pass the certification exam and to perform the job that you're after and succeed in your cloud journey. And then I would recommend augmenting your certification with some hands-on experience, either obtained on the job or by taking advantage of guided projects on Coursera, or even experimenting with your own hands-on projects. In the case of Coursera guided projects, they're designed to provide you with hands-on experience with some skill in approximately 2 hours.
And try things out in the cloud. So just get your hands dirty and spin up a virtual machine in the cloud, spin up a function, write a function, make it go to a queue, which goes to another function. Just try hooking things up together in the cloud. And one more thing about the career advice. Once you get your cloud certification, put that on LinkedIn, because recruiters search for cloud certifications, and that's pretty much a guaranteed interview for you.
And my final advice would be always ready to skill up. This landscape in this cloud native world changes really fast, and you have to be on your toes and always learning new things and new technologies and frameworks.
Welcome to this course, where you'll learn HTML, CSS, and JavaScript essentials. First, let's meet Michelle Saltoon.
I'm Michelle Saltoon, and I'll be one of your instructors throughout this course to teach you the fundamental skills you need to develop web applications. According to the U.S. Bureau of Labor Statistics, the overall employment of web developers is projected to grow 30% from 2021 to 2031. Which is significantly faster than the average for all occupations. Web developers are in high demand across a variety of industries, from e-commerce stores to education platforms. With more and more people working remotely in our increasingly contactless world, this will continue to be a huge growth area.
In the first module, you'll delve into hypertext markup language, HTML, an essential for every website. First, you'll explore the history and purpose of HTML. You'll learn to use HTML features to build flexible and interactive websites. Then, advance your knowledge by learning about the HTML Document Object Model, or DOM tree, how HTML uses APIs, and how you can use browser scripting for extended functionality. Then, explore cascading style sheets, referred to as CSS, and learn how you can use CSS to format HTML elements. You'll also learn to differentiate among some of the many CSS frameworks. You'll then learn about the basic structural elements of HTML5 and the attributes of HTML5 input elements. Next, gain essential JavaScript programming knowledge. You'll begin by learning basic JavaScript syntax and identifying common DOM objects. You'll also learn about controlling the flow of a JavaScript application using control statements. Then, explore variables, custom objects, functions, and prototypes. Tie your HTML and JavaScript knowledge together when you learn about using client-side JavaScript with HTML. You will discover how JavaScript integrates with the DOM, explore common APIs used in JavaScript applications, and learn how to modify the inline object styles and attributes. Gain the advantage of experience when seasoned professionals share their recommendations for working with HTML and HTML5, and their best practice recommendations for using JavaScript. Let's meet your course experts.
My name is Bradley Steinfeld, and I'm a senior full-stack developer.
Hello, everybody. My name is Carl Litter, and I'm a senior product manager.
My name is James Reeve, and I'm a full-stack software engineer at IBM.
I'm Dennis Harvey. I'm a content strategy manager at Coursera focused on cloud technology.
Hi, my name is Rupinder, and I work as a Chief Solutions Architect at Skillup Technologies.
My name is Daniel Rudnitsky, and I'm a full-stack software engineer at IBM.
Hi, I'm Jan Stoneman. I'm a solution architect at Smartronix.
In addition to module-level activities and labs, you will practice your new skills and build your portfolio with labs where you will edit HTML to correct errors, add missing tags, and modify CSS to improve a web application's look and feel. Then, grow your skills with a lab where you'll write JavaScript code to implement a simple interest calculator and a lab where you will test a web application. To complete this course, you will complete a final peer-reviewed project related to building a single-page portfolio website and evaluate your peer submissions. While you're finishing up the course, consider publishing your portfolio at GitHub Pages, which you'll find at pages.github.com. Next, learn if this course is right for you.
This course is designed for everyone. It doesn't matter if you have a background as a developer. Whether you're an IT person looking to develop new skills, a fresh graduate looking to make a career in cloud or web development, or someone who's never touched programming in their lives, this course will equip you with everything you need to get started. So, absorb the videos, reinforce your learning with the quizzes, and use the discussion forums to talk with your peers and your classmates. Finally, make sure you complete the hands-on portion of this class throughout the course and start building a portfolio to demonstrate to future employers. Congratulations on embarking on this exciting journey, and good luck.
Hello, and welcome to Introduction to HTML. After watching this video, you will be able to explain what Hypertext Markup Language, or HTML, and HTML5 is, and list the objectives of HTML5. The core HTML specification includes this background information. HTML stands for Hypertext Markup Language, which can be thought of as the language of the Internet. It is a markup language that was originally designed for sharing scientific documents. Adaptations to HTML over the years have made it suitable to describe a number of other types of documents that can be displayed as web pages on the internet. HTML elements are the building blocks of an HTML page. The pieces of content that form the page are assigned labels, such as paragraph, list, and table. They are represented by tags. Browsers do not display the tags, but use them to render the content. HTML has been in continuous evolution since it was introduced to the Internet in the early 1990s by CERN, the European Organization for Nuclear Research, and the IETF, Internet Engineering Task Force. The World Wide Web Consortium, or W3C, made a number of recommendations to the HTML standards over the years. New features were continually added, and specifications changed over time. Initially, the Web Hypertext Application Technology Working Group, or WHAT-WG, worked on recommendations independently. Then, in 2007, W3C formed a working group chartered to work with the WHAT-WG on the development of the HTML5 specification. The W3C published the specification under the W3C copyright, while a version with a less restrictive license was kept on the WHAT-WG site. Since 2007, both the W3C and the WHAT-WG groups work together on the development of the HTML5 standard. The HTML5 specification, as drafted by the W3C, includes the following objectives. The HTML5 specification defines a single language called HTML5 that can be written in HTML or XML syntax. The HTML5 specification defines a processing model that can interoperate with earlier HTML implementations. HTML5 improves the markup for documents. HTML5 includes markup and APIs for idioms such as web storage, video, and audio content. When speaking about creating web pages, developers may use the terms HTML and HTML5 interchangeably. In general, the term HTML implies HTML5. Use the full term HTML5 if you need to differentiate between versions, such as when discussing features new to HTML5. In this course, HTML refers to HTML5 unless specified otherwise. In this video, you learned HTML stands for Hypertext Markup Language, a markup language that enables documents to be displayed as web pages on the Internet. Tags represent the elements of an HTML page like paragraphs, lists, and tables. HTML5, the latest version, supports pages written in HTML or XML syntax, interoperation with earlier HTML versions, markup and APIs for web storage, video, and audio content. Hello and welcome to HTML Features. After watching this video, you will be able to list some of the features of HTML5, describe the Document Object Model or DOM tree, explain when you would use XML and when you would use HTML. So, what are some HTML5 features? It provides the means to categorize web pages into different sections and includes tools for effective data management, drawing, video, and audio. Facilitates the development of cross-browser applications for the web and portable devices. Allows greater flexibility, permitting the development of exciting and interactive websites. Helps to create a more engaging user experience. Pages that are designed by using HTML5 can provide an experience similar to desktop applications. Allows for enhanced multiple platform development by combining the capability of an application programming interface, or API. By using HTML5, developers can create a modern application experience that is uniform across platforms and devices. Here is an example of a document that conforms to the syntax of HTML5. Documents that have the text or HTML media type are parsed using HTML rules. If a document is transmitted with an HTML content type, such as text or HTML, it is processed as an HTML document by web browsers. This example uses the following elements. The exclamation point doc type is a declaration tag that represents the document type. The exclamation point doc type declaration is not an HTML tag. It is an instructional to the web browser about what version of HTML the page is written in. Although this declaration is not required, it should be the first line of the HTML code if the developer decides to include it. The HTML tag is the root element of this tree. It contains all of the other HTML elements except the exclamation doc type tag. This example contains two elements, head and body. The head tag contains a title tag, which contains the text sample page in the example. The head element can contain the following tags: title, scripts, style, style sheet links, meta information, browser support information, and other initialization functions. Finally, the body tag contains all content that is displayed on the web page. HTML user agents, commonly known as browsers, parse the markup, turning it into a DOM, or Document Object Model, tree. A DOM tree is an in-memory representation of a document. DOM trees contain several kinds of nodes, which include a doc-type node, elements such as headers and paragraphs, text nodes, and comment nodes. Here is an example of a document that conforms to the XML syntax of HTML5. Extensible Markup Language, or XML documents, look similar to HTML documents, except they have an XML tag on the first line. In addition, with XML documents, the content type must be specified as an XML media type, such as application or XML. When a document is transmitted with an XML content type, it is treated as an XML document by a web browser, and an XML processor parses the document. How do you decide whether to use HTML or XHTML for developing web pages? Which of the two options you choose is related to how you intend to use the application. For instance, are you using XSLT, or Extensible Style Sheet Language Transformations, to create other documents and resources from your web pages? People are equally divided about whether to use XHTML or HTML. Both HTML and XHTML use the same semantic, or tags. However, XHTML tags all need to be in lowercase, while the case used does not matter in HTML. In addition, XHTML must be well-formed. Every element must have an end tag. All attributes must have a value, and double or single quotation marks must surround all attribute values. If an XML parser encounters a situation where the syntax is not well formed, it stops processing. In HTML, different case, unmatched quotation marks, and non-terminated and uncontained elements are allowed and commonplace. In this regard, HTML syntax is less rigorous than XHTML syntax. In this video, you learned that HTML5 includes features for categorizing sections of web pages and managing data, video, and audio tools. Enables you to develop a single cross-browser application for the web and portable devices, and helps you to create a more engaging user experience. The DOM tree is an in-memory representation of a document, and DOM trees contain nodes which define the type of document and its structure, such as headers and paragraphs, text nodes, and comment nodes. Hello, and welcome to HTML Management and Support. After watching this video, you will be able to list some HTML document API properties and methods, describe how scripting is enabled in browsers, Describe browser support for HTML5 features. So let's examine some of the key themes of the HTML5 specification. The syntax it defines is compatible with HTML4 and XHTML1 documents. HTML5 is defined in a way that is compatible with earlier versions in the way browsers handle deployed content. It separates conformance requirements for user agents and authors. In other words, how browsers treat HTML5 code and how page authors treat HTML5 code is different. For user agents, HTML5 is defined in a way that supports elements and attributes of the earlier specifications. For authors, several elements and attributes have been removed in order to simplify the language. HTML5 includes some elements and application programming interfaces that help in the creation of web applications. Examples include video and audio elements and an API that supports the creation of offline applications. What do you think makes HTML suitable for creating web applications? There are a number of possible reasons. The range of devices that all have built-in browsers that support HTML5 features. The number of APIs that enhance the user experience, such as the advanced animation, drawings, audio, and video elements. The efficient use of HTML and CSS while reducing the number of images can lead to faster load times for rendering web pages. Search engine optimizations can use keywords that are taken from HTML attributes to improve the visibility of a website when search results are displayed. The meta tags shown are used to provide information to search engines. Here are some examples of elements in HTML5. New structural elements are part of the HTML5 specification. These markup elements help you to logically define the page structure. New APIs such as Canvas, audio, and video help with graphics and embedded content. New attributes were added to the input element attributes. Examples include the email, date time, and number types. The browser automatically validates the input field according to the input attribute, without the need for custom validation scripts. By using web storage APIs, you can store data in the browser. The Web Workers feature can be used for non-interactive processing. Web Workers provide a way to run processing-intensive tasks without blocking the user interactions to the current page. In this video, you learned about HTML5 themes, which provide syntax compatible with HTML4 and XHTML1, new and refined APIs for video and audio elements, offline web pages, and drag and drop. About HTML5 web applications, which have improved search indexing with meta tags, better page load times, enhanced user experience, and about HTML5 elements, which enable you to define and manage web page structure and content. Welcome to HTML scripting. After watching this video, you will be able to define scripting, explain how browsers enable scripting, and identify DOM tree accessors. The use of scripting within a website, often through the use of JavaScript, can be done directly within your HTML code within the script tag or within a separate file which is called in your HTML code. Scripting provides a more interactive user experience when browsing websites. It can be used for various tasks such as form validation, dynamically changing the content of a website, and manipulating images. Since scripting can be turned off, the recommendation is to use scripting but not to rely on it. Scripting is enabled for a browser context when the conditions shown on the slide are true, the browser in use supports scripting, and the user has scripting enabled. HTML5 also defines a sandboxed media type which specifies an extra set of content restrictions and can be used when hosting untrusted content. This sandboxed browsing content can be set at the page level or specified as an attribute for embedded objects. Running a page that contains an embedded object without the sandbox attribute grants the embedded object the same permissions as the rest of your page. This implicity gives third-party vendors permission to run scripts with the same permissions that you have for that page, which is one way that you can inadvertently allow advertisements to occur in your application. So, to prevent granting implicit permissions to embedded objects, use the sandbox attribute on any tag that contains an embedded object. Each HTML document that is loaded into a browser page becomes a document object. The document object provides access to all HTML elements in a page and can be accessed from within a script. The DOM tree accessors are HTML document APIs that provide access to all the HTML elements on a page. The property to access is prefixed by the word document. For example, document.head returns the first head element that is a child of the HTML element, if there is one, otherwise null. The function document.images returns an HTML collection of the image elements in the document. The function document.scripts returns an HTML collection of the script elements in the document. Here are some common HTML DOM tree methods. The document.getElementById ID function has one required parameter, which is the ID of the element you want to access. The ID is specified as an attribute on one of the elements that is coded elsewhere on the page. The document.getElementsByTagName tag function has one required parameter, which is the tag name of the element you want to access. This function returns a node list of all the elements with the tag that matches the required parameter. This is a fragment of HTML with JavaScript code that uses the document API. When Submit is clicked inside the page that is running in a web browser, the text checker function begins. The document.getElementById text field 1 retrieves the contents of what was typed into the input field that has the ID of text field 1 and places this content into a variable. The JavaScript logic then tests whether any data was typed into the field, and an alert dialog is displayed with the result. A similar function will be used later in exercise 1. Here is the output from running the code on the previous page that uses the document API. The user types test in the input field and clicks submit. The result is seen in an alert dialog box on the same page. In this video, you learned scripting is used to provide a more interactive user experience when browsing websites. Since scripting can be turned off, the recommendation is to use scripting but not to rely on it. Scripting is enabled when certain browser conditions are met. HTML5 sandboxes enable you to manage iframe mashups, web pages that pull content from more than one site. HTML documents loaded into a browser page become document objects, which you can access through scripts. Welcome to HTML5 browser support. After watching this video, you will be able to explain how browsers support HTML5 features, list which browsers support which HTML5 features, and define browser support table. Not all browsers fully support all the features that are described in the HTML5 and CSS3 specifications. For example, older versions of browsers do not support certain features. The developers of different browsers are continually adding support for HTML5 features to their new browser versions. For the most comprehensive support of HTML5 features, consider using Google Chrome. Support tables show which features are supported by which browsers and can be a useful tool when developing web pages. For example, CanIUse.com has great support tables for HTML5, CSS3, and more. Here are the results of displaying the input type equals date element in different browsers. The Google Chrome browser displays a calendar to enter the data. The Microsoft Edge browser displays spinning boxes to enter the data. Notice the difference in date formats. Year, 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 month, month, day, day versus month, month, day, day, year, year, year. The Firefox browser displays the date field as a text field. This could raise several issues regarding input format and validation. This example shows a support table for the input type equals date element. The numbers represent the browser version. The color determines the level of support. Green, full support. Olive, partial support. Red, no support. Edge, Chrome, and Opera browsers are green, meaning they support the input type equals date element. Internet Explorer and Safari browsers are red, meaning they do not support the input type equals date element. Support levels change as developers of browsers add new features, so check back frequently to see if the features you require are supported. You can also use JavaScript to check whether a certain HTML5 element is supported by a browser. First, create a DOM element by typing document.createElement and include the element type as a parameter argument. As a result, the DOM object gets created. If the browser does not support that element, the DOM object that gets created has a set of common properties, but nothing specific for that element. You then test for a known property or method on the DOM object that you created. If that property or method does not exist, then the browser does not yet fully support the DOM element or the HTML5 tag that has been created. Browsers that do not support the element can revert to a fallback or default behavior, such as displaying the field as a regular text field. Here is an example of using JavaScript to check whether a certain HTML5 element is supported by a browser. This code is used to test whether the browser supports the element input type equals date/. In the example, you dynamically create the DOM object for the input element, and then you set the type attribute to the value of date. If the browser does not support the input type equals date, the field is displayed in the browser as a regular text field. In this video, you learned not all browsers fully support all the features that are described in the HTML5 and CSS3 specifications. CanIUse.com has good support tables that show what features are supported by which browsers. You can use JavaScript to check whether a certain HTML5 element is supported by a browser. Welcome to Insider's Viewpoints, working with HTML and CSS. In this video, we will listen to several professionals discuss their experience working with hypertext markup language, or HTML, and cascading style sheets, or CSS.
So a typical challenge when writing in CSS and you're kind of new at it is it can be hard to center an element perfectly in a space, whether it be the whole page or within a box. It can be hard to center things really nicely. It might just be off a little bit. And for that, it was really helpful to learn Flexbox. So I encourage you to give that a shot and understand it and be comfortable with Flexbox.
While working with HTML and CSS, sometimes the main challenge is finding the errors or bugs in your code. It is important to validate your code frequently. You can use an online HTML and CSS validation service to make sure that the code is properly formatted and there is no missing parentheses, incorrect property names, etc. To find out any CSS errors, you can also use developer tools in browser. Another challenge is testing the code on different browsers. Some of the old browsers do not support modern HTML features. Once you have decided on the technologies you would be using, it is a good idea to research the browsers that would support these features. You should also add fallback mechanisms to your HTML code for browsers not supporting the new features. For example, if you're using HTML5 video, you can add a link to download video as a fallback option for browsers that don't support the HTML5 video player.
My answer is going to focus on CSS since it is far more complex than HTML. In my opinion, it's unthinkable to tackle cross-platform CSS without using a framework. So the challenge, becomes then, how do you pick your framework? And here's some ideas. Bootstrap is one of the most popular. It has powerful cross-browser capabilities. There's Foundation. It has a significant learning curve. There's the Materialize framework from Google, which has an optimized feature set that many developers value. There's also UIKit, which is most popular in iOS development.
Welcome to HTML5 Tags and Structural Elements. After watching this video, you will be able to list elements specific to HTML5, describe HTML5 structural elements, section, article, header, footer, figure, and fig caption, and explain the difference between navigation and grouping elements. There are many HTML5 specific elements. The table shows some of them. Notice that the HTML5 element tags have intuitive names, such as audio, that is used to embed sound content, and canvas, that is used for graphical content. Not all of these element tags are covered in this video, so take a moment to read through the table. This table shows more HTML5 elements. The last tag in the table is the comments tag. Comments in HTML can assist the developer to explain what the code does. The browsers do not display these comments unless the viewer views the source. In a division-based layout, each part of a page that you want to format differently is separated into its own division. Think of the natural divisions into which you can divide the page that is shown here. These divisions might include the page title, a banner with selectable tabs, an area for the image, and further blocks for text and thumbnail images. The div tag was not introduced in HTML5, but is a good starting point for laying out a page or document. Then, you can use other HTML5 specific structural elements inside the div tag. Most HTML elements have a semantic meaning. In other words, the element describes either the function or the type of data that is contained within. For example, a P element is a paragraph that usually contains some text. In contrast, the div tag has no innate semantic meaning besides the logical grouping of the content. You can use these dedicated elements to mark up your website rather than using the generic div or span elements. An article defines a block of code that can be distinguished from the rest of the page. A section defines a logical separation in the document, such as the numbered chapters of an online manual. A header element is used to group the headers for a page. The footer defines the area at the bottom of the page. This code example shows some of the HTML5 structural elements. Here, the article element is used to create an online news report. The article includes a header. Within the article, the page is marked up into sections that have their own headers. The page also includes a footer element. The aside tag is used to provide additional information that is related to the main discussion. The aside tag lets you extract and display further content or go to additional resources without detracting from the main discussion. The figure tag defines a self-contained element that is referred to from the main content. The figure element can be used to embed graphics, images, or code sections. The fig caption tag defines the caption for the contents of the figure element. Websites typically have sections that are dedicated to navigational links that go to these sites or for moving between pages of a single application. In HTML5 syntax, these navigational links are placed inside a nav tag. The nav tag is a convenience tag for grouping navigational links in a web page. In this video, you learned tags provide control within an HTML5 document. Some tags provide structural elements. The div tag separates areas in a document into divisions, enabling you to apply different styles to different parts of a document. Dedicated elements like article, section, header, and footer are more specific than the generic div element. The aside, figure, and fig caption tags enable you to group content, and the nav tag enables you to group navigational links. Welcome to HTML5 Input Element Attributes for the Input tag. After watching this video, you will be able to describe the attributes of the HTML5 input elements, explain the different input type attributes such as tel, email, date, time, number, range, and color, and importance of implementing validation fallback. The input type equals color/attribute allows the user to select a color. The dialog varies depending on the browser, and some browsers don't support this input type. In non-supporting browsers, this input type is displayed as a regular text input field into which the user might type a valid color name or color code. The input type equals date attribute is a date control, year, month, day, with no time zone. The example shows the input type equals date field as it is seen in Google Chrome. The input dialog varies from browser to browser. The date time local attribute provides input for a date and time, year, month, day, hour, minute, AM, or PM with no time zone. The date time local input field is displayed as a drop-down calendar in the Google Chrome browser. The time can be typed or entered using the spinner control. The input type equals email attribute is displayed as a regular text input field. It provides feedback when the input does not follow the email format. The input type equals number takes a numeric value as input. You can optionally specify the minimum, maximum values, step size, etc. The example shows the number selector in the Chrome browser. Only the numbers between 5 and the 10 are available for selection. The input type equals range takes a numeric range as input. The example shows the number selector in the Google Chrome browser. Only the numbers in the range of the minimum and the maximum are available for selection. The range attribute displays a slider with a range of values between the minimum and maximum. Only the slider itself is shown. Additional JavaScript code is needed in order to display the value of the slider. The differences between input type equals search / and input type equals text / are mostly in style. WebKit-based browsers return a history of recently searched text strings. The search input field on the Safari browser has rounded corners. The input type equals tel pattern equals parameters attribute expects a telephone number as input. On its own, the input type equals tel provides nothing more than a text entry field in the browsers. It does not enforce numeric-only input since many telephone numbers include other characters, such as the +sign and hyphens. You need to supply your own pattern matcher if you want the browser to validate the telephone number. The URL attribute is used to validate that the user typed in a properly formatted URL or web address. The input list equals some list uses the data list feature, not to be confused with the select element. The data list options are only suggestions, useful for autocomplete functionality. You can fill the list by nesting option elements inside the data list tag. These options are the types of fruits listed in the drop-down list. Placeholder text is used to provide hints of what the input text format looks like. The placeholder fills the input text field with the example values in a lighter shade of text. The form does not submit the placeholder text value if the input text is not overwritten. The required attribute implies that some text must be typed. The requirement to type some input applies even if the field contains placeholder text. What happens if browser-based validation is not supported for these input attributes? There are several options to performing validation in browsers that do not support all HTML5 input attributes. You can use JavaScript and jQuery libraries. You can assume that more browsers will support these features over time and leave all final validation to server-side processing. You can code client-side validation that is attached to the form submit event handler to validate all the fields on the form when the form is submitted. In this video, you learned common attributes of the input tag and how to implement validation fallback. Welcome to Insider's Viewpoints, Enhancing the User Experience with HTML5. In this video, we will listen to several web development professionals discuss using HTML5 features that enhance the user experience. So, what are some of the exciting features in HTML5? And how do they enhance the user experience? Can you include some advice and best practices for the new learner?
HTML5 introduced several new input fields for web forms to enhance user experience. Developers can use these input fields to display customized virtual keyboard layouts and build-in data validation. For example, using an email input field, the user is shown a custom keyboard containing @ or a .com for handy autofilling of the field. HTML5 has native video support and can be directly built into the supporting browsers, which allow faster, high-quality videos to be distributed. This also has a positive impact on the SEO of a web page. HTML also supports geolocation, which is of tremendous importance when developing location-based applications or services.
Hello, and welcome to CSS, Styling HTML. After watching this video, you will be able to explain what a Cascade Style Sheet, or CSS, is, describe how to use CSS to format HTML elements, describe how to use CSS in HTML documents to format web pages. By using a combination of HTML5, JavaScript, and cascading style sheets, developers can create web pages that can be displayed on desktop computers and mobile devices. These technologies have powerful features that can be used to show rich interactive applications without requiring plug-in technologies like the Flash Media Player. HTML documents might be rendered to a browser window or through a speech synthesizer to provide assistive technologies for vision-impaired people. Being able to meet accessibility requirements is one advantage of using HTML markup over browser plugins for delivering interactive content. CSS is the design that is layered over the top of an HTML web page. CSS is a style sheet language that describes how HTML elements are displayed. What makes the style sheet cascading is that developers can apply CSS to create a uniform look throughout each element of each page of the website. Child and descendant elements often inherit styles that are defined for parent elements. However, exceptions to this rule do exist. For websites, it is an important concept to separate the data from the design. The data is sent to the browser by using HTML, and the design is applied to that data by using a CSS. This separation allows people to render a web page without your design if they have special accessibility needs. It allows machines, such as search engines, to index a website without the design interfering. You can code CSS as a style attribute in an HTML tag, a head section of a document, or an external document. The preference is to code CSS in external documents, referred to as style sheets. You can use CSS to control a document's appearance and specify style rules for the following web page elements: fonts, text, colors, backgrounds, sizes, borders, spacing, positioning, visual effects, tables, and lists. CSS style elements are structured like this. In this example, the HTML tag name can be one of the following elements. Any tags you find in HTML code. For example, a, div, li, or label, etc. An ID reference that is displayed with a preceding hash symbol in CSS code. A class reference that is displayed with a preceding dot or period symbol in CSS code. When making a site design, begin by establishing the base style. Establish a base style by styling the body tag as shown here. This example makes the following styles. Sets the background color to off-white using background color. Ensures that the font color is black using color. Ensures that all content edges match the edge of the browser window frame using margin and padding. Horizontally aligns the textual content to the left using text align. Sets the font size to the browser's default using font size, and uses a sans serif, a font without the little flicks around the edges, as font family using font family. These settings are simple. Generally, follow these guidelines. When a color is specified, use red, green, blue, or RGB, hexadecimal light values. When a size is specified, use pixels, indicated by a PX after the number, an M, which is indicated by EM after the number, that is, the size of the font multiplied by the specified number, or a percentage, which is indicated by a % sign after the number. Text can be aligned left, right, or center. Floats can also be left or right. Vertical alignments must be top, middle, or bottom. Fonts can be any specific font or font family, serif, sans serif, or monospace, or even a downloadable font. One of the most important decisions you must make when you are determining the design of your website is whether to use a fluid or a fixed layout. A fluid layout is a layout in which the height and width of elements is flexible and can expand or contract based on the browser window, the operating system, and other user preferences. You specify these elements mostly by using percentages and ems. A fixed layout is a layout where you specify the height and width of elements, and those values remain the same regardless of which operating system or browser you use to access the website. You specify these elements mostly by using pixels. When determining the layout, consider also the pros and cons for fluid and fixed layouts. The type of layout you choose depends on the type and amount of content and the target audience of the website. To apply a CSS, you must tell the browser where to look for it. This step is the only true point where HTML references a CSS. You can make the reference in one of three ways. First, there's inline CSS. This is used for a single HTML element, but the HTML document can get messy very quickly as more styles get added. To use this method, insert the style attribute inside any HTML element. Then there's the internal CSS. This is used for a single page, however, it dirties the page with a non-HTML code. If you copy and paste this style on each page, this approach increases the load time of each page, which causes the user to wait longer. To use this method, the style tag must be used with your CSS code inside. Finally, there's the external CSS. This method is used to style an entire website. You can link to it from other pages, which ensures a clean HTML and a smaller page size. To use this method, the link tag must be added to the head tag section in your HTML code. While it's not recommended, it is possible to use a combination of all three ways. In this case, if more than one CSS method points to an element, the type with the highest priority will override the others and be applied to that element. The order of precedence for CSS styles is inline CSS, which has a higher priority than internal CSS, which in turn has a higher priority than external CSS. In this video, you learned CSS creates a uniform look throughout each element of each page of the website. CSS design is separate from the data. Design can be removed for special accessibility renders, and search engines can index the website without the design interfering. CSS is usually coded in external style sheets, and you should create base styles for your website first. You also learned you must choose a layout type, fluid, where the height and width of elements is flexible and can expand or contract, or fixed, where the height and width of elements remains the same. And finally, HTML references CSS in 3 ways: inline CSS, internal CSS, and external CSS. Welcome to CSS Frameworks. After watching this video, you will be able to differentiate between the different types of CSS frameworks, list the advantages and disadvantages of each type of popular framework, and identify popular CSS frameworks and how to use them. Recall that a framework provides a foundation on which you can build your code. CSS frameworks specifically can provide you with all of the tools you'll need to spin up a basic user interface or UI. This makes it easier to implement various visual elements on a page, which can include navigation bars, forms, and grids, and to create dynamic and responsive websites, which can make a website suitable for any screen size. Since frameworks must be used from the creation of your project, it is important to know about different types of frameworks available. Different frameworks focus on different features, so it's important to identify which are the most important to your project when deciding which framework to use. There are 2 types of CSS frameworks: utility frameworks and component frameworks. Using no framework at all and just using plain CSS, also called vanilla CSS, requires you to write all of the styling on your own. This gives you the freedom to style everything exactly as you want it, but also requires a lot of time and effort as you must style every component. An alternative to this is to use a utility framework, which gives you utility classes that scope to a single CSS property. This makes it easier to apply CSS properties directly in your HTML code, which can save a lot of time while still giving you the freedom to style components as you wish. Component frameworks provide you with pre-styled components and templates, which are easy to add to any website. This requires little knowledge of CSS and makes it easy to keep consistent styles, but also limits you to only the components made available by the framework. Utility-first frameworks provide you with an easy way to reference CSS properties. These typically come in the form of classes called utility classes, which scope to single-purpose CSS classes. Instead of having to write out the entire CSS property, utility-first frameworks allow you to use a property by referencing its corresponding class within the class attribute of your desired HTML element. For example, instead of using the text-align : center : CSS property in your code, a utility-first framework might have a self-descriptive class, such as text-center, which does the same thing when added to the class attribute of an HTML element. They make it easy to be consistent with color choices, spacing, typography, shadows, and everything else that makes up a well-engineered design system. However, having these styles mixed into your HTML classes reduces the separations of concern within your code, making your HTML markup more verbose. Since utility-first frameworks involve adding many classes to your HTML markup, this often causes the download size of your markup to increase and potentially slows down your web pages. A popular utility-first CSS framework used today is Tailwind CSS. It is packed with classes that can be composed to build any design directly in your markup. For example, say you want to style a link to indicate it's dangerous. You could underline the link text and change the text color to be red, as well as make the link a darker shade of red when hovered over. Doing this in vanilla CSS would require this code where you need to specify what the link looks like regularly and when hovered over in 2 separate sections. However, with Tailwind CSS, it can easily be done within the class attribute directly in the HTML, which can save a developer time. The hover portion of the Tailwind CSS is a special type of class called a modifier, which can be used with any other Tailwind class and is only applied when a user hovers over that element. There are many instances of modifiers in Tailwind CSS, some of which can make it very easy to create responsive websites fit to any screen size. For example, adding MD: before a class will only apply the class when a user's screen size is greater than 768 pixels wide, which is defined by Tailwind as a medium-size screen. This code will display an image with a width of 16 or 64 pixels by default, a width of 32 or 128 pixels on medium screens, and a width of 48 or 192 pixels on large screens. This saves developers a lot of time when styling many different elements, allowing them more time to focus on the back end. It also provides them the freedom to style elements however they want. Component frameworks provide pre-styled components which can be easily added to your code. This results in the ability to develop well-styled websites rapidly as significantly less time needs to be spent styling each element. It also makes it easier to keep all related elements styled uniformly, as you can simply choose the same or similar styles each time. However, having all of these predefined styles limits you to only what the framework provides and doesn't give you the freedom of customizing everything exactly as you want it. They also provide a lot of overhead code that you wouldn't otherwise get if you choose not to use any frameworks, as component frameworks will often provide you with more components than what you'll use. One of the most popular component CSS frameworks in use today is called Bootstrap. It allows you to build fast, responsive websites with a feature-packed front-end toolkit. If we take our example of adding a red danger link to your web page, which we saw earlier, we can see how much easier this would be with Bootstrap. Recall how to add this with vanilla CSS and Tailwind CSS. Now, Bootstrap provides a red danger link as one of its many components, and so adding this can simply be done by using the link danger class. Seeing all of these side by side, it becomes clear that for this example, Bootstrap has the easiest implementation of a danger link. However, this may not always be the case. In addition to providing individual HTML components such as buttons and links, Bootstrap also supplies entire templates which range from anything as comprehensive as an entire website to a simple sign-in page. As a whole, all of Bootstrap's components and features save time designing web pages and make it easy to remain consistent with styles throughout a website. Its ease of use also means that you don't need to be an expert in CSS to use it. Only limited knowledge is needed to use its basic features. However, it is important to keep in mind that it's limited in the components it can provide and may not have the ones you're looking for. In this video, you learned that CSS frameworks make it easier to implement UI elements and create mobile-friendly web pages. Plain or vanilla CSS lets you write all of the styles and layouts of a website on your own. Utility-first frameworks provide you with utility classes to help you build your own styles and layouts. Tailwind CSS consists of classes that are composed to build designs directly on the markup. Component frameworks provide you with a wide selection of pre-styled components and templates which can be implemented onto your website. And Bootstrap allows developers to build fast, responsive sites with its feature-packed front-end toolkit. Hello, welcome to the JavaScript language, overview, and syntax. After watching this video, you will be able to describe JavaScript primitives and objects. JavaScript is a scripting language that is derived from the ECMAScript standard and originally designed to run on the Netscape Navigator browser. Virtually all browsers now support JavaScript. Although the name Java appears in the word JavaScript, the two languages are not related. When a JavaScript interpreter is embedded in a browser, the result is the ability to create dynamic web pages. JavaScript adds behavior to otherwise static web content. The content of a web page can be dynamically changed with the scripting capability of the JavaScript interpreter. JavaScript code acts on the document object model that the web browser generates. One of the ways that server programming and browser scripting work together is an architecture that is called AJAX, or Asynchronous JavaScript and XML. The term AJAX encompasses more than asynchronous server calls through JavaScript and XML. AJAX represents a series of techniques that provide richer, interactive web applications through HTML, JavaScript, cascading style sheets, and modifying the web page through the document object model. Nowadays, JSON is commonly used instead of XML. In JavaScript, there are 5 primitive types that are associated with various primitive values. Number, all numbers such as 0 or 3.1412. String, all strings such as hello world. Boolean, the values true or false. Null, the value null. Undefined, the value undefined, since a data type has not been assigned or the variable does not exist. All other non-primitive data types are objects. The number primitive represents both integer and floating point values. The value NaN, not a number, and infinity. Integers can be coded as base 10, decimal, base 8, octal, or base 16, hexadecimal values. The integer literal, 16 in decimal, 020 in octal, and 0x10 in hexadecimal all have the same value. All numbers in JavaScript are represented internally as double precision, or 16-bit floating point numbers. JavaScript strings are delimited by either double or single quotation marks. There is no behavior or methods that are associated with primitive data types. The primitive types number, string, and Boolean can be wrapped by their object counterparts. Wrapper objects have the same name as the primitive type, except that they start with an uppercase letter. Like most object-oriented programming languages, JavaScript provides built-in ways to convert between these wrapper objects and primitive values. The wrapper objects use special methods such as the value of and toString methods to convert between objects and primitive literals. The type of keyword in JavaScript is used to find out the data type of the supplied operand. Notice how strings created without the new keyword have a type of string. The keyword new is used to create the string wrapper object. This object can be converted to a primitive string type by calling the value of function on the object wrapper class. Arrays are specialized collection objects that aid the programmer in the storage and retrieval of data by indexed keys. Arrays use a zero-based indexing scheme, meaning that the first element of an array has an index of 0. Arrays grow or shrink dynamically by adding or removing elements. The length property holds the number of elements that occur in the array. Arrays can be declared by using either an array constructor or an array literal. When declaring an array with a constructor, you use the new array keywords and specify the array elements as parameters of the new array. Array literals are created by declaring the array elements within square brackets. You then assign the array to a variable, as seen in the last example on the slide. The date object is a specialized object that is used to hold the date and time. The constructor for a date object is in the format new date and takes optional parameters. If you create a date object without any parameters, JavaScript returns an object that contains the current local date and time. If you send this date object to the console or try to display the date object on a web page, JavaScript automatically applies a toString method to the object. The result that is displayed is a string version of the date as shown on this slide. You can also create new dates by passing parameters to the newDate function. Examples on the slide show how either string or numeric values can be used for the date parameters when creating new date objects. As with other object-oriented languages, JavaScript creates error object instances when an exception occurs. The error object instance includes two properties that contain information about the error. The message property contains a description about the error. The name property identifies the type of error, such as a range error. A range error is an error instance that is created when a numeric value or parameter is outside its valid range. Besides a generic error, there are 6 other core error types in JavaScript, 3 of which are shown on the slide. The other 3 are eval error, reference error, and syntax error. The error object can be extended to create custom error types. The last line of the slide shows the creation of a generic error object with a custom error message in the parameter field. In this video, you learned JavaScript is a scripting language that adds behavior to otherwise static web content. Primitives are values and have no properties or methods. Examples of primitives include number, string, Boolean, null, and undefined. Wrapper objects allow objects of corresponding primitive data types to be created. Wrapper objects can store a primitive value and provide methods with which to process it. Wrapper objects have the same name as the primitive type, but they begin with a capital letter to differentiate them from the primitive data type itself. Welcome to JavaScript Variables and Control Statements. After watching this video, you will be able to define JavaScript variable declaration, show how JavaScript uses variables, and identify JavaScript control structures. Variables are containers for storing data values, which can be used and modified throughout a program's execution. Variables in JavaScript are declared with the var keyword, followed by the variable name, as in the example var age. Variables can also be declared and initialized in one step, as in the example var age equals 54. You can assign a value to the variable at a later time or reassign the value of a variable. Since JavaScript is a loosely typed language, you do not need to declare the data type of a variable. The variable assumes the data type from the value of the field during assignment, and the type of a variable can change during program execution. Be careful about not initializing variables and not assigning them a value. If a variable is not assigned a value, then the value is not 0 or an empty string or any other default value. The variable value is undefined. Remember that the only keyword is var, and JavaScript has no way to know whether the variable is a numeric or a string or anything else until you provide a value. Therefore, by default, it cannot decide whether to assign a 0 or an empty string. Variable names or identifiers have the following rules. The name must start with a letter, underscore, or a $sign. Subsequent characters can also be digits 0 to 9, and identifiers are case-sensitive. Variables also have a scope. Variables declared within a function have a scope local to that function. This means that they exist within the function but not outside of it. Variables declared outside of a function have a global scope. Variables with a global scope can be used elsewhere in the JavaScript program. And variables declared without the var keyword have a global scope. Variables that are not initialized have a value of undefined. You'll learn about functions shortly. Conditional statements are the set of commands that are used to perform different actions for different conditions. In JavaScript, the if statement is the way the program logic decides which path to take based on the current values of variables or object properties. The JavaScript syntax for a decision begins with the keyword if, followed by the condition to test, then the statements that run if the condition yields a true result. The true processing follows immediately after the test condition and is delimited by braces, unless it is a single statement. If the condition resolves to false, the statements that follow the else keyword are executed. Indentation of the statements of a compound control statement is not required in JavaScript. However, a programmer can find that indentation helps in deciphering the control statement. Many JavaScript-aware text editors automatically indent the control structure to make it more readable. Unlike Java, there is no block statement scope in JavaScript. Having no block statement scope means that variables declared inside one if condition can be used outside the scope of that condition. JavaScript supports the switch statement as an alternate to the if, then, else control statements. The condition that is being tested is placed in parentheses that follow the switch keyword. The expression parameter of the switch statement can evaluate to any number or string value. The labels in the case statement are enclosed in quotation marks when the labels represent string values of the expression. The program looks for a case clause with a label that matches the value of expression and then transfers control of that clause, running the associated statements. If no matching label is found, the program looks for the optional default clause, and if found, transfers control to that clause, issuing the associated statements. The break keyword is used to prevent the code from automatically falling into the next case clause. The for loop repeats a series of statements for any number of times. The for loop takes 3 parameter arguments, namely the initial value, the condition that is being tested, and the increment expression. When the for loop runs, the following occurs. First, the initial expression is set. Second, the conditional expression is evaluated. If this condition evaluates to true, the loop statements run and the increment expression is updated. If the condition evaluates to false, the for loop terminates. If the loop does not terminate, control returns to the second step and the conditional expression is evaluated again. The while loop is another common loop in JavaScript. The loop repeats while the condition remains true. The while loop assumes that the condition reaches a conclusion and then exits the loop. Make sure that the condition evaluates to false at some point, otherwise the loop never terminates. In this video you learned variables are declared using the keyword var followed by the variable name. You can initialize variables at the time of declaration or assign a value later. You do not need to declare the data type of a variable. Variables take their data type from the value assigned and can change type during program execution. Variables also have a scope. Variables declared within a function have a scope local to that function. Variables declared outside of a function have a global scope. Variables declared without the var keyword have a global scope. When executing, the flow of the program is directed by control statements, including conditional statements like if, then, else, switch statements, repeat statements like for loops and while loops. Welcome to JavaScript Functions and Prototypes. After watching this video, you will be able to describe functions in JavaScript, describe prototypes in JavaScript, and demonstrate how to create a custom object. A function is a block of code which can be called from any point in a script after being declared. A function is made up of the following parts: the keyword function, the name of the function, parentheses with optional parameter arguments, curly braces with the logic. The last statement in a function block is the optional return statement that returns control back to whatever called the function. This example is a function that is named add. This function takes 2 parameter arguments and returns the sum of the arguments, or concatenates the 2 arguments if they are strings. Notice that you do not specify the data type for the arguments of the function. The data types are determined by the values of the arguments that are being passed to the function. There is no specific return type declared. The function returns whatever type is required. In this case, the return is a simple addition or concatenation of the input parameters. The action chosen depends on what data is provided to the function. If the values can be interpreted as numbers, they are added. If they can be interpreted as strings, they are concatenated. This is an example of declaring a function named car that accepts 3 arguments as parameters. A little further down, you specifically ask the function to run by declaring the statement var c equals new car with the arguments Meridian, Sabre GT, and 2012. In the car function, the keyword this refers to the current instance of the car object that is being created. In other words, an instance of car that is associated with the variable named c. Using the this keyword can differentiate whether you are referring to the global or local instance of a variable. The use of model in this example refers to the argument that was passed into the function, while the use of this model refers to the model property associated with the current instance of the car object. The getName function of car returns the make, model, and year of the newly created car object. Prototypes allow you to easily define properties and methods for all instances of a particular object. All JavaScript objects which can be created with the new keyword inherit properties and methods from a prototype. For example, the car object we created previously inherits the make, model, and year properties from the constructor function, which are implicitly defined in the car prototype. When a car object is created, that object inherits all the properties and methods that are defined by this prototype. Unlike objects, the methods and properties of prototypes can be changed with one call. So, if you want to add a new property to an object's constructor function, for example, you must add it to the function directly by adding it as an additional argument. It cannot be done simply by calling the object itself. With a prototype, however, it is possible to add a property or method with just one call. Since all objects have a prototype property, this is an easier way to add properties and functions to objects. Any object that gets instantiated inherits the current state of the prototype. If a prototype changes, all objects using it will automatically inherit the new properties and functions within that prototype. One way to change a prototype is via a script, which can override prototype properties and functions. Here is another example that uses a prototype to change car instances. This time, you add a method function called getName to the car prototype. Now, when a car object is instantiated, it also includes the getName function that returns the make, model, and year. All existing instances of the car object also inherit the getName method. Functions are usually declared first and not run until you specifically ask them to, as you saw in some of the previous examples. Auto-invocation or self-executing functions start running immediately after being declared. The functions and variables inside self-executing functions are only available to the code inside the self-executing function. Auto-invocation functions can also be unnamed or anonymous functions and have the format that is shown in the code block on the slide. Self-executing functions are often used to initialize data or to declare DOM elements on the page. In this video, you learned a function is a block of code which can be called from any point in a script after being declared. Functions can take arguments passed as parameters and can return results. By using prototypes, you can easily define properties and methods for all instances of a specific object. Prototypes exist for all JavaScript objects that can be created with the new keyword. To add a new function to the template for the object, modify the prototype for the object. Self-executing or auto-invocation functions start running immediately after they have been declared. The functions and variables are isolated from the rest of the script. Welcome to JavaScript APIs. After watching this video, you will be able to explain how to work with nodes, describe how to modify the content of an element, explain how to modify the inline style and attributes of an object, and describe how to use the window object methods and events. The DOM Level 1 core and Level 1 HTML specifications have too much detail for one unit. Instead, the remainder of the unit focuses on script functions and properties that are commonly used when working with HTML pages. Some of these common APIs used when accessing HTML DOM elements in web pages are seen on the slide. DOM elements are reviewed next. To retrieve a node referenced for an element of a document given an ID, use the document.getElementById function and pass the ID value as an argument. This returns one specific HTML or XML element if a matching unique ID is found on the web page. The getElementsByTagName function retrieves a node list of elements with a specified tag name. The node list contains an array of elements in your document. You provide the name of the element you are interested in, and an array of all elements with that name found in the document is returned. For HTML elements, the tag name parameter is the literal name of the HTML tag. If you run the function getElementsByTagName with a p as a parameter argument, a node list of all the paragraphs in the document is returned. This example shows how you can retrieve all the image elements from a web page by using the getElementsByTagName function and passing image as the parameter argument. The result is a node list that is assigned to the variable image set. In the next part of the code, you loop through the node list and concatenate the results into a DOM output stream. The src attribute is a common property for the image tag. The src attribute indicates the location of the image source. The document.write function adds the script-generated HTML to the document. You can use the DOM API function document.createElementTagName to create an element in the current document. After creating the element, you can use any number of functions to place the element in the appropriate location within the document. Examples of these functions include the InsertBefore, AppendChild, or ReplaceChild function that can be used to add the newly created element into the document. This example shows the source code for adding a node to a document. A new paragraph element is being created that includes a text node with the string "Hello World." The text node is then appended as a child of the paragraph element. Finally, the entire paragraph with text is appended as a child node at the end of the body node of the HTML page. The function element.innerHTML retrieves or sets the contents of an HTML element. The innerHTML property returns all child elements as a text string. With the element.innerHTML function, you can change the contents of an HTML element by setting it to a text string that can include HTML tags. Setting the inner HTML value of an element to a string removes all of the current child elements. The browser then parses the string and sets the contents of the HTML element. You can use the element.style method to retrieve or set the inline CSS style for a particular element. If you use element.style to set the style of an element, it overrides any setting from a CSS style sheet with one specific style. The way to set the style in JavaScript is with the format element.style.propertyname equals value. For example, if you had an element, div style equals color:blue. Here, the div tag is used to group block elements to format them with a color style. You can change the style of this div tag with the JavaScript statement div.style.color equals red. In contrast, the element.setAttribute style wipes out all previous set inline CSS styles. The function element.setAttribute with parameters attribute name, attribute value dynamically modifies the attribute of an element. In the example, the src attribute of an element with an ID of the image is set to a different target image. The function element.removeAttribute, attribute name, removes an attribute from an element. The function element.getAttribute, attribute name, retrieves the value of the specified attribute in the element, if it exists. Here are some window object functions and events. To open a new browser window, use the window.open function. This method returns a reference to the new window object. You can use this reference later to close the window with the reference name followed by the close function. The parameters of the window.open function are URL, a string that indicates the location of the web page to be displayed in the new window. You can pass an empty string if you are going to write some script-generated content to the new window in the current URL content. Name, a string that specifies the name of the window. Features, an optional string that specifies the features of the window, such as its placement and dimensions. The features string is a comma-separated list of name-value pairs. Replace, an optional Boolean value. If true, the new location replaces the current location in the browser history. The window.onload function can be used to start a function after the page is loaded. The function window.dump message writes a string into the console for the web browser. The dump function is a less intrusive way to display diagnostic information than the alert method. Finally, the window.scrollTo x value, y value scrolls the web browser to a particular set of coordinates on a page. The onload event handler runs in the current window after the documents load the web page. In this example, the onload event causes an anonymous function to run. This function, in turn, runs the function addPara. In this video, you learned you can retrieve a reference to a node using document.getElementById returns one specific element that is based on the ID attribute. Document.getElementsByTagName retrieves elements with the specified tag. You can create an element using document.createElementTagName and place it using insertBefore, appendChild, or replaceChild. You can modify elements using element.innerHTML to retrieve or set the contents of an HTML element. Element.style to retrieve or set the inline CSS style. Element.attribute to modify the attributes of an element. You can manage a window object using functions including window.open to return reference to a new window object for the web browser. Window.dump message to write a string into the console for the web browser. This is not an exhaustive list. Many more functions exist that enable you to work with HTML elements and nodes. Welcome to client-side JavaScript with HTML. After watching this video, you will be able to define a client-side script, give examples of when client-side script can be used, explain how to use the NoScript tag, describe event bindings in scripts. A client-side script is a program that accompanies an HTML document, or might be embedded directly in the HTML document itself. The script program runs on the client device when the document loads, or at some other time such as when a link is activated or when a button is clicked. Although JavaScript is widely used as a scripting language in HTML, other scripting languages can be used instead. Scripts offer authors a means to modify and extend HTML documents in highly interactive ways. Scripts can run after an HTML document is loaded. Scripts can be used to validate forms or to process input as it is typed. Scripts can be triggered by events that occur on a web page, such as the clicking of a button. Scripts can be used to dynamically create document elements on an HTML page. This slide shows two ways in which the script tag is used to include scripts in an HTML document. Example 1 demonstrates how you can include a script directly inside the HTML document. This method is good for short scripts, but when a script is long, the method used in example 2 is preferred. Example 2 uses the src attribute to point to an external script file. This method has several use cases, such as importing JavaScript libraries for complex interactions or using the same script across several HTML documents. Some users who visit your website might disable JavaScript from running, or they might be using a browser that does not support scripting. To allow for these situations, place the content for the alternative path within the NoScript tag. If the browser does not support scripting, the browser runs the section of the code that is within the NoScript tag. Scripts can run on the detection of certain events that happen when the page is running in a browser session. Calling a function when an event occurs is called event binding. For example, the onload event can run a script when the browser finishes loading a page, or a function can be performed when the onClick event occurs. This event occurs when the pointing device is clicked over an element, such as a button, that declares a handler for the event. The event handler is a function that declares what to do when the button is clicked. Other useful events include onMouseOver, which occurs when the cursor is moved onto an element. Here, the inline event handler named showAnswers runs when the button is clicked. In this video, you learned a client-side script is a program that accompanies an HTML document. It may even be embedded into the HTML itself. Scripts offer developers ways to extend HTML documents to enhance the user experience, especially by incorporating more interactive elements. You can use the script tag to include a script within the HTML document, or to call a script from an external file. Use the NoScript tag to provide an alternative when scripting is disabled. Scripts can be bound to events so that they run automatically. For example, the onload event can run a script when the browser finishes loading a page. Welcome to Insider's Viewpoints, JavaScript Best Practices. In this video, we will listen to several web application professionals discuss best practices from their experiences with JavaScript. Can you share with us some best practices from your experiences of working with JavaScript?
Okay, I want to share 3 best practices that I've learned over the years working in this field, especially with JavaScript. So first is use of IDEs. I love using something like VS Code or WebStorm to write code. The content assist and being able to look up functions and documentation and classes all within the same editor is very powerful to me, and it's very effective. It makes me a more productive developer. My second advice would be to use linters. So if you're new to JavaScript and you don't know what linters are, they help you write standard code. Now, I don't mean standard in terms of ES6 standard, but this could be standard in terms of how your team decides to write functions and documentations. And this is very important when it comes to version control and resolving conflicts. It makes your life a lot easier. And finally, my third tip would be to learn the different paradigms and patterns in JavaScript. So assuming you're using JavaScript for your front end and or back end, learn how to modularize code in JavaScript. Learn how to then import or structure your code so it's easier to unit test. Structure your code so it's easier to import other packages into your application.
So working with JavaScript has changed a lot over the years. It's actually pretty robust nowadays, and there's a lot of tools you can use for it. I definitely would recommend linting your JavaScript. One really great tool that I personally use is called XO, spelled XO. It's a great linter that has some great default set, and you just run that on your code, and it makes you follow specific standards, styles, so that you and everyone on your team make sure that your code looks good, but also hopefully reduce the amount of bugs and confusion in your code. I'd also recommend using TypeScript. It's a wonderful addition to JavaScript that often can just be plonked right on top of a current JavaScript project without needing to change much code at all. And then you can add a whole significant set of features onto your code to make it much better.
While working with JavaScript, avoid declaring global variables and functions. Global variables can slow down your program since they are not deleted until the window is closed. Also, scripts that include same variable and run after your code will override your variables. In order to reduce page load times, place your JS at the bottom of your page, especially if the purpose of JS is to add functionality after an event occurs. When declaring lengthy for statements, declare variables outside of the for statement. You should also optimize loops. For example, instead of reading the length attribute of an array at every iteration, store the length value in different variable. Always comment important sections of your code so that you or your colleagues can understand the purpose of the code when you need to revise your code.
So when writing JavaScript, I really like to take advantage of the features in ES6 because it can make my code look cleaner, easier to read, and just more beautiful, such as the arrow functions or the ... operator. And so I encourage you to, after learning JavaScript, dive into ES6 a bit and have fun with it.
One best practice for JavaScript developers to keep in mind is to avoid the use of global variables. You might have heard this advice for other programming languages as well, and the reasons there apply here as well. But with JavaScript specifically, the risk of name collision is quite high. So it's very common for developers to include their code as well as third-party libraries on the same page. And all of these scripts will share the same global context, which means if you happen to pick the same name for a global variable as one of those third-party libraries, basically one or both of your programs will not work.
JavaScript is a very powerful language. It lets you do pretty much anything you can imagine, including shooting yourself in the foot if you're not careful. The practices I typically follow with JavaScript include proper scoping of variables and functions, and writing unit and integration tests for my features.
Welcome to Client-Side JavaScript with Dom. After watching this video, you will be able to describe the document object model, or DOM, hierarchy, describe the window and document objects, identify the DOM objects that are commonly used in JavaScript applications for working with HTML documents. The document object model is the programming interface between HTML or XHTML and JavaScript. The Document Object Model, or DOM, is a browser-based interface for applications and scripts to dynamically access and update the content, structure, and style of documents. JavaScript uses the DOM to access and modify web page elements in the web browser. The World Wide Web Consortium released 4 levels of the Document Object Model specifications. Each successive level provides a more detailed set of features for describing structured documents. The different browsers have various levels of compatibility with the DOM standard. The discussion of the DOM in this unit focuses on the DOM Level 1 core and DOM Level 1 HTML APIs to access HTML elements with the DOM. The JavaScript engine in most web browsers fully supports DOM Level 1. Here is a representation of the basic DOM model for browsers. The window object is at the top of the DOM hierarchy and controls the environment that contains the document. The history object keeps internal details about the recent history of pages in the browser. The history object has methods for letting you simulate clicking the back or forward buttons in a browser. The location object contains information about the URL of a page. The navigator is an object representation of the client internet browser or user agent. There is no standard that applies to the navigator object, so the property values returned when running queries on the navigator object are not consistent across browsers. The screen object is used to derive information about a user's screen, such as the dimensions of the display screen. The screen object is useful for determining the screen size of browser windows that run on mobile devices. The document object provides access to all HTML elements within a page. Each HTML document that gets loaded into a window becomes a document object. The window object is the outermost global container of all the objects in the DOM hierarchy. When the browser loads a page, a window object is automatically created for you. You can then access the window object properties and functions from your JavaScript code. In client-side JavaScript, the window object serves as the global object, and everything in the DOM takes place in a window. A number of predefined methods exist for the window object. The window.alert, window.confirm, and window.prompt dialogues that are used in web pages come from the global window object. You can leave out the window prefix for methods in the DOM API, so the window.alert method can be coded more simply as alert with a message argument. This figure shows the object model for a simple HTML document. Notice how the object hierarchy matches the HTML containment hierarchy on the left. The object diagram can also be represented as a tree structure that corresponds to the structure of the HTML document. The branches of the tree structure are termed nodes. There are 2 types of nodes in the W3C DOM: element nodes and text nodes. All HTML tags, HTML, head, meta, title, and body, are element nodes. The nodes that contain actual text that go between an element's start tag and end tag are text nodes. The figure shows the DOM Level 2 tree for the form portion of the document. The line feeds between elements are text nodes and are part of the DOM Level 2 tree. The DOM Level 2 tree includes a line feed text node before the paragraph and input elements. The input element includes a text node that contains all the text that follows the input tag. An additional line feed text node follows the input element. The DOM Level 0 for the form portion of the document would have only the form, P, and input boxes. The DOM Level 2 adds the carriage returns, tabs, and spaces, sometimes referred to as white space. In this video, you learned the Document Object Model, or DOM, is the programming interface between HTML or XHTML and JavaScript. Each successive level of the DOM provides a more detailed set of features for describing structured documents. Different browsers have different levels of compatibility with the DOM standard. The basic DOM for browsers is a hierarchy that includes objects that perform different functions. For example, the window object controls the environment of the document. The location object contains information about the URL of the page. Screen object derives information about the user's screen. And the document object provides access to all HTML elements within a page. DOM levels define object types with which developers can build a variety of documents, from plain HTML documents for web pages to more complex forms. Welcome to JavaScript DOM objects. After watching this video, you will be able to list related node types, show how to access doc elements, and explain object naming. The W3C DOM Level 2 defines 12 different types of nodes, 7 of which have direct applicability in HTML documents. Node types that are not applicable to HTML are omitted from the table. This table is of interest so that when you view a DOM tree, you understand the meaning of the numeric node types. Each node type is a named constant that is also represented by an integer value. So, for example, an element node type is represented by the integer 1. An attribute node type is represented by the integer 2. A text node type is represented by the integer 3. A comment node is represented by the integer 8. In the DOM tree, the node name for element node type is the name of the element or tag. For example, if you are looking at a div element, the node name is div. If the div element has an attribute like id equals div123, then the attribute name is id and the attribute value is div123, which is the name-value pair. Another example, if a paragraph element is followed by some text, the text string has a node name of #text, and the node value is the text string itself. The table lists some of the DOM Level 2 node object properties and corresponding data types. You see these properties when you view a DOM tree for an HTML page in a browser's developer tools like Chrome's DevTools. So how do you access the elements on an HTML page with the DOM API? When the document is loaded, the browser creates arrays for forms, images, anchors, links, applets, and embeds. It then places all the objects of each type into these arrays. The arrays are indexed as they occur in the source document. The first index of each array starts at 0. Each of the array types, such as forms, contains an array of elements with each index element being the fields or buttons that occur in that form. You can reference the element named field 1 in the figure by its relative position as document.forms0.elements0. You can reference the same field with named elements, for example, document.forms form1.elements field1, or even the shortened document.form1.field1. Since only one document can be contained in a window, shown by the dashed line in the figure, you can leave out the window prefix. However, you cannot omit the document prefix from the referenced object. The ID attribute identifies an element in a document. The ID attribute of an element is used by scripts to refer to the element with a name that matches the value of the ID attribute. In order to assign a scriptable reference name to an HTML element with the ID attribute, use the following conventions. The ID must be a unique name in the document. The name must be in quotation marks when assigned to the ID attribute. The name must not start with a numeric digit. The function that is used to return a node object that matches the ID value is document.getElementById, with the name of the ID as a parameter argument. It is suggested that the same value is used for both the ID and the name attribute, seen earlier, when both are used. In this video, you learned how to list the related node types, how to access nested objects using a dot notation, and how to name objects to make accessing them from the script easier.